हेलो।
ईयरफोन है ना लेकिन मेरा चल रहा है, आपका चल रहा है।
बंद करो ना। We are waiting for a few more guests. Very soon we will begin our today's session. Please be seated. And those who can hear me outside this hall, please come inside and take your seats.
हेलो 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 हेलो
हेलो हेलो ठीक है। I request you all to please be seated. I request you all to please be seated. Take your seats. I know waiting is always the longest thing which we all feel. बट ऐसा कहा जाता है कि इंतजार का फल मीठा होता है और मीठा ही नहीं होगा आप सभी के इंतजार का फल लेट मी एश्योर यू कि मीठा ही नहीं बल्कि बहुत ही फ्रूटफुल भी होगा नॉलेजेबल भी होगा All of you, those who are outside this hall, please come inside and be seated.
ये कनेक्ट हो गया, वहां रख दो पीछे लैपटॉप, ये फोन चल जाए।
This is a humble reminder to those who have just joined us. Please turn your mobile phones to silent mode so that we can begin with the session and continue with the smooth conduction. Ladies and gentlemen, hold on to your hearts. Very shortly, our guests will be here. Our chief guests and guest of honor have already joined us. Hello and namaskar to everyone. I welcome you all to this magnificently glorious day. Our long-awaited moment is finally over. Our honorable chief guests, Padma Shri Professor V.K. Singh, Professor Ganesh Pandey, Professor and Scientist P.M.S. Chauhan, our Honorable Vice Chancellor, Professor Rajiv Jain, have already joined us. May we have a big round of applause for them. The energy seems low. May I request again, may we have a big round of applause for them. Thank you very much. Ladies and gentlemen, today we are gathered here for the inaugural ceremony of the International Conference on Frontiers at the Chemistry and Life Sciences Interface FCASI 2023, jointly organized by the Department of Chemistry, University of Rajasthan, Jaipur, in association with Rajasthan chapters of Chemical Research Society of India and Indian Society for Chemists and Biologists. Distinguished guests, respected dignitaries, eminent speakers, dignified faculty members, media persons, and dear participants from the various parts of the country and world. I, Dr. Preeti Sharma, on the behalf of the organizing committee and on my personal behalf, heartily welcomes you once again to this galaxy of intellectuals. May I now request our today's chief guest, Professor V.K. Singh, Professor Ganesh Pandey, our guest of honor, Professor P.M.S. Chauhan, our Honorable Vice Chancellor, Professor Rajiv Jain, Head of the Chemistry Department, Professor Meenakshi Jain, and convener of the conference, Dr. Satpal Singh Batsara, to take their dedicated seats on the dais. May we have you all here. I request you all to once again give them a big round of applause. Thank you very much. To begin this ceremony, as a part of custom and culture, may I request you all to please rise as a mark of respect for the University Trilgeet. Thank you, everyone. You may please all take your seats. At this very initial stage, I find it's very apt to quote here that light symbolizes knowledge and divinity. It not only dispels darkness from us, but also it illuminates our souls. And thereby, following these words, I may now request all the respected dignitaries to kindle the auspicious lamp to embark on today's proceedings. May I request you all, please?
Only play.
Ladies and gentlemen, it is indeed a pleasurable day. Now, it is time to welcome our guests formally. May I now request Honorable Vice Chancellor, University of Rajasthan, Professor Rajiv Jain, and Dr. Asha Gurjar, Organizing Secretary of this conference, to heartily facilitate Professor V.K. Singh with a plant sapling and memento as a symbol of prosperity and growth. Thank you, sir, and Asha ma'am. Now I request once again our Vice Chancellor, Professor Rajiv Jain and Dr. Pragati Pagiria, Organizing Secretary of this conference, to kindly facilitate Professor Ganesh Pandey. Professor Ganesh Pandey have joined us from Banaras Hindu University. Once again, I request Dr. V.S. Alani to join our Vice Chancellor for the felicitation of our another esteemed guest, Professor and Scientist, Professor P.M.S. Chauhan. He has joined us from Central Drug Research Institute, Lucknow. Taking the series of welcoming our guest, I further move and request Professor Meenakshi Jain, Head of the Chemistry Department and convener of this conference, Dr. Satpal Singh Batsara, for the felicitation of this head of the university fraternity, our Honorable Vice Chancellor, Professor Rajiv Jain, who, despite of his busy schedule, not joined us, but also kept inspiring and motivating us for the conduction of various such academic fests. Thank you, sir, for giving us your valuable time. I also welcome Professor Meenakshi Jain, who has always been a support system and guiding force for this department as well as for this conference. Thank you, ma'am. Ladies and gentlemen, the ceremony would have been next to impossible without the convener, Dr. Satpal Singh Batsara, who had worked day and night to bring this day in reality. Though Dr. Batsara has strictly denied a formal welcome, yet I'm doing it because I believe hard work must be acknowledged. Thank you, sir, for bringing this day and keeping us all together. Moving up next, this is the time for the official release of the volume of this international conference. May I request all the dignitaries on the dais to please take the copies of the abstract volume and publish it officially. Thank you, everyone. And now, taking the ceremony further, may I request Professor Meenakshi Jain for the welcome address. Madam. Good morning to everyone. Honorable Vice Chancellor, Professor Rajiv Jain, esteemed Chief Guest Professor V.K. Singh, and Professor Ganesh Pandey, Guest of Honor Professor P.M.S. Chauhan, Convener Dr. Satpal Singh Batsara, and all eminent speakers and delegates. It is my privilege and honor to welcome you all on behalf of Department of Chemistry, University of Rajasthan, and my own behalf to this August gathering. The Department of Chemistry came into existence in 1960, 30 years after the establishment of the University of Rajasthan, Jaipur. Current faculty strength includes 7 professors, 2 associate professors, and 37 assistant professors. Department offers MSc in chemistry and PhD courses at university campus and BSc pass and honors courses at 2 constituent colleges. It is heartening to note that the Department of Chemistry, University of Rajasthan, Jaipur is holding an international conference on frontiers at the Chemistry Allied Sciences Interface, FCASI 2023, along with the Indian Society for Chemists and Biologists, ISCB Rajasthan chapter, and the Chemical Research Society of India, CRSI Rajasthan chapter. I heartily welcome all dignitaries, distinguished guests and participants to this conference and congratulate the organizing team and appreciate their efforts that have materialized this event. The most enriching feature of this academic conference is that it brings together academicians, researchers, and delegates from industries to derive maximum benefits. I am confident this conference will provide an interdisciplinary platform at the interface of chemistry and allied sciences. The highly intellectual discussion that will take place during the conference hours will not only contribute to the present scientific knowledge, but also pave way for invaluable opportunities of research. I extend my best wishes to the organizing team FCASI 2023, a grand success. Thank you, ma'am. Taking the ceremony further, next I invite Dr. Satpal Singh Batsara, convener of the conference, to introduce this conference and give you a brief about the marathon of sessions you all are about to experience in the coming 2 days.
A very beautiful good morning to all of you. Respected Professor P.K. Singh sir, Professor Ganesh Pandey sir, Professor P.M.S. Swan sir, Honorable Vice Chancellor Professor Rajiv Jain, Head of the Department Professor Meenakshi Jain, my teachers, my mentors, my well-wishers, my colleagues, dear participants, media personnel, and friends. I welcome you, all of you, in this Augusta gathering, APCASI 2023. On behalf of Organizing Committee APCASI 2023 and my own, I extend a warm welcome to the galaxy of leading experts, academicians, researchers, and students from different parts of country and abroad participating in this international conference on Frontier at the Chemistry Applied Sciences Interface APCASI 2023, which is the 6th edition of this conference series. This conference we are organizing jointly in collaboration with Indian Society of Chemists and Biologists Rajasthan chapter as well as Chemical Research Society Rajasthan chapter. Although we shared most of the information on the conference website, but I take this opportunity to share with all of you that the 2-day technical sessions will be including 3 keynote lectures, 12 plenary lectures, 26 invited lectures, 4 short invited lectures, and along with this, there will be almost 250 presentations from young budding researchers. Also, it is worthy to mention here that the poster presentation will be recognized by American Chemical Society, Royal Society of Chemistry, and Indian Society of Chemists and Biologists in the form of Best Poster Award. I express my heartfelt gratitude to our Honorable Vice Chancellor, Professor Rajiv Jain, Head of the Department, Professor Meenakshi Jain, all my faculty colleagues, these scholars for their kindly help and cooperation at every stage. I take this opportunity to express my most sincere thanks and gratitude to keynote speaker, Professor V.K. Singh sir, Professor Ganesh Pandey sir, and Professor Lord Sakarman, who will be joining us through online mode, who have spared their time from their valuable schedule to be over here. I'm sure your presence will give young generation of researcher a new direction and motivation. I also put on record my special thanks to my PhD supervisor, Professor B. Basoya, for his blessing and mentorship. He was about to be here, but due to some unavoidable circumstances, he is not there. I also thank all my teachers from BHU, Professor K.N. Singh, Professor Maya Sankar sir, from my alma mater, Hyderabad University, from ISC, Priya Prasad sir, Professor Hota, Professor Ramna, Professor B.L.E. Prasad, I'm sorry if I missed some name, and my young friends from different part of this country to joining us over here and spending their valuable time. I personally thanks Dr. P.M.S. Swan, General Secretary IC, for his cooperation and invaluable help. Again, I'm extremely grateful to all the speakers and delegates who are participating in this conference. I'm sure that your deliberation would add new dimension to research in frontier of chemical science with emphasis on interdisciplinary approach. At this point of time, I would also like to thank Professor Nilima Gupta, Secretary CRSI, my good friend and mentor, Professor Mahesh Sharma, President ISB Rajasthan chapter, all the member of Conference Advisory Committee and team APCASI 2023 for extending their unconditional support in all respect for organizing this event. I also greatly acknowledge the financial support by all the sponsors. A special thanks to organized committee and volunteer. Without their unturning efforts, we would have not reached at this stage. I hope that you will have a pleasant stay and fruitful scientific interaction at APCASI 2023. The organized committee has spared no efforts in making your stay comfortable at Jaipur, but if there are any shortcomings, I sincerely offer my deep apologies. I hope that this conference will be inspiring and highly learning experience for all and will provide an exciting opportunity to establish contexts focused on forging new collaboration in research. Once again, it is my pleasure to welcome all of you at APCASI 2023. enjoy the presentation and have a great discussion. With this, I also like to inform that very soon the abstract volume will be appearing at conference website, or we'll try to send it by email. So please, for time being, and with this, I thank you and all of you. Thank you. Jai Hind.
Thank you, sir. Moving further, dear participants, ladies and gentlemen, now this is the time when we will hear out our eminent speakers from the various parts of the country. In this quest, I first request Professor P.M.S. Chauhan to please come and address the gathering. Professor Chauhan is working as a professor and scientist in Central Drug Research Institute, Lucknow. Please, sir.
Good morning, Honorable Vice Chancellor Ji, Jain Sahab, Professor Ganesh Pandey Ji, Professor V.K. Singh Ji, and convener of IHCV local chapter, Professor Mahesh Sharma Ji, Professor Kaushik Ji, Professor K.N. Singh Ji, and all members of scientific community. It is very important if you go through the title, Chemistry and Allied Sciences. Those scientists working in drug research area, they know the importance of the allied sciences. When chemists synthesize the molecule, but he have no idea bioactivity of those molecules. If synthetic molecule have no activity, no relevance for society. And here role of the allied science. Chemists alone cannot do drug research, one of the most important area. For getting the bioactive molecule, for sending molecule in market, the several discipline required. So you can understand the importance of allied sciences. And here I also want to just inform everybody, have the idea, out of 5 lakh molecules synthesized by chemists, only 6 molecules we can say the hit molecule. And out of 6 molecules, only 2 molecules can go in market, and out of 2, only 1 can survive. And investment for this process around $1 billion. So you can understand how important and expensive area of the drug research. So I always suggest my young chemist, develop the new methodology, develop the molecules, but always cooperate biologists and to know the bioactivity of the molecules. If you really want to serve the nation and the society. And here of Indian Society Chemist and Biologist. During 1995, Society Chemist and Biologist was formed at Lucknow at CDRI because we understand during 95 their great lab, there is no platform, they are in a single platform. Chemists and biologists come together and discuss their idea. So keeping in mind, now the Indian Society Chemist and Biologist, one of the largest society, we have the every year gathering of 1,000 people, not less than 7,000, 6,000, 30 chapters working, more than 4,000 members are there, and we still working hard to promote this organization. So in this world, we only request you, please join the Indian Society Chemist and Biologist for better promotion of the science. Thank you.
Thank you very much, sir. Thank you very much once again for your wise words. I'm sure the budding scientists here must have been benefited by your words of wisdom. Taking this program further, I now request Professor Ganesh Pandey, a distinguished professor from the Department of Chemistry, Institute of Science, Banaras Hindu University, to please address the gathering.
Honorable Vice Chancellor, Professor Jain, Professor V.K. Singh, Dr. P.M.S. Chauhan, Dr. Satpal Butsala, and friends. It's my pleasure to participate in this conference, and not only for myself, I see that many active researchers around the country, they have come together here and hopefully will make this conference very successful. And because of this, I would like to congratulate Dr. Satpal for taking initiative to organize such a wonderful meeting, which will, I'm sure that students and researchers from this university will be greatly benefited, because they will interact with the people from other parts of the country to see how the research should be done and what other people are doing, what are the future perspective for them, where to go, and what kind of area they should select to do research. So with this, I would like to once again thank you, all of you, for inviting me to this place. Thank you very much.
Thank you, sir. Thank you so much for your kind words. We have Professor P.L. Prasad, Professor Ramanna, Professor Mala, Professor A.K. Sahu. I request you all to please come forward and take the front seats. I request all the professors to please take the front seats. The professors I just took name, Professor B.L. Prasad, Professor Ramanna, Professor Mala Record, and Professor A.K. Sahu. Thank you so much, sir. We welcome you here. Professor Prasad. Professor K.R. Prasad, please. Thank you, sir. Ladies and gentlemen, now this is the time when we hear out our another eminent speaker, Professor V.K. Singh, Chair Professor, Department of Chemistry, IIT Kanpur. Sir is a Padam Shri recipient in 2014 for his pioneering contribution in the field of chemistry. Sir.
Vice Chancellor of this university, Professor Raju Jain, Professor Ganesh Pandey, Professor P.M.S. Chauhan, Professor Meenakshi Jain, Head of the Department, and convener of the conference, the most important person, Satpal Singh Batsara. Other invited guests, my friends, speakers sitting in the audience, I'm very happy to be part of this conference. In fact, I always like to come to Jaipur. Not because of city, of course city is wonderful, but mainly because the people of University of Rajasthan. This may be my nth visit to the university. The difference I see, I think the hall has been renovated, but still some things have to be done here. What I like about the conference, the title of the conference, these days people, it's a fashion. So people use all kinds of title, but the title here is very straightforward. chemistry and allied sciences, as Professor Chauhan mentioned. Basically, it covers everything. Chemistry has become so broad that even I do not understand my own sub-discipline, which is organic chemistry. This is bound to happen because of growth in research. I only like to draw attention from the students that listen to all the talk, take away something, keep your pen open and notebook open, write something. Don't listen like katha, and that will help a long way. Passion and hard work is very important, and it's more important in experimental science. And chemistry, it is much more important because it requires various kind of things, not knowing the chemistry, but other tricks and trades. And I'm sure you will learn a lot. I was happy to see outstanding speakers. So selection of speakers really is great, and I like to congratulate Satpal for that. Covering all areas and complex areas. I also like to request our Vice Chancellor. He has only 6 months left, but what I hear, the facilities in the department is still not up to mark in terms of instrumentation and all that. And if you think about University of Rajasthan, chemistry first thing comes to your mind because the people who are associated with this university. Before going, if he can give away some daan to chemistry so that they can have an MR and other instruments, I really appreciate it. And for that, even if you need my personal donation, I'll be happy to donate personal money. Just like building a temple, you give 10 rupees, 100 rupees. I think one NMR is must. I was happy to see a paper in ChemCom by Satpal, and that really is very nice, very nice. And with this, I close it because we started a little late to save time. And I wish all the best for the conference. And I look forward to my talk after this, of course. So nothing much to speak now. Thank you.
Thank you, sir. You stand tall amidst the gallery of educationists. We are highly honored to have you here. Dear all, with this, we are coming to the end of the inaugural ceremony. So before I call the another person, the speaker, I would like to make an announcement for the participants and the audiences. Please remain seated. After the immediate presidential address, we will begin our first session with the keynote lecture by V.K. Singh. Moving up further, I now request our Honorable Vice Chancellor, Professor Rajiv Jain, for the presidential address.
International Conference on Frontiers at the Chemistry Allied Sciences Interface. On this occasion, on the dais, Chief Guest Professor Vinod Kumar Singh. He is from IIT Kanpur. Professor Ganesh Pandey from Banaras Hindu University, Varanasi. Guest of honor, Professor PMS Chauhan sir. Conference on the dais, the head, the Professor Meenakshi Jain, HOD Chemistry. Convener of the conference, Dr. S.S. Batsera. In the hall, the Dr. Asha, organizing secretary team, Dr. Asha Gujar, Dr. Ria, Professor Dandia, Professor Asha Jain, participants from the country, dear students. I am delighted to offer a cordial greeting to the sixth journey of the frontier at the interface of chemistry and other allied sciences International Conference 2023. The conference is being hosted by the Department of Chemistry of University of Rajasthan in the association with two esteemed organizations, namely ISCV Rajasthan Chapter, CRSE Rajasthan Chapter, boasting an attendance of approximately 450 professionals from diverse regions globally. This August gathering guarantees a fulfilled and illuminating encounter for all participants. The current convention emphasizes on the growing importance of cross-disciplinary research in today's society. It is widely acknowledged that contemporary problems are complex and multifaceted, demanding a team effort that combines expertise from various knowledge areas to address them sufficiently. The blended of the chemistry with allied sciences presents an exciting opportunity for significant advancement in diverse areas such as healthcare, energy, material sciences, and environmental sustainability. This conference offers a chance for experts with different backgrounds to communicate their thoughts, showcase their latest discoveries, and investigate fresh pathways for cooperation. It brings me a great joy to observe the varied representation of individuals from parts of the globe, including esteemed scientists, emerging scholars, and the learners. The forthcoming presentation and dialogue guarantee to incite novel ideas and stimulate intellectual curiosity. I am confident that these events will lead to breakthrough and fresh discoveries. I would like to extend my warmest congratulations to Dr. Satpal Bharsera and his hard-working team for this a good job in hosting a high successful and informative conference. For the moment I arrived at the venue, I am impressed by the attention to detail and the level of organization that had clearly done into the planning, execution of the event. Overall, it is a truly understanding experience that I will always remember. Additionally, I would like to convey my thanks to our sponsors for their support. Without their contribution, it would not have been feasible to hold this type of conferences. Greetings to all attendees and visitors. My utmost wish is for you to have a productive and pleasant stay in the University of Rajasthan. In addition, I urge everybody to make the most out of this opportunity by immerse yourself in your city's remarkable cultural heritage. Thank you for your kind attention, hoping that this conference will be a fruitful and fulfilling experience for everyone here. Now, with that, but I have to speak some more regarding the Department of Chemistry of University of Rajasthan. वैसे तो राजस्थान यूनिवर्सिटी की इतनी बड़ी लेगेसी है, हिंदुस्तान में इस विश्वविद्यालय का नाम सर्वत्र है, राजस्थान और इंडिया को छोड़ के बाहर भी है, और खास तौर से सारे डिपार्टमेंट्स के अंतर्गत बड़े विद्वान यहाँ पर रहे हैं, जिन्होंने न केवल हिंदुस्तान बल्कि विदेशों तक अपनी सेवाएं दी हैं, अपने ज्ञान को वहां तक विस्तारित किया है। जहां तक सवाल स्पेसिफिकली इस डिपार्टमेंट का है, तो ये डिपार्टमेंट में पिछले साल ही 100वीं प्रोफेसर मल्होत्रा साहब का जन्म शताब्दी थी। उसके अंतर्गत उनके कुछ लोगों ने, उनके जो रिसर्च स्कॉलर्स हैं जो अमेरिका में हैं, उन्होंने हमसे संपर्क किया एंड दे वांट टू डू सम बिगर थिंग। जो अभी आपके क्या कहते हैं सिंह साहब बता रहे थे, मैं उसी रेफरेंस में बैठे बैठे ध्यान आया, तो उन्होंने इच्छा जाहिर की कि हम चूंकि क्या कहते हैं हम उनके स्टूडेंट हैं एंड वी हैव अचीव्ड ए लॉट, और हमने उनके ही ज्ञान से हमने अपना स्थान बनाया है। तो ऐसी स्थिति के अंतर्गत हम अभी तक तो इतना कर पाए हैं कि 10 लाख रुपए से एक गोल्ड मेडल उनके नाम से स्टार्ट करने का योजना बनी है, और वो एक तरह से इंप्लीमेंट हो गई है। अगले कन्वोकेशन में गोल्ड मेडल दिया जाएगा, और अभी तो बहुत कुछ उम्मीदें हैं। आपने ठीक कहा, कल ही हमारी सरकार में बात चल रही थी कि बहुत जल्दी रोस्टर फाइनल हो जाएगा, और सरकार भी कीन है। तो हो सकता है कि हम डिपार्टमेंट के अंतर्गत कई पोस्टों को यहाँ पर लाएं, और इसके पश्चात उस पे हम अपॉइंटमेंट्स की प्रक्रिया को भी आरंभ करें। जहां तक सवाल जब केमिस्ट्री की, एक तो वैसे आजकल केमिस्ट्री वर्ड साइंस का होने के बावजूद केमिस्ट्री किससे क्या मिलती है, ये भी आजकल एक वर्ड एक सोसाइटी के अंतर्गत बहुत हो चुका है। तो आजकल जैसे कि मैनेजमेंट में एक वर्ड है मार्केटिंग, नोबडी सेज कि मार्केटिंग का यदि हिंदी बात करें तो विपणन होता है, वो तो बहुत लोग नहीं जानते हैं, बट गांव का लेमैन व्यक्ति भी मार्केटिंग पर मार्केटिंग कहते ही समझ जाता है। तो वैसे ही आजकल लोगों की केमिस्ट्री, लोगों का ज्ञान आपस में चारों तरफ बात को बहुत विस्तार से सब जगहों पर बताया जाता है, चाहे वो टीवी पर शो हो, चाहे और किसी जगह पर्सनैलिटी की बात हो, तो ये केमिस्ट्री की बात वेल नोन है। मैं चूंकि क्या कहते हैं कई जगहों पर मैंने सुना कि हिंदुस्तान में, मैं भी उसका दवाई का नाम भूल रहा हूं, कि वो हिंदुस्तान में 3 पैसे में हमारे यहाँ के लोगों द्वारा बनाई जाती थी, और हमारे ही पास के मुल्क में उसे 36 पैसे में बेचा जाता था, और बाकी कंट्रीज में उसे 12 रुपए 22 रुपए के रूप में होता था। हम भारतवर्ष जो केमिस्ट्री के जो केमिस्ट हैं, वो बहुत अच्छी दवाइयां, उसका पेटेंट की बात मैं नहीं समझता कि पेटेंट उतने अधिक हम कर पाए हैं, परंतु उस मॉलिक्यूल डेवलपमेंट का लेबोरेटरी टेस्टिंग के बाद में जो भी काम किए गए, तो भारतवर्ष का पूरे विश्व में बहुत बड़ा स्थान है। केमिस्ट्री के लोग इसके लिए सार्थक परिणाम के लिए एक साधुवाद के पात्र हैं। मुझे ऐसा याद है जब मैं कोटा में था, तो वहां का जो केमिस्ट्री डिपार्टमेंट है, उनमें जो वहाँ की हेड ऑफ डिपार्टमेंट आशु रानी जी थी, और उनकी जो रिसर्च स्कॉलर्स हैं, उन्होंने भी वहां पर जो कोटा में थर्मल से ऐश निकलती है, उससे भी कोई एक टेबलेट को बनाया था, और उसका भी कोई शायद केमिकल चीजें आगे बढ़ी थी। तो कुल मिलाकर कहने की बात यह है कि मैं तो खैर केमिस्ट्री के बारे में ज्यादा जानता नहीं, परंतु केमिस्ट्री सर्वत्र है। आपने ठीक कहा कि क्या कहते हैं केमिस्ट्री डिपार्टमेंट का साइज आज कई यूनिवर्सिटी में टोटल पूरी यूनिवर्सिटी में जितने लोग होते हैं, उससे अधिक लोग तो केवल केमिस्ट्री डिपार्टमेंट यूनिवर्सिटी ऑफ राजस्थान में रहे हैं, न केवल केमिस्ट्री, फिजिक्स, बायोलॉजी सभी जगह रहे हैं। तो एक बहुत बड़ा योगदान एक विज्ञान के क्षेत्र में राजस्थान यूनिवर्सिटी के केमिस्ट्री विभाग का रहा है। मेरे से जितना बन पड़ेगा पूरे डिपार्टमेंट को हम सभी को साथ लेके चल रहे हैं, जरूर इसको आगे लाएंगे। वीके सिंह साहब को पूरा विश्वास दिलाना चाहते हैं कि हम उनकी अपेक्षाओं पर खरे उतरने की कोशिश करेंगे। और बाकी तो खैर ये कॉन्फ्रेंस बहुत लगन के साथ में, मैं बरसेरा जी को कल तक भी देख रहा था, बहुत लगे हुए हैं। ये नहीं, इनके साथ पूरी टीम लगी हुई है, और ये इस कॉन्फ्रेंस की सफलता की शुभकामनाएं मैं एडवांस में देना चाहता हूं। आने वाले 2 दिनों में बहुत सार्थक रिसर्च पेपर्स पढ़े जाएंगे, और कुल मिलाकर के इसकी सफलता की शुभकामनाएं करते हुए अपना स्थान ग्रहण करता हूं। जय हिंद, जय भारत।
Thank you so much, sir, for your valuable insights as well as for sparing time for us. Dear audiences and participants, now we are beginning with today's first session. This session will be chaired by Professor Nilima Gupta. It is my privilege to introduce her. Professor Nilima Gupta is working in Department of Chemistry, University of Rajasthan. She holds many reputed seats, like she is the honorary director of PG School of Physical Sciences. She is the additional director, Nanotechnology, Center for Converging Technologies, University of Rajasthan. She is the course coordinator for Computer Assisted Drug Designing, BIC, University of Rajasthan. Along with this, she has a rich professional experience of research, teaching, and training. She has been visiting faculty of Philipps University, Marburg, Germany. She has holding an Indian patent with title A green process for making a new polymorph from and of sucrose. She has been awarded with the ISCB Distinguished Women Scientist Award 2019 by Indian Society of Chemists and Biologists. Her achievements includes many more. I now request Professor Nilima Gupta to take over this session forward.
माइक ले जाओ माइक यही है ना या और कोई ये
So thank you, Preeti. Indeed, it's an honor for me to formally introduce Professor Vinod K. Singh. We know that Professor Vinod Singh visits our department frequently, and almost in the previous 5 other conferences of the FKC series, he was our distinguished guest. And to most of us, his personality and his achievements are well known. But for the information of present here, our Honorable Vice Chancellor, Professor Rajiv Jain, other distinguished guests, and our young students and the research scholars who are attending this conference for the first time, I take this opportunity to formally introduce Professor Vinod K. Singh. Although he is a well-known chemist in the fraternity in our country. So few words to introduce him, I will say. Professor Vinod K. Singh presently holds the Rahul and Namita Gautam Chair Professor in Department of Chemistry, IIT Kanpur. He is at the same time holding Director's Chair Professor at IISER Bhopal also. And the IISER Bhopal, he had been the founder director. And during the 2 terms of more than 10 years, as a founder director of IISER Bhopal, Professor Singh built the institution from scratch. Those who have got the opportunity to visit IISER Bhopal can see with how much planning this beautiful campus has come up. He has served as mentor director of IISER Behrampur also, director of SPA Bhopal also, and chairman of the board of governors NITTR Bhopal also. He had additional charges of many prestigious institutions in our country. MA NIT Bhopal, mentor director of IIIT Bhopal, and many more. He is the immediate past president of the Chemical Research Society of India. He is chairperson of the Governing Council of IACS Kolkata. And he has been, as already told, been honored by our president with Padam Shri. Professor Singh works in the area of synthetic organic chemistry, especially asymmetric synthesis, and his research work has been recognized with several awards and honors. To name few of them: Sir Jayanti Fellowship, Shanti Sura Bhatnagar Prize, Padma Shri, and many other prestigious ones. He has been elected as fellow of the all academies, science academies of India long back. He has been elected as a fellow of the World Academy of Science, Tavas, also editor of many prestigious journals, tetrahedron letters, one remarkable this, and then he is on the advisory board, editorial advisory board of Organic Letters, Journal of Organic Chemistry, Asian Journal of Organic Chemistry Frontiers, all the most prestigious journals in organic chemistry. So, not taking much time, we are eagerly waiting to listen him. His title of his talk is An Enantioselective Approach Towards Isoindolenones and Related Heterocycles. So, I welcome Professor Vinod Singh for this talk.
Well, thank you, Nilima, for the introduction. I thank the organizing committee, including the convener Satpal, for the invitation. As my title depicts, I'm going to talk about enantioselective approach towards some heterocycles, mainly isoindolenone and the related ones. What I'm going to do is, in few slides, I'll just talk about the principles, the strategy behind it, and rest of the slides will be just extension of the work. Details will be missed. For details, you have to go and read the paper. If you look at these heterocycles, isoindolenones, isoindolenes, and tetrahydroisoquinolines, they are quite prevalent in natural products found and have associated with a large number of biological activities, which are mentioned here: antihypertensive, antipsychotic, anti-inflammatory, anti-tumor, anesthetic, etc. I like to mention here when we are working on it, for example, strategy for this kind of system, was known, not difficult. But the strategy for this kind of system was little difficult. So once you do one strategy, you extend your chemistry to other systems as well. So, I'm showing one background slide because the genesis of the whole strategy was done in 2006. We had published a paper for in situ selective propargylation reactions. Idea was you take aldehyde, amine, and propargyl system, in situ informs imine, and the propargyl thing adds to give you corresponding product in high in situ selectivity, and in situ selectivity in all the cases was more than 99%. So we were interested here at paramethoxybenzyl group so that it can be cleaved and the method becomes useful. And what we had used is this kind of pi box diff ligand, and this ligand is well known pi box. Our addition is by adding gem diphenyl group, and that changed the selectivity a lot, not only for this reaction, for a large number of reactions, we have published it. If you don't use gem diphenyl group, in situ selectivity is poor in large number of cases. And the working model, what we had published is, we don't have any proof because you have imine which chelates with the copper and chelation in a manner so that the whole transition state becomes very rigid. And these distances, I don't want to mention it, that they are quite attractive in nature. And if the transition is rigid, you get high in situ selectivity. And these substituents at the chiral center, for example, you see here isopropyl, here is isopropyl, they dictate the facial selectivity in the reactions. Okay. For example, because of these chiral substituents, one phase will be blocked, another phase will be accessible, and you get high. We have used various ligands with a different kind of substituents, depending upon the size of the substituents, isopropyl, tertiary-butyl, phenyl. But tertiary-butyl you see is expensive, so we avoid it. And isopropyl phenyl gives very high selectivity, and isopropyl based amino acid is cheap, so one can synthesize this ligand. In initial selective reaction, I like to draw attention to the student. It's very important. The chiral ligand or catalyst, you should be able to procure easily or buy it. You should be able to make in 2-3 steps. Otherwise, nobody is going to use it. Okay. So this we published 2006. Then in 2014, what we did, we carried the same reaction in intramolecular, and the strategy was that if you have ester here and you do the reaction mentioned in the previous slide, in situ, what you'll have is when the propargyl attacks the imine, the nitrogen can zip in with ester to give you cyclic compound. That could be 5-membered, 6-membered, whatever you want. And if it works, one can get this kind of heterocycles. We've already published, details are there. So we are able to get very high using isoindolinone system, and we use some small synthesis also applied it. And as you can see that in one pot we have elimination, alkylation means adding a propargyl system, and cyclization, which is lactamization. Okay. And so in sequence you form 1 carbon-carbon bond and 2 carbon-nitrogen bond. One imine is adding to carbon and nitrogen is adding to the carbonyl of the ester. Okay. So this is already published, so I don't want to talk about it, except like some small application I'm showing for student's sake, because any methodology you develop, if you cannot apply, show some application, uh, as Dr. Chauhan said, that your reaction will not be worthwhile. So as you can see that we are able to synthesize some biologically important compound in very simple routine transformations. And the transformation here is nothing but your alkyne, you do hydration to get carbonyl compound here, and oxidative cleavage of paramethoxybenzene group using sodium ammonium nitrate, which is 1 electron oxidant, gives you this amide, and then Baer vinegar gives you this ester, reduction gives you benzyl alcohol. You activate the primary alcohol, make it a good leading group as a mesylate, and displace by corresponding amine to get these systems. So that way we could use the methodology to synthesize the important ligand which have psychotic activity. Now, here as you can, just showing it. Now earlier we didn't have CS2, we added CS2 because then you can make 6-member ring. And as I said, tetrahydroisoquinoline, this is not a challenging. We have several good methods which can be made it, but intramolecular thing did not work. So we had to add in extra step. As you can see that after preparing it, what you do is we reduce the ester with lithium aluminum hydride, activated as a mesylate. Now it becomes a good group, and then the intramolecular lactonization takes place to give this compound, and initial selectivity is very high. There was no problem. Okay. Now, what we had done, we extended the approach. So far I described you the strategy behind the whole thing, what I'm going to talk. Now, here what we did, what we thought we can have another approach. You carry out everything here, and your acceptor, instead of carbonyl group, ester and all that, you can have as a Michael acceptor. And let us see whether it works. And it didn't work here. So again, we had to कान पकड़ने के दो रास्ते होते हैं. So we had to add extra way. And you can see that what we get is this amine. And then one has to use base. And use base, then it can work. And the next slide, I'm just describing the result. As you can see here, we use these substrates. We use copper complex of the ligand, and then in situ you get amine. You treat with lithium hexamethyl disulfide, and you get this compound in very high initial selectivity. But diastro selectivity was modest, not very good, 9:1. But we are able to synthesize this compound. We also shown small applications which are mentioned in this paper, and basically in one pot we have initial selective elimination, alkylation, and as a Michael reaction. Now then we thought, what about creating a system by having this kind of 3-hydroxy isoindolinone? Now if you have this system, and if you treat with acid, you will have a dehydration, you will have uranium ion, and then you can add nucleophile. And depending upon your chiral ligand, one can get one enantiomer. Addition can take place from one phase, and one can generate a quaternary center. So in situ we generate ketamine. And acid is, as you know, the bronze stage acid. Phosphoric acid is well established, so one can use chiral phosphoric acid. Okay, we tried all kinds of things, but in this one, I'm going to describe some of the nucleophiles. I'm only describing the positive result. I like to tell students, what we show here is only 10%. 90% is something which is not shown here, which have not worked. So we use various nucleophiles, thiols, dicarbonyl, phosphides, digoesters, And so strategy is this one, okay? And let us see what we have got and what we knew when we started the work from the literature. What we knew that this imine can be used an electrophile where enol silyl ether in the presence of Bronsted acid. This is Akiyama is the first one who used chiral phosphoric acid for enantioselective reaction in 2004. And I'm not sure this is maybe the first paper where enol silyl ether adds in enantioselective manner to give you this kind of compound in very high enantioselectivity and diastereoselectivity. So this was already known, this kind of reaction addition, but our approach is little bit different. So let us see what happens. What we thought, if you have this compound, aryl compound, we tried in the beginning some other things but did not work, but aryl is easy to generate a carbocation, you can, reaction will be more facile, and also the enantioselectivity thing. So phosphoric acid, what you will have is the thiol will be made more nucleophilic by the hydrogen bond of the lone pair body, the phosphoric group. Here what you have is this OH of the phosphoric acid will chelated with this iminium ion. If the whole thing sets, you will have a dual activation approach, and the nucleophile attack the iminium ion from one phase. If everything is planned well, one is lucky, one should be able to get compound in enantioselective. And you can see that this result is described. We are able to get this compound in 99%. The reaction worked well and there was no difficulty. I'm only showing the chiral is Bronsted acid, which gave high enantioselectivity, but several were used, which are discussed in this paper. Now, we use this one in synthesis of biologically some important compound. For example, this one you can synthesize this HIV reverse transcript inhibitor, and this, if you add extra carbonyl group, one can synthesize 6-membered also. So that shows the small application of this method. And recently, last year, we showed that instead of phenyl, if you have this kind of group also, this adds here and you get very high enantioselectivity. And for that, we have used this Bronsted acid. Okay. So this is again a similar chemistry, except phenyl, we have here alkyne group. Last year, we also showed what 1,3-dicarbonyl can also be used. And we are able to synthesize this one and this kind of compound in a reasonably high enantioselectivity. And then other kind of thing, if you look at, you use nucleophile like phosphite can be used as a nucleophile. Normally this phosphite and this phosphonate, they are tautomers. Okay. And equilibrium is more towards phosphite. But since it's equilibrium, even a small amount can act as a nucleophile. And use this chiral phosphoric acid, and the activation takes place the way it is mentioned here, the same philosophy, and one can synthesize these phosphonates. And these phosphonates are also very important. They are associated with biological activity. And as you can see that this slide shows the result where we have been able to synthesize these phosphonates, so hydrophosphonylation reactions, and there's a good substrate generality and in very high enantioselectivity. If you look at here, what we have shown here, that if you, just to have some control experiment, if you have N-methyl group, there is no reaction. And if we use a trimethyl phosphide, there also reaction is almost nil. So that shows that in order to have the reaction going, we have to have NH group and nucleophile of this kind, otherwise the reaction doesn't proceed. So free NH essential, OH group iodalkyl alpha size is also required. And we just try to cleave it because the selectively cleaving one phenyl ether here, as you can see, we have shown using lithium hydroxide. And if you use hydrogen in the presence of platinum oxide, the Adam catalyst, you can see that both can be cleaved here. The next we wanted to add different nucleophile, one that worked was alpha diazoesters. For example, if you had a diazoester, the philosophy is same, and you can have this kind of dual activation approach, and this nucleophile can attack this imine from one phase. One can synthesize this compound, which can be used in synthesis later on. As you can see here, the result is described. You can see that we got more than 99% in large number of cases. And this phosphoric acid gave the highest selectivity, and large number of examples have been carried out in this paper. We also try to cleave this one, but as you can see that, sorry, we make benzyl derivative and took X-ray for the absolute chemistry of the compound. And some of the transformations, for example, one can convert into this using this. We have a better method, but here the yield was poor. And somehow if you treat with lithium hydroxide into this one, we get some interesting heterocycle, but you lose chirality. Then we thought, what happens if you use ester here, and if you can synthesize this compound, if you use the amine, so same thing happens. In situ you form imine, this attacks here, then cyclization occurs, as is shown here. For example, you can have X as a nitrogen or oxygen, and if the diazo compound attacks this selenium ion, then intramolecular cyclization gives you this one. As you can see here, there is a concern, the Eza-Darzin's reaction. The concern was, this is already known in literature, that if you take aldehyde, amine, and this diazo compound, you get this aziridine. And the way it happens, this ion pair is involved. This diazo compound attacks here, and then the intramolecular attack of the nitrogen gives you nitrogen, which becomes a good leaving group, and you get aziridine. So the concern is, in our reaction, whether we get aziridine or isoindolinone. If you use this one can get this compound and this compound. If you go by literature, one will not carry out reaction thinking that will not get this compound. So if aziridine is formed by a Darwin reaction, or if this form, the very thing will have isoindolinone by a manic lactonization reaction. Okay. The result is summarized in this slide. As you can see that what we wanted did happen. We were able to synthesize this compound. The reaction did work. Very high E, large number of examples carried out. So we have this reaction successfully in synthesizing isoindolinone. Now, as you can see that this is again mechanistic model, what I showed you earlier, that this phosphoric acid, this gets activated, and then this was attacks. And if the ester in the proximity, this actually zips in, gives you isoindolinone. Now, for every method, it's good to do little large scale. It's not possible in all the time, but as you can see, the gram scale, I like methodologies to be done to make it useful and reproducible. So we carried out this reaction. As you can see in 10 millimole scale, the initial selectivity is 96%. And then one can apply in synthesis also. We tried to reduce it using Adam catalyst, but you can see that we get mixture of these two compounds. Here we get 68%. This is only poor yield. But by treating with sodium borohydride, one can synthesize this compound. Okay. But there are other methods shown here where one can remove this one in the good yield 70%. As you can see that. So once this is there, then this becomes very useful in synthesis. And again, the oxidative cleavage of paramethoxy phenyl group using ferric ammonium nitrate gave this compound, and the reduction of ester to alcohol using lithium borohydride gave primary alcohol, and then you can activate the primary alcohol as a good leaving group and displace by nucleophile to get compound. Here we have synthesized dopapine this ligand in 95% yield. We also have a small application shown here. This has been converted into corresponding acid, which has been converted into some important compounds. As you can see that this is anxiolytic drug. This is already known. So basically we have synthesized these two intermediates to show you. Okay. And absolute histochemistry was established by comparing the specific rotation with the known compound. What we thought that, what happens if you don't use amine and if you have aldehyde here and diazoesters would attack and give, again, gives you phthalide. And that time there was no method to synthesize phthalide by this one. Again, this is a kind of cartoon where it shows that if everything works, we should get this compound. And these phthalides are also were medicinally important compounds as shown. There are several natural products or other compounds which have biological activity. As you can see, the results are summarized here. This attacks to gives you this 85% E. E was not very high. 85% E is not acceptable E. But we were not able to improve it. It was the first report of this kind. So we are happy, but still we are trying to improve the E. Hope someday we'll get 99%. So some of this is synthetic transformations, and this is absolute histochemistry. We are also trying to add in extra CS2, but somehow by adding extra CS2, as you can see that E is 50%. We are still struggling for more than a year, but still no hope, because initial selectivity has to be more than 90%. Okay. Then what we thought we can, when use this kind of compound we use for the addition of thiol compound. So we can have this selective formal 3+2 cycloaddition. One can synthesize this compound we published last year, and the mechanism is shown here. In the presence of acid, what happens? The dehydration takes place, you get iminium ion, and then the phosphoric acid activates this one. As you can see that the attack at C2 carbon takes place to give you alien kind of compound. You can take C2 alienation reactions, and then what happens? The loss of H plus gives you this compound, and again in the presence of acid, the protonation takes place here, and as you can see here, you generate a the positive charge and the nitrogen. As you can see, making this more electrophilic. And this attacks here to give you this compound. So this is a kind of proposed mechanism to synthesize this one. And then we have, we wanted to synthesize some of these spirocyclopropyl oxoindolenones because they're this kind of systems which are associated with important biological activity. What we thought that we can synthesize this kind of compound from this oxoindole compound. And as you can see the slide shown here, last year we reported this result using vinologous Michael initiated inclusion reaction. So This ISO used earlier for analogous initial selective reactions, and using this catalyst, urea-based catalyst, we are able to synthesize this compound very high initial selectivity and high diastro selectivity. And the reaction, the way it proceeds here, as you can see that this isoxazole, basically what happens, the deprotonation takes place to give you this kind of species. Okay, and this is your acceptor, the electrophile, and this gets activated by this urea. And this one, what happens, comes here, attacks here, and that gives you this kind of species. Again, this comes back, attacks here, gives you this is the proposed mechanistic model for this kind of reactions. Okay, since we knew it, we had done several years ago this analogous reactions. So isoxazole can be cleaved. Unless you are able to cleave the reaction, is not going to be useful. As you can see that we have been able to cleave it in corresponding ester, and so this compound can be very, very useful. And we have also carried out here some simple transformations where NBOC has been cleaved. This is the last example I'm showing. I have read with 1 minute. As you can see here, we have used this kind of compound to synthesize pyroxyindole using squaramide this ligand as and we got very good initial selectivity. And as you can see that the reaction shown like here, that what happens that this comes and this attacks here, this acts as electrophile, then generating this and this attacks here, and this gives you this kind of species. This is again proposed model. I don't have any proof. With this, I like to conclude here that we have been able to develop initial selective method for synthesis of isoindolinones and other related heterocycles such as indoline, phthalate, tetrahydroisomerase, etc. And I acknowledge the contribution of my students, and I thank you for your attention.
Thank you, Professor Singh. So we can have 1 or 2 quick questions from the audience if there are any. Yeah.
Thank you very much, sir. My name is Harish Kumar from the CST on Science Technology Reporting. सबसे पहले तो मैं आपको बहुत बहुत धन्यवाद दूंगा कि आपने एक्सपेरिमेंटल साइंस की बात की, उसके लिए बहुत बहुत धन्यवाद.
Thank you.
We are facing the problem of climate change in whole India और इफेक्ट बाय ह्यूमन बीइंग एंड एग्रीकल्चर सेक्टर. तो क्वेश्चन है कि जो अप्लाइड साइंस है, एडेप्टिव साइंस है, उसको कैसे एनहेंसमेंट किया जाए, कैसे उसको एक नया पैराडाइम शिफ्ट किया जाए जिससे ये कार्बन न्यूट्रल सोसाइटी बने, ग्रीन बिल्डिंग बने, ग्रीन सोसाइटी बने, हैप्पीनेस हो, जीरो इफेक्ट हो, एवरीथिंग हो. व्हाट्स द पैराडाइम्स इन अप्लाइड साइंस और एडेप्टिव साइंस?
आपका बहुत डिफिकल्ट क्वेश्चन है. Doing science is a too complex thing. One, you require infrastructure. More than infrastructure, one requires common sense also, which is very difficult to find. And there will be hard work, passion, and all those required. Unless somebody is good in basic science, you cannot do applied science. Because it's easy to do in social media, Twitter, but very difficult to do in round bottom flask. So one has to be very, very good in this. If a faculty joins as a faculty, you cannot tell him to make a drug right away. And drug cannot be made in academic institutions. It's a very too complex thing. Although people write project, get money, that's a different thing. So it's a too complex thing. I think we can discuss over tea. Because if I say something, something may not be liked by people. So I like to, and I don't lie, so I think I'll be
Great.
quiet.
Thank you very much, because there is a need of adaptive activity. We are the climate change से कितना effect हो रहा है हमारी society के ऊपर.
Climate change, I request our vice chancellor की इस hall की प्लास्टिक सब निकलवा दें सबसे पहले. ठीक है. मैं लोगों के घरों में जानता हूँ 10 साल तक प्लास्टिक कुर्सी के नीचे लटकी रहती है. Something which requires common sense. कार में लोग खरीद लेते हैं, प्लास्टिक रहती है, मिरर के ऊपर वाले में 10 साल तक रहती है प्लास्टिक. See, these are the simple things which doesn't require money. I'm sure my close friend and outstanding synthetic organic chemist Prasad is here, who will tell that you require only common sense. That's it. Thank you.
So if there are no more questions, I thank Professor Singh for his wonderful talk. I see some of our even MSc students sitting here in the hall, and I'm sure Professor Singh, the way you have presented this asymmetric synthesis work must have made them understand the organic synthesis paper they are just studying in their semester right now. So thank you once again, Professor Singh.
I request Professor Nilima Gupta, chairperson of this session, to offer a memento as a token of reverence to Vicky Gupta.
So again, it is my pleasure to introduce formally Professor K.R. Prasad, the second speaker of this session. Professor Prasad completed his initial undergraduate and postgraduate studies from Andhra Pradesh and then obtained his PhD from Pune, working on again asymmetric catalysis from the National Chemical Laboratories. Then he moved to Germany on the postdoctoral fellowship, the prestigious Alexander von Humboldt Foundation. And he worked at the University of Münster with Professor Dieter Hoppe, and another postdoctoral stay with Professor Franklin A. Davis at Temple University, Philadelphia, USA. Then he started his career as a scientist in medicinal chemistry at Precious Pharmaceuticals, presently known as GlaxoSmithKline, in again USA. And then he moved to India, back to his own country, and joined the Department of Organic Chemistry, Indian Institute of Science, Bangalore. Presently, he is working as a professor there, and his research interests are concerned with the development of synthetic strategies for the total synthesis of natural products with therapeutic applications and their evaluation as potent therapeutics also. Professor Prasad is recipient of numerous awards and honors. To name few are the Swan Jayanti Fellowship of Department of Science and Technology, and then National Academy of Sciences Scopus Young Scientist Award, then Professor N.S. Narasimhan Endowment Lecture Award, Professor Rajiv Goel Prize, and Shanti Swarup Bhatnagar Prize in Chemical Sciences, one of the prestigious awards in our country. Professor Prasad is an elected fellow of the Indian Academy of Sciences, Bangalore, and the National Academy of Sciences, India. He is Associate Editor of Organic Letters, a premier journal in the organic chemistry published by ACS. Today, he is going to talk on the scope and limitations of the enine metathesis approach for the total synthesis of strychnine. So, I welcome Professor Prasad for this talk.
Thank you very much, Professor Nilima Gupta, for an elaborate introduction. Thank you so much. This mic looks like as if you are an astronaut. Anyway, thank you so much. And it's indeed a pleasure to be here at Jaipur. Thanks to Satpal for the invitation, and happy to present work on the total synthesis of strychnine. I must mention that this is directed to the audience who are at the back, the students. If I can convey some message so that you can take up the total synthesis as a, as a research project, that would be, I would be succeeding in my presentation. So Professor Singh has already started with the importance of heterocycles, especially the nitrogen containing compounds. And just to emphasize a little bit on natural products, I would like to say that most of the drugs, what you find in market, has the origin to natural products, whether it is a synthetic drug or a modified drug. Most of them have their core, from the natural products. So 50% of the marketed drugs have their origin to natural products, because most of you know that natural products controls most of the cellular processes, whether it is arresting a cell cycle or promoting a cellular reaction. So they are very important. At the same time, these are the ones which you can use to generate large number of scaffolds. Like Professor Singh has shown some of the synthetic molecules or some of the natural products, what they find in indoline, isoquinoline, indolizidine, and all that. Before I get on to the synthesis of strychnine, I would like to just briefly mention how we entered into the synthesis of strychnine. So some of you, the students, must have read about the synthesis of strychnine by Woodward. So we accidentally got into the synthesis of strychnine with this molecule, which was synthesized by my friend Dr. Ramana in NCL long back. This is called Scholzine B, having a moderate activity against glycosidase inhibition, basically useful for the treatment of diabetes. So this was a compound which was of interest in those days. And if you see the components in that particular molecule, you realize that you have a isoquinoline with an amine here and a polyhydroxylipid type structure. Now, this particular isoquinoline can be synthesized by a Pictet-Spengler reaction of a glutamic acid with a phenethylamine. Of course, since glutamic acid has a chiral center, you can have a diastereomer here. Otherwise, if you have to create a chiral center,
revise our retrosynthesis. And then we started with something which is known in literature that this is something to do with Professor Basavaya's reaction. This is called an intramolecular Asa-Baylis-Hellman reaction, where you knock out this bromide and the iminium ion, what is there, is undergone a reaction like a Baylis-Hellman type reaction to make this particular product. But then, to make the story short, when we did this reaction, it did not work in this case. It is very clear that you require a free NH, not the N-allyl, to do the particular cyclization. So we thought, let us make the free NH and then proceed for the Baylis-Hellman reaction, type reaction. So the revised retrosynthesis is that you require a free NH to do this, cyclization here. Instead of Baylis-Hellman reaction, can we introduce the alkyne right in the beginning? That means the same substrate what you have here, it should be modified to this particular intermediate. So we started with the sulfite added allyl zinc bromide, deprotected the sulfonamine. Now bromo is still bromide alkylation works pretty good. And the alkylation with the allyl iodide is very nice. And then we did the deprotonation here, which concomitant displacement of the bromide to make the spirocyclic compound. And the imine was reduced with sodium cyanoborohydride to give a non-separable mixture of diastereomers. I must tell you that I'm not aware of the stereochemistry at this particular center. So we did the protection as the TBS ether, and now we could able to separate both the diastereomers. So once the diastereomers were made, we did from the minor isomer and from the major isomer, we separated, and then we did the ring closing metathesis. And from the minor isomer, we could get the cyclized pentacycline 54% yield. And this was very nice. So we thought, why not we do it from the major isomer? I would like to mention to you again that I don't know the stereochemistry at this center at that stage. So we did from the, this is basically the structure, what I have shown here. This is what is strychnine. What you require is a CC bond from here to here. That's it. But you would be surprised to learn when we did the major isomer, what we found is some other product. There's nothing to do with the strychnine pentacycle. So we know very well that there's something wrong with the stereochemistry here as well as the stereochemistry there. But then you must appreciate that we are getting 6612 major minor isomers. And from the minor isomer, we are getting the product what we want. Then what we thought that a very simple way of making strychnine is becoming more deep and complex and not something which is so accomplishable, right? So we realized that there is something wrong with this major isomer, and we should see how we can improve the minor isomer with required stereochemistry here. So what we did is, at the same time, Viresh is an expert in this one. So I wrote to Viresh how we can, improve the synthesis as well as why this one is not undergoing the HEC type reaction. He said that, perhaps this amide is the one which is causing a problem. So you reduce this amide to an amine. So the question is, you need to reduce the amide to an amine. And this might look very simple because most of you who are in MSc, if I ask you how you reduce an amide to an amine, you can give me some half a dozen examples of functional group conformations. But you would also appreciate the fact that you have two double bonds. You have a vinyl iodide, another double bond. So there are three reactive functional groups. One has to be very careful in choosing the amide to amine reduction without affecting the other functional groups. So at last we found that this is because, if you make this compound from here, it is known synthesis of strychnine. So at least you can have a formal synthesis. After long trial, we realized that we can reduce this amide before the ring closing metathesis with Mirwin salt and sodium borohydride with very good selectivity or regioselectivity of only touching this amide, not the other functional groups. That was very nice. Then we thought that half of our problem is solved. And then when we did the ring closing metathesis reaction, for reasons which I don't know, this reaction did not work. It did not give us the this pentacyclic product. So we realized that there is some problem with this ring closing metathesis reaction. So we thought that instead of having this allyl group right in the beginning, we should start with para-methoxybenzyl group. And if we have the para-methoxybenzyl group, we should be able to make the same kind of spirocycle and then proceed further. So we started the reaction with deprotection of the sulfonyl group, reductive amination to do the para-methoxybenzyl, attached to bromoacetyl bromide, and then reacted with sodium hydride, which cyclizes to give the spiroindoline, and then you have the imine reduced to the sodium cyanoborohydride. Now the diastereoselectivity selectivity is 99 to 1. Now, if you remember, previously it was 66 and 12 is the minor isomer, which is our required one. It is 99.1, but I was more worried whether it is the unwanted isomer or it is the wanted isomer. And then we did as I said, this was the previous 16. Now this is 99.1. And then when we subjected this to the acrylation, that we got very nicely, and then reduced this amide to amine. That's also very nice. And everything is going good, and this stereochemistry was confirmed with crystal structure. It is the wanted isomer which we require. All that is fine. So we thought that the problem is solved. It's only a ring closing metathesis and a Heck reaction. Mind you, two reactions which we need to do. And when we deprotected the tips and then reacted with the Grubbs catalyst, and this is something, as I said, that's what we require. If it is done, then it should be done. And the product did form in 38% yield. So this is the strychnine structure. This is what we have. You have to remove PMB and put this allyl group. And from here to here, this is known in literature. There's nothing you got to do. Only remove PMB and put an allyl iodide. I must tell you that removal of PMB was so difficult, we could never do it. So the PMB group, in which you learn in your MSc that you put DDQ, you put something else, you some other ones, all those reagents did not provide this particular product with free NH. So we need to look for an alternate, like how we can make this intermediate for strychnine synthesis. So the student suggested that instead of PMB group, can we use orthonitrobenzyl group, because nowadays there's a lot of chemistry using photochemistry. So perhaps we can deprotect orthonitrobenzyl group with photolysis. So we made the same thing by doing the orthonitropenzaldehyde reductive amination, bromoacetyl bromide, and then we did the cyclization. And again, here it is 99 to 1 stereochemistry. And then we did the photoirradiation. We realized that this is getting oxidized. So it's not the one which we wanted. But then if you protect it as the acrylyl, then obviously this worked pretty good, and then you can make the corresponding free NH group and make this particular one. Now, we have reduced this to the corresponding amine, but we know that the ring closing metathesis was not great. We are at this stage, and we could reduce this alkyne to an alkene. And this is, of course, the ring closing metathesis was pretty good. And this is part of another natural product called tubifilidine, which we are progressing now. So basically what I want to emphasize is that what we thought is a simple reaction and then we can make strychnine has become more complicated as we go more into the synthesis. Simple protection of the functional groups and deprotection has become little difficult. But now we are at this stage where we are trying to make strychnine from this intermediate, and we are in the process of doing it. Okay, that is what I want to. We made some other natural products and some other methods. I know that I'm in between, and for yourself, so I concluded here. And then most of the work was done by Sopan, who is now in Singapore doing his postdoc. And we have a very small group of not more than 8 students in IAC, not because we cannot have harmful accommodation, so we need to respect our group by 8 or so. And most of the work that was done with the sulfonamide was a generous gift from Suven Pharmaceuticals in Hyderabad, and funding for work has come from DST SCRB, and this is the person
who started the sulfanilamine work in my lab, Dr. Robul Reddy, who was a PhD with Professor Priyasamy and was a UGC Qatari postdoc fellow in my group in those days. He was the one responsible for us to start this sulfanilamine chemistry. And for those who are, who have never visited Bangalore, this is our campus, one of the most beautiful campuses, and this is the season where you get this gulmohar. I'm sure in Jaipur also you see most of the gulmohars in the campus blossoming like anything, and one of the beautiful sights. So thank you very much for your attention, and I would be happy to answer any questions you have. Thank you.
Yeah, thank you, Professor Prasad. Any questions? Any? So, if there is.
Regarding your this enine and ring closing metathesis, did you also try to add petroleum sulfonic acid or any acid to essentially quench the nitrogen nucleophile and lone pair and then do it?
Did.
Okay, so did not work.
From paradone sulfonic acid until trifluoromethane sulfonic acid.
Okay. Did not work. Okay. Thanks.
So, anyone else? Yeah, piche wahan. Back.
Hi, sir. Ritesh here. Wonderful lecture. I mean, so that NO bond cleavage, I mean, you tried with that photo version actually. So what about the chemical way, like simply using other like MOCO6 and something like that? Uh-huh. Okay. Yeah, yeah, okay. Thank you, sir.
So, any more questions? So, join me in thanking Professor Prasad for a wonderful talk.
Thank you, ma'am. I now request Professor Nilima Gupta, chairperson of this session, to kindly hand over the memento as a token of reverence to the eminent speaker.
So, we had wonderful inaugural lectures, one keynote lecture by Professor Vinod K. Singh and the second one from Professor K.R. Prasad. So beautiful asymmetric synthesis chemistry, stereochemistry, disconnection approach. So this is an example to the PG students and the young PhD researchers when they have to apply the chemistry what they have studied from the books to the laboratory for their experiments and planning something for their research. So such lectures present, I think, the wonderful, pathway for the understanding. So once again, I thank the speakers and take the opportunity to extend my thanks to Dr. Vatsala for giving me this opportunity to chair this session. Thank you.
Thank you very much, ma'am. I now request our Honorable Vice Chancellor, Professor Rajiv Jain, to come over the stage and kindly felicitate Professor Nilima Gupta for her all the efforts. May we have a big round of applause for her? Thank you, sir. Thank you, ma'am. I now request you, all the speakers of the second session, to hand over their PPTs to Dr. Pragati Fageria for the backstage for the second session. Once again, I am announcing that please hand over your PPTs to Dr. Pragati Fageria on the backstage for the second sessions. Thank you everyone for your kind cooperation, for being a lovely audience. Now it is my duty as well as my pleasure to invite you all for the high tea. Before we go for the break, I must request that please join us back by 11:40 a.m. It's a 20-minute break. May we all have. Please. Thank you very much.
this drug or that drug, and that is just but we forget that our molecules for the benefit of humankind. And but how to find molecules? We make molecules just random. But how to find molecules? We go back to the nature, that nature provides a lead molecule and natural products which are biologically active. And from this slide, I will give you a glimpse of the natural products. You know, till 2019, aesthetics, almost 58% of FDA approved drugs are either natural products directly or natural product derived molecules, which are a drug. And more it is becoming clear that a future drug will not be a plain molecule, not flat molecule. It has to be a three-dimensional molecules. And three-dimensional molecules need has to come from the nature. And that is why there is a strong justification to do natural product synthesis. And natural product synthesis is important from many points of view because it is a driving force for the development in the field of synthetic organic chemistry as well as drug discovery for the welfare of human beings. Complex structures of natural product provides an opportunity to innovate new chemistry for the development and sustenance of this vibrant branch of science. Well, we do develop a new methodology, but without showing that it has application in making a compound which will be of any use. To motivate, the most important thing is that this branch of or this total synthesis of natural products motivates the young mind to understand the nuance of organic chemistry research. Because this is an area of organic chemistry research which teaches the young people to many aspects of chemistry, synthetic organic chemistry, how to make bonds, how bonds in a stereoselective manner, and how to put together methodology to make a natural product. Also, the synthetic developments have enabled the design modification of natural product templates in a way that cannot be readily achieved by biosynthetic means. It potentially allows large scale and commercial scale synthesis. It happens that many times natural product as such, they are not very biological, they are biologically active, but they cannot be drug. But slight modification of them can lead to a drug candidate. With this kind of background in mind, we initiated area total synthesis of natural products, especially alkaloids, and we selected some of this kind of molecules. I am not going to, don't be scared that I am going to burden you with the total synthesis of these molecules. These are published and many more of such structures. So I am not going to go describe this. But I would like to describe how this how a new strategy was developed to make these molecules. So let's see these kind of molecules, which are alkaloids. As you know, the plenty of natural products alkaloids, and they are biologically active, and they are having a complex structures, many ring systems, many quaternary stereo centers, and so on and so forth. Now, if you are challenged with such kind of molecules and to develop a synthesis for most of them in a single methodology, then it is an enormous task. But we decided to develop a strategy where most of these molecules and some more which I have not put it here, they can be assembled. Now, we selected or we hypothesized that such kind of a template, if we make, then this will allow to make many kind of ring systems which can be used to assemble these natural products. Now, for example, if we have, why we selected? Because this is a string ring bicyclic compounds where selectively bonds can be broken. Now, if you break this bond, you can make this kind of compounds. If you break this bond, you make this kind of compounds. You have a quaternary stereo centers. Now, if you break this bond, you have a bicyclic ring systems having a quaternary centers and this here. Depending on the groups here, you can make. And also, you make this kind of compound. So with this background, we took this template and we have been working in this area for the last maybe 10 to 15 years, that we are selecting based on the structure of the alkaloids, which bond has to be broken from here to make that molecule. This was a hypothesis and we proceeded with that. So, but how to make this compound optically active in a large scale? Because when you are doing total synthesis with several natural products, you need to have starting material which is readily available and plenty available. You cannot do total synthesis with every time a small molecule preparation. So we decided to make this compound with a desymmetrization process, making this meso compound, desymmetrize this and make this compound. Now, this total things here in my group, in 1 week time, the students used to make, I won't say that all the students, but most of the students who had become quite experienced, they can make a kilogram of this compound in a week. Now, this is 100% optically pure compound, and this was made through a desymmetrization process starting from here. And most advantageous of this, that you can make both enantiomers, because this is both enantiomers of this diol is commercially available. So you can make any of the enantiomer of the natural product. I won't describe this, but a few examples to put my part in perspectives, that this was used to make advanced intermediate for all Amalgasi class of alkaloids. As you all know, Amalgasi class of alkaloids are biologically active and many complex structures are there. And we decided to use this to make advanced intermediates from which many of these things have been synthesized. Now, let's see how you can synthesize all compounds. I will just show you that very complex structure, gracilamine, which I will show you the detailed synthesis later. It can be synthesized through intramolecular 3+2 cycloaddition. This is also methodology developed in our group. and which can come from this structure, and this structure can be used not only for gracilamine, but you can make mesembrine, cadherin, crinine, and so many other structures which I have shown you here. How do we make this advanced intermediate or a common intermediate? This, let's see, electrosynthetically, you make like this. From here, you have desulfonylation, this compound, one carbon truncation and reductive cyclization, which comes from the coupling reaction here and from enol triplet here. Let's look at the synthesis. Enol triplet, coupling reaction, Grignard reaction, conjugate addition to get this compound, very high yielding, as you see here. Now you can ask that why not vinyl Grignard? We have tried it many reactions, but vinyl Grignard doesn't work. So we have to try allyl Grignard, and that is why one carbon degradation has to be done to have this, and then reductive amination to have this. You can have AR, either this or this, and depending on the AR, you can make these kind of compounds and this kind. Let me show you just gracilamine synthesis. Gracilamine synthesis was isolated in Turkey, and around 2013, the structure was determined. And that time, the molecule was obtained in such a small quantity that no biological profiling was done. The structure was a complex, very interesting, 2 quaternary stereocenters, anticyclic case structure, and 7 stereocenters. So it was a challenge. Many people jumped on doing synthesis of this molecule because this is also isolated from a species which gives a lot of Amalgasi class of alkaloids. Since Amalgasi class of alkaloids are biologically active, chemists thought that this will have a good biological activity. And many people started synthesis, so we also jumped in that because we were synthesizing other alkaloids. So we started from our intermediates. Here, we did bromination here, then aldehyde and protection. First removal of tosylate group by reductive reactions, then protection here, then allylic hydroxylation. And since the stereochemistry in the natural molecule is opposite, so we inverted by Mitsunobu reaction to this, and PCC oxidation gave this. And now this was, take this to make the precursor for the azomethylhalide, to have this, and simply heating in toluene gave this compound. Now, deprotection of bar group and making N-methyl straightforward gave this compound. Now, while we were working on this, the absolute stereochemistry of the molecule was determined through synthesis. And also, 2 more syntheses came in the literature. Now, when the absolute stereochemistry became known, and unfortunately, our molecule, what we synthesize, happened to be the opposite enantiomer. So, other journals were not ready to take up this, so we published in European Journal of Chemistry. While doing this, we were also interested to, we were looking more complex molecule to attempt our synthesis, to sharpen our synthetic skill and also our methodology. So we selected this tricyclic compound, isolated from frog skin, G-phyrotoxin. It has biological activity as you see here. It has fused tricyclic ring, 5 stereo centers, and main framework is pyrrolocumulin framework. This molecule attracted attention very much because it has this kind of biological activity and the intriguing structures. When we started synthesis of this molecule, there was only one synthesis asymmetric was known. Racemic synthesis was known, 3-4, but when we started, only one total asymmetric synthesis was known. So we thought that we can publish this molecule much easier by synthesizing this molecule. So we thought, let's do like this. So we used our template, did this coupling reaction, fast reaction to have this, then cyclization, 1,2-diaxyl addition to have this intermediate, opening of this with sodium methoxide in THF methanol, give this tricyclic ring, which is we have now this where easily this can be transformed into the G-phyrotoxin. We spent a lot of time because if you look at this, you need a carbon here and we had a carbonyl. We thought we will do a Wittig reaction or any variants of Wittig reaction to do one carbon homologation here, but didn't work. Finally, we spent several months, we didn't succeed. So then we went to Curie reaction, made epoxide. I like to say here, the student could not do this epoxidation with a good yield. So only 40 to 50% yield was, she tried many times. Now we don't know whether the student's skill problem or the chemistry problem, but this here, bent, you open, protected, and from here we did this here, one carbon homologation, protection here, and she left from here, and we are proceeding here to, once we make here, the compound is known, the steps are known already. Now, why do this? I started thinking that why do we make molecules? Why do we develop our methodology? So this was bothering to me because of maybe the age, because we justify everything, but when you get more wisdom, you think, now why I am doing this chemistry? So this was bothering to me. So I thought, let me try something where I can do something for the benefits of humankind. So we made this G-phyrotoxin, and also we made one molecule, which is isoindolene, which processing had shown a methodology, but we made 1,3-isoindolene in a very simple way, which you can see here. I will not describe the method, but very nice. So we thought, let's give a hypothesis about how to make heat molecule in medicinal chemistry terms. So I said to you that we do synthesis and we build complexity. And as many of people in the audience, they know that I also have developed many methodology for organic synthesis. But this was something was bothering to me, that why all things we do. So we thought that let's do give a strategy for drug discovery, because this is what the ultimate aim of an organic chemist. And we thought that we can integrate product framework with the bioactive moiety to see if this gives you a strategy for a new drug discovery. And as many of you know, or many of you may know, drug discovery is a long process. Dr. Chauhan will know because he has spent his whole lifetime in CDRI. So it's not a simple thing. Not writing an introduction or make molecule, heterocyclic molecule, and that we have made a drug. So here, first you have to do target selection, lead discovery, medicinal chemistry, in vitro study, in vivo study, and potential. Now, I would like to justify this, why I started this work, because by the time when I was doing this research, I left NCL and I came to Lucknow, and people like Dr. Chauhan came in contact, and I thought I should use some of the expertise which they can provide. And with their collaboration, we started looking this. Now, look at this. You know, this many molecules are possible in the universe. The chemical space is this much. Now, you keep on making molecules, but what is the use? And also, we have 3,000 targets in the human beings. So how to do target selection? Random, you make molecule, you may get a lead molecule or not. And according to this, you can minimize to some Lipinski rule, but it is very difficult way to find a lead molecule. So that is why discovering a therapeutically useful molecule out of this vast chemical space, capable of modifying the biological target, which is this, essential for disease phenotype, is the most arduous and challenging task. Now, to reduce this problem, time to time, people have come with some idea. It's not working. Oh, I think battery has gone. Can you change the battery? Some problem. Okay, thank you. Now, minimize this kind of possibilities. Time to time, people have come with some kind of hypothesis. The hypothesis, see, people have been making random molecules screening. That is a separate thing, but more organized way of searching a molecule for biological activity started from somebody named Professor Schultz, and he says you do combinatorial chemistry. You take a pharmacophore and you do things, many molecules, thousands and thousands molecules you make, and some molecule may become active. But he forgot that pharmacophore is the same, modification won't work. But he advertised this so much, and machine came, and all national laboratories, including my National Chemical Laboratory, spent crores of rupees to buy a combinatorial chemistry machine, and they gave nothing. Okay. Another person, well-known organic chemist, Stuart Schreiber, he came up with the idea that you take a molecule and you diversify. And whatever the diversification you test, you may get a biologically active molecule. But it didn't work, that also failed. Some of these things are working, but it has not been established that this is the only way. But Waldman in Germany, he came up with the idea biologically oriented synthesis. What he means that if you have a molecule which is biologically active, that molecule you modify, and you may hit a molecule which may be that candidate, which is working. He claims that he has a molecule for anti-cancer and it is working. I don't know what is the success for this. In between, Professor Mehta and Professor Tietze from Germany, they come up with the idea that you make hybrid natural products, you take two natural products and combine them and they may become biologically active. That also didn't work. So, New York, Samuel Lenswetsky, he also came up with the idea. He called this diverted total synthesis. What he says that precursor molecules you divert, which looks like a natural product, and that may be biologically active. And somewhat he is successful. He has given a few drug molecules which are marketed, especially in anti-cancer. And along with this, we have also come up with the hypothesis that integrating natural product framework with bioactive molecule may hit and give a molecule. And I will show you the success of this hypothesis now. Now, this concept that you have a natural product, a bioactive molecule, and I would like to say that the G-thyrotoxin is our natural product. 1,3-isoamidolane is a bioactive molecule, and we integrate this, that which doesn't look like bioactive molecule or natural product in new entity, and this may turn out to be biologically active compound. So integrating natural product framework and bioactive concept takes an advantage of selectivity, diversity, and complexity of natural product framework and fuse it with a highly bioactive molecule in such a way that both are indistinct. And this careful selection of natural product framework, bioactive molecule, that you can find out. I don't have to do. Now, the stage has come target selection, and we selected. I'm sorry. Muscarinic receptor. Now, why muscarinic receptor? Because G-thyrotoxin has muscarinic agonist, and our isoindolane is also weak. Both are non-selective and weak. So we thought that let's see this receptor in detail, and we found out with the CDRI people's help that we have in this muscarinic receptor, you have M1, M2, M3, M4, and M5. And each of them has distinct biological activity associated, biological actions associated with this. And their locations are also pretty much described. M1 is CNS and gastro. This thing is there, and we have. Now, to cut this story short, we selected this muscarinic receptor controls vital physiological role in human system, and hence discovery of new and selective ligand which can modulate the muscarinic receptors will have a higher implication for drug discovery against several pathophysiological conditions. Now, having come to this, we came to now chemistry. As I mentioned, a natural product is integrated with the bioactive compound substituted indolene, and it can be done in two ways. This structure is shown here. You have G-thyrotoxin fusion here, and this is substituted indolene. We started making molecule. I will not show you retrosynthesis. It is clear that you can make through this chemistry. So let's proceed. we did synthesis of this, and first we make this compound, we get RG01. Why RG01? Because Rajesh was working on this molecule, this area, and he gave Rajesh Ganesh 01. So this, and you open this, he gave RG03, and further he made 4, 5, and so many. So he made 13 molecules altogether, and we started now testing. Now, first, as you see, it has to be tested in vitro, and with vitro, first molecule, which RG02, was found to be active in a 4 nanomolar concentration. The activity was there, and we thought, and all the more important, this was very selective to only M2 receptor, not all this, because the problem, as I understand, many drugs which are there, they are not selective. They target many in the biological system. That is why the effectiveness is less, and that is why search is on to find more selective molecule. So we studied in vitro. Now the same molecule. This is called water maze test. A mice is here moving. They have. I will show you a control. Where is control? Well, anyway, I'll show you later. And it is confused. Memory is lost. If this drug is given to them, the memory comes back and the mouse sits on this. So this is a pharmacological test, which is a universal test, is done everywhere in the world. So you will see that, now the mice will sit here. And then we made molecules, just to cut the story short, we made a molecule which is RG02, is active at M2 agonist, is active M2 agonist, 4 nanomolar, RG09 M3 at 0.1 nanomolar active. RG056 is M3 agonist again, 0.1 nanomolar, and this is not selective, it is M1, M3 both, it affects the combined here, and this is non-selective. Now, what we do here? So now we have after 30, just finishing, one slide. We are finishing. We found a drug candidate molecule which can be used, spending less time, wasting less compound chemicals. We made 13 compounds, and out of which 3 compounds are some use. And what you do? You first patent it. So we patented the word patent. This is Indian patent, UK patent, and US patent. Now, I just like to take 1 minute to say a few words about the patenting. When patent was written, that was a time that I had to move from Lucknow, CBMAR to PHU, and patent costs money. So CDRI people ask that who will pay 50% of the money for patenting. It's a CSIR jargon. So I said I have no money and I am not in now. I am not a director anymore. I am going. So I have no, either you patent or maybe I have nothing to do. They then approach to CSIR Of course, the patent was written by CSIR people, and when CSIR agreed that all the costs of patenting they will bear, neither CDI has to give, not the CDMA. So they paid the money and it got patented. And I would like to say concluding words. The natural products still hold out the best option for finding novel agents, active templates, which when worked on in conjunction with synthetic chemists and biologists offer the potential to discover novel structures that can lead to effective agents in variety of human disease. I'd like to just mention here, now this molecule has reached to a stage that one PK study has to be done and IND filing has to be done, then it can enter into the phase 1 trial. So PK study costs a lot of money and I am not there in CDMR, so I don't know what is the thing. Now, before I close, I should thank SCRB for supporting my research over at least three decades or 4 decades now in this fashion, JC Bose Fellowship, and now as a National Science Chair, Banaras Hindu University, for giving me a place to continue my hobby, and Dr. P.N. Adams, CDI, for doing all the biological activity. I just like to show the city of Banaras. Many of you may not have gone to Banaras. It's a beautiful religious place. See, this is the river Ganges. This is the main temple. And evening there is a Ganga Aarti. Is worth seeing. Thousands and thousands of people gather to watch this thing. And I would like this university, their department where I still carry out my research. And last, thanks all of you for your presence here. Thank you.
Excellent lecture, Professor Ganesh Pandey. And you have seen the wonderful lecture, and he told how the hybrid molecule approach to synthesize the more active. And in this approach, the artemisinin and chloroquine combined one molecule synthesized and found the parent molecule found the better than the hybrid molecule. So this type of the several approach the medicinal chemists use. But in hybrid approach, the combination of the pharmacophore having the different activity, target site. If they have the same active against the same target site, we never combine in the hybrid molecules. So this way the hybrid molecule concept progress, and we thank you for a wonderful lecture. And I think the time not permit to the question, then the Pandeyji is here, we can discuss. Okay. So, and now.
So, thank you, sir. I request Professor P.M.S. Chauhan to present a memento as a token of appreciation to Professor Ganesh Pandey.
Now the second speaker, Professor Mark Telefer, CNRS, the University of Montpellier, France. He is basically the synthetic organic chemist. His research focus on discovery, breakthrough methodology in field of the organic synthesis, homogeneous catalysis, CN-CO CC bond formation. He is excellent researcher and title of talk transition metal catalyzed or transition metal free CC and C heteroatom bond formation from the discovery of mechanism and industrial applications. So I request Professor Mark, please deliver it.
It's okay. Merci. Okay. Okay, thank you. Hello, everybody. It's a real pleasure for me to be here in Jaipur for the first time. And I would like to thank, of course, the organization committee for the invitation and also the SEFRIPA for the financial support for this travel. So today I'm going to present you some of my team's research axes, which correspond to the CC or C heteroatom bond formation. So I live in Montpellier, which is a city for India of small size, by the sea and also by the mountains. And in my team, whose name is Molecular Synthesis Methodology, we are looking for new reagents and methods in organic synthesis with two main themes focused on phosphorus chemistry and on catalysis. On catalysis, the goal is to try to discover new methods allowing the formation of CC or C heteroatom bond formation while using inexpensive and low toxic metals such as, for example, copper, iron, or manganese. And we have also methods proceeding in transition metal-free conditions or under visible light irradiations. So for these topics, we follow three main directions. The first one is the arylation of nucleophiles. The second corresponds to the hydrofunctionalization of unsaturated carbon chains. And the third deals with the functionalization of nucleophiles starting from alcohol as carbon sources. So first, the arylation reactions, whose general equation is represented here. The goal is to prepare this type of backbone, aryl nucleophile, which are very important targets in pharmaceutical, agrochemicals, but also in materials. These molecules are prepared from the reaction of aromatic halides used as electrophiles with nucleophiles in the presence of transition metal-based catalyzed. And the goal is also, of course, to have soft, mild, sustainable, and competitive conditions. There are a lot of methods allowing this method, and about 20 years ago, we found in the lab that it was possible to perform this coupling using catalytic amount of copper, as it is illustrated here with the arylation of various nucleophiles of pyrazole types performed in the presence of catalytic amount of copper in mild temperature conditions, thanks to the presence of ligands. Below you have our first ligands used, which are mono, B, or tridentates. So these results for us were very important because they correspond to a catalytic version of the Ullmann reaction, which require more than stoichiometric amount of copper and temperature higher than 150 degrees. So we immediately protected these results as a general methodology patents, as did my colleague in the MIT, Steve Backwald, And these two patents have been at the origin of what is now known in the literature, the renaissance of the Ullmann reaction. So since we did a lot of work with copper, mainly with copper, but also with manganese and iron, and we synthesize various families of compounds. We also synthesized drugs, and we have a lot of patents in this field. So today I'm going to present you some selected examples, and first, coupling resulting of CC bond formation with a first example with the iodation of enolizable ketones, which are possible in presence of a very simple copper catalytic system, copper iode and ligands. So this is the product. You have a CC bond formation here, and this method is very competitive compared with the method of the literature, which require palladium, for example. Palladium, which is a metal much more expensive and much more toxic than the copper. We synthesize, for example, tamoxifen, which since about or more than 30 years is the world's most commonly administered drugs for management of breast cancers. After the CC bond formation, one example of CO bond formation with the center of phenol. So above you have an industrial way to produce the phenol is about 10 megatons a year. The industrial way you start from benzene, propylation, then cumin, oxidation, workup, and for the industrial way, you have only 5% overall yield. Below, you have the synthesis of phenol derivatives, that is, phenol with giving electron or donating or withdrawing group. That are used for the synthesis of drugs, for example. There are hundreds of methods allowing this synthesis, and I represented here, for example, the iodation of silicon hydroxides catalyzed by palladium with sophisticated ligand. This is one of my colleague and friends, Matthias Beller, in Germany. So we tested the copper for this type of reaction, and we observed that iodation of potassium hydroxide is possible here too, in the presence of a very small amount of copper, catalytic amount of copper, associated with simple ligand to give the phenol. So it was a very competitive ligand results compared to the palladium, and the difficulty here is to stop the reaction at this level. Why? Because the phenol itself is a nucleophile which is potentially able to react with the starting electrophile. But by a fine-tuning, you could either stop the reaction at this level or continue and starting from two different aromatic halides as a electrophile with cesium hydroxide, we could obtain the synthesis of unsymmetrical diaryl ethers. Now, one example of CN bond formation with the synthesis of aniline. The production is about here, like a phenol, more or less 10 megatons a year. And the main industrial way is this one, the reduction of nitrobenzene in presence of catalytic metals, mixtures, and at huge temperature. There are not really efficient industrial way to produce aniline using ammonia. And it's a pity because it will be interesting to have a method with ammonia. You can see here that ammonia, which is obtained by the Haber-Bosch process, its production is really huge, and more or less 2 to 3% of the worldwide energy production and consumption is dedicated to the synthesis of ammonia. So it will be interesting to use it. And we try the copper system, and we obtain that the iodation of ammonia is possible to give very good results with these extremely simple ligands. You can compare the literature, the other way requires the presence of toxic and expensive palladium. You have some example below. So after these first three examples, some was concerning the mechanism for which we carried out a lot of experience. I selected just a small part. We observed the conclusion of these works was that the mechanism is strongly dependent on the nature of the ligands, because we have nitrogen ligand, carbon ligand, or phosphorus ligand. So today I present with
carbon ligand, ketone type ligand. I choose the reaction I presented to you right before. And the first step is we perform a lot of work in collaboration with NUJ Paris, DFT calculation, with a lot of work. The first step will be the attack of the copper by the nucleophile to give this first intermediate, copper 1. Then there is a formation of a iodine-oxygen bond to give this intermediate bond, which evolves to the formation of this product, a copper 2, which is a formal result of an oxidative addition. And then via reductive elimination, you have a product. So this is quite unusual. This kind of oxidative addition is assisted by the formation of this iodine-oxygen bond. It's really unusual. We thought it was new, but actually, when you want to prepare phenylithium from phenyl iodide and butene, for example, then you go through this intermediate, which is really close to this one. That's the Rice transmetallation. So the conclusion of all our works is that copper 1 is the real active species in all this chemistry, and that the nucleophilic addition takes place before the oxidative addition, which is quite unusual. After the copper, some example with manganese and iron. Manganese and iron, which has the copper, low toxic and expensive. A few words. Why finally palladium, platinum, for example, are so toxic? Maybe because the life evolved without these metals, or in the presence of very small amount of this metal. It's not the case for iron, copper, manganese. The life evolved with them, and maybe the best example is the butane, with an iron atom in the hemoglobin. So the first example of coupling started with iron catalysts, which allow the homocoupling, thus the formation of biphenyl in the presence of butyl lithium. It's a first example that I will not detail today. What is interesting is that we try to perform this reaction also with manganese. First, by exchanging iron CO3 with manganese, and then we observe nothing. But as for the iron, the reaction was performed under inert atmosphere. When we perform it under dry air, then we could obtain the homocoupling reaction, starting from iron to halide, or even from arene. You have below the scope, which is very, very broad. So this is a very competitive system because exactly the same has been published, but with palladium quite recently by Ferenga, and palladium associated to a sophisticated carbon. You can compare the two systems. What about mechanism? So the first step will be from the two catalyst its reaction of two equivalence of iodine in situ generated in the medium to generate a new manganese 2 complexes. And then the oxygen allows to transfer manganese 2 in manganese 4, from which a reductive elimination is much more easier than from manganese 2. Then the product is expelled, not really because it is first coordinated to the manganese through one aromatic cycle. And then in the presence of lithium, the product is expelled and the catalyst will be regenerated. Because even for all the mechanism, even if you carry out a lot of work, you are never sure, okay? Thank you. Now after metals, some example without any metals. So here, you remember maybe the first example I gave you to synthesize some oxyphene, catalyzed by copper. Actually, we could perform the same reaction without many metals. Sorry. Okay, we could perform this reaction instead of copper using potassium testosterone and the solvent, DMF. And this couple was able to favor this reaction with a broader scope than the copper and then a broader scope than with palladium.
we suspected, we assumed that the mechanism was a radical one, and we carried out a lot of work together with DFT calculation. We first thought that the potassium tertiary oxide was able to give an electron to the starting aromatic iodide to generate the aryl radical. But DFT calculations showed that it was not possible, and that it was rather this intermediate carbonyl anion in situ formed from the reaction BFMF with the potassium tertiary oxide, which was able to give an electron to the aryl iodide, thus generating aryl radical in the medium. Then it reacts with the nucleophile, which is the enolizable ketones, which is deprotonate in situ. There is a formation of a new radical anion intermediates, which gives an electron to a new equivalent of aromatic iodide, and then you have a product. And the aryl radical is regenerated. What about the current on this chemistry, on this arylation chemistry? So we must always improve our system. For example, with copper, with reusable catalytic system, or with even more sustainable conditions. We are also to improve our turnovers and our turnover frequencies. Concerning the starting substrate, aromatic chlorides are not very efficient. It's a pity because aromatic chlorides for the industry, even they are less reactive, they are also less expensive. So it will be interesting to find efficient method. And finally, it will be also interesting to start from aryl mesylate used as electrophile for the industry, because that could open all this coupling chemistry to phenols, which are feedstock. Concerning iron, manganese, our method without transition metal, now a lot of teams works on the topic, but compared to the copper or palladium, it's only the beginning. What about the industrial applications? The Rodier company was the first to apply our concept, the copper catalyzed arylation of nucleophiles in production. And after, an Indian company, the Fashion company, produced a lot of drugs and agrochemicals in the United Kingdom. You have below the industrial production site. So after you are here, it is not an exhaustive list. A lot of companies applied the concept either at the laboratory scale or in productions. And the success of this method is probably due to the fact that the copper is inexpensive and low toxic. And that has been recently reinforced by a new European regulation. Sorry, it's difficult to stop. Okay. Quite recently, since about 10 years, to sell a drug now in Europe is more difficult. Why? Because there is a new very strict safety regulations. And the consequence of that is that there is a risk of stockout for drugs. And now it's no more a risk, it's a stockout for dozens of drugs in Europe. And that has been recently reinforced by the COVID crisis and by the Ukrainian war. In this context, the copper catalysts are efficient too, because they are inexpensive to synthesize active principle of drugs. And we could, for example, synthesize with our system the active principle of Central. Central is an analgesic and antiseptic. It is a very popular drug in France. Almost families are in France has a bottle sample at home. But with this new European regulation, and because non-confirmed production, Central, more or less 10 years ago, was withdrawn from sale in pharmacies, no more Central. However, thanks to the efficiency of the copper system and the low toxicity, we could synthesize the active principle of Central in the south of France, and now you can find the Central in pharmacies. That's an example of you start from a molecule in the lab, and then in your village you can boil the drug. A last example of industrial application. The copper here is able to catalyze the coupling because alkynes, for example, and vinyl bromides. Vinyl bromides, the reactivity is more or less the same than aryl bromides. to give this molecule, which is a pheromone. And this is a pheromone of a processionary caterpillar on pine. This caterpillar is a pest which destroyed almost all the forest of pine in the south of France quite recently. If you want to control this pest, you can use pesticide, or there is a new tool which appeared recently using pheromones. And if you put this pheromone, this is the pine, around the pine, then the male is no more able to recognize the female, and the reproduction is blocked. You destroy the pest. So now it was really the bigger part of work. Now, the hydrofunctionalization of unsaturated ketone chains. I will not present the iron. Okay, this type of reaction can be catalyzed by the copper. For example, starting from alkynes or alkenes with a total atom economy, which is interesting. So these two alkynes and alkenes are substrates of choice for this type of reaction, but I have chosen to illustrate that starting from another one, starting from alene, which is said that we hydrofunctionalize with nucleophiles in the presence of a proper catalytic system to give a product. Very often, the nucleophiles is in terminal positions. You have here some type of electrophiles, nitrogen electrophiles, oxygen, phosphor, sulfur, carbon electrophiles, and illustrate the catalytic cycle I've chosen the sulfur. You have here the hydrochloration of an alene to give the product with some selected example to show the growth scope of the method. And you can see that the catalytic cycle is the catalyst is very simple, room temperature 2 hours. For the mechanism, the first step will be the reaction of this cation, copper cation with alene coordination. Then attack of the nucleophile the first time to give these intermediates. Attack the second time of the nucleophiles to give a new intermediates and to give the proton. And then there is the product is expelled and catalyst regenerated. You can use the same system starting from alkenes or alkynes. It's sufficient too. Now, last example for hydrofunctionalization. Under visible light irradiation, with the hydrofunctionalization of styrene in the presence of starting reagents such as, for example, hydrides. Give the corresponding hydrocarbomoylation, acylation, alkylation, or silylation product. This system is possible thanks to a double catalytic silicon based on tungsten and sulfur, and under visible light irradiation. The first step is the generation in situ of a radical, thanks to the presence of activated tungsten from the starting reagent here. This radical works with the styrene to give a new radical which evolves via HRT to the product. This HRT process is possible thanks to thiophenol, and the thiophenol also helps the regeneration of the catalytic active of the tungsten. Now, the last example I'm going to present you today concerns the functionalization of nucleophiles starting from alcohol in transition metal-free conditions. Alcohol are cheap and environmentally benign substrates which can be obtained from lignocellulose and from biomass, and they thus constitute sustainable alternative to fossil resources. So we try to use them to synthesize an heterocycle. Through this reaction, the alkylation of methylated N-heteroarene. So reaction is represented here. This is a noun reaction where methylated heteroarene reacts with alcohol in the presence of transition metal-based catalyst. This is a well-known hydrogen process. So we show that it was possible to perform this reaction without any transition metal with the same couple I showed you before, but for a completely different reaction and with a totally different mechanism, duality. And we obtain like that families of compounds, pyridine, quinolines, pyrazine, quinoxalines, for example. The probable mechanism is represented here. First, you deprotonate the alcohol in the medium. It reacts with the solvent to give the formulates, which itself reacts with the deprotonated and methylated RM to give the office intermediate, the product. We also apply the system to the synthesis of alkenes and also of benzophenone. So now, just before concluding, from the phenol, we have also a collaboration with Professor Hota from Pune. This is a state-of-the-art collaboration in which we work on decarboxylative glycosylation, but work being in progress. I will not present it, the corresponding results today. It's at the end. I was at the conference of Professor Negishi some years ago, and at the end of the lecture, he presented these two pictures of two Nobel Prize, Victor Grenier and Paul Sabatier, as an exceptional pioneer in this type of chemistry. And I had the photo of Fritz Ullmann. He was not Nobel Prize, but he was also an exceptional pioneer in this type of reaction. So to conclude, I thank all my students and permanent research and my team, the financial support, and I thank you for your attention.
Thank you, Professor Mark, and excellent presentation. If you have one or two query, please you can ask.
If you want, you can ask me. Discuss with me after. Do not hesitate.
Okay. If you have no query, then please thank you. Excellent presentation by the Professor Mark.
Thank you, sir. I once again request Professor P.M.S. Chauhan to offer a memento as a token of gratitude to Mark Taylor from University of Montpellier, France.
Window B, sir. Sir, one. नहीं ना नहीं वो है साउंड क्या बता ऑफ विंडो
Good afternoon. The next speaker, Professor Akila Sau, He is a student of Professor Ganesh Pandey. He worked as a postdoc, 6 year postdoc at University, and 1 year in RWTH Aachen. And he is a synthetic organic chemist. I request Professor Sau for his presentation. Professor Sau.
So it is just 12 o'clock. So I don't know, it is good morning or good afternoon. Oh, 1 o'clock, good afternoon. Thank you, Dr. Satpal, for the kind invitation. So I'll be discussing some of the recent discoveries that we have made in our group. So if you know that one, any of this alkyne, if it is a heteroatom substituted alkyne, that is sulfur, nitrogen, oxygen containing alkynes. And the reactivity, if you see all the three things, the homolomograph interaction between the enamines is quite compatible or good, where you can functionalize the molecule with your own domain. Whereas these things is quite difficult, and in case of sulfur containing alkyne, it is quite easy, but it is difficult. It is quite non-sustainable, as the compound is quite unstable into the molecular skeleton. The problem of these enamines, because if the nitrogen lone pair electron, when it is delocalizes to this, the beta position is nucleophilic, alpha is electrophilic. Therefore, a nucleophile can quench at alpha position, and electrophile as beta position, you can get a difunctionalized molecule. But the problem is that because of the ketoniminium species, the hydrolytically is unstable, and that can be avoided if you put electron neutral group on the nitrogen, such that the delocalization of electron is inhibited. Over the years, various protecting group has been used, and then they had different kind of enamide has been prepared, and that can be exhibited for various difunctionalization species. And this one is the predictable reject selectivity, but there is always, if you want to discover something which is completely different, then the Ompolong fashion, where a nucleophile quench at nucleophilic center, electrophile electrophilic center, and this type of things is quite challenging. None of the group in the world is working on this area, because it requires a lot of challenges that you have to inhibit of this electronic factor as well as steric factor. Moreover, radical assisted reactions are recently gained attention, and they have been cooking. What I'm going to tell you in the next 15 minutes, the difunctionalization of this type of alkyne species, as the world is now cooking about a lot of difunctionalization of olefins, and the reactions in which a nucleophile and electrophile can quench, and this can be possible if you have a low oxidation state of addition of a metal to the electrophilic species. You get higher oxidation state of a metal that undergoes migratory insertion and followed by ligand exchange and nucleophilic replacement, and you get a difunctionalized compound. In contrast, the same reaction is not very common in case of alkyne. That is because primarily due to the higher oxidation state of a metal, which is alkynyl species, that undergoes protodemetallation is quite easy or quite high, and therefore this type of species is rather difficult. Moreover, in case of alkyne, unsymmetrical alkyne, there will be always regioisomeric mixture. So over the years, what I have mentioned, that the olefin can be exposed to various of the electrophile, nucleophile reagents, and that can give you the highly substituted olefinic factors. And then in case of the most striking examples recently has come up from the Sigman group, where the terminal olefins, in case of a diene, can undergo selectively the olefination reactions. The boronic acid and the vinylic triplet has been used for this type of disubstitution of the olefins. But moreover, as you can see here, in case of alkyne, a serendipitous discovery has been discovered by Itami, in which a silyl pyridyl group has been used for difunctionalism of alkyne, dated in 2003. The intention was to do about the silicon-based cross-coupling reaction, but they ended up with this type of molecular scaffold. But molecular scaffold, whatever they get, this is not very large enough. So as I have already mentioned, that can we do some kind of reaction discovered in case of unsubstituted alkyne like nitrogen with alkyne, where a nucleophile and electrophile can quench in the Ompolong fashion. Moreover, if you have a tetrad acetate or any kind of alkali containing unsubstituted alkyne, can we do a difunctional species?
So these are beyond NGP, and this is just electronic factor. Another will be the neighboring group participation, but it is not basically the neighboring group participation effect. So to accomplish this task, what we can think of that one of the group on the LAM in 2019, very striking examples where this kind of dynamide has been subjected to the difunctionalization where the rhodium and zinc complexes have been synchronously used, where the vinylic rhodium undergoes transmetallation zinc to make it a soft and then undergoes the electrophile quench to get this compound. The cyclization motif that has been, we have demonstrated a few years before, a ring strain moiety can undergo intramolecular cyclizations where a 1,3-sulfonyl migration followed by 1,5-sulfonyl migrations could give you such kind of molecular skeleton, and that we have demonstrated in a ring strain method a few years before. But all these things in a cyclization method. What about a naked molecule when you get three-component reaction with three different entities can brought together and make it in a perfectly synchronous way? This can be possible if you have dynamide and then quench with a corresponding higher oxidation state of a metal, you get a ketinimino species. Provided if this species is stable enough, then there is a 1,3 migration occurs. You get a corresponding electrophile to the electrophilic center and then vinylic metal species that undergoes nucleophilic transmetallations followed by reductive elimination to get this compound. Although it was very simple, but we are surprised and then fortunate enough to get this type of nucleophile and electrophile quench by the palladium catalytic system to get such kind of highly modulated, very stereoselective, 100% regioselective tetrasubstituted enamide species. The condition is quite simple and make this type of compound from a simple precursors that has been readily available. And the scope of the reactions is quite broad, in which we can make such kind of molecular scaffold where heteroatom heterocycles can be also introduced in the molecular scaffold. Then you can do different kind of aryl diazoinium salts where you can introduce here different groups. Moreover, interestingly, a vinylic moiety also can be introduced here if you have a corresponding vinylic boronic acid moiety. The different protecting group has been also did not affect the molecular outcome to get a corresponding this type of highly peripheral decorated enamides. Interestingly, if you have alkyne and olefin, this alkyne and olefin, they are unaffected by these reagents where only the corresponding the enamide species undergoes the corresponding difunctionalization process. As mentioned by many people, so here we can do the reactions in a gram scale. You can do the oxyfluorination where you can introduce a fluorine group here, a quaternary substituted keto compound. You can do epoxidation, you can do intramolecular dehydrogenative coupling to make a corresponding expanded pi conjugated system. And then we can do a corresponding oxidation of the corresponding moiety which are present here. And then we can take the corresponding halo moiety to different kind of molecular skeletons, and that can be used for various applications about the molecular topology. So to make these things, when we discover new reactions, we always are interested to take the help and to say what we discuss or what we discover or what we propose should be proper. It should not be like a plausible mechanism without any bias. So in that case, I'm very happy that Vincent, who is going to give lecture in the afternoon, he always extends the help to showcase or to mitigate that what we discover, what we observe should be thoroughly investigated or supported by the DFT studies. What you have to do here, the palladium 0, in that case, oxidative insertion occurs to get a corresponding cationium palladium species where DMSO plays major role that makes the palladium cationic species stable. And then it undergoes the corresponding insertion to the alkyne motif, you get this. And then it releases energy of around close to 13 kilocalorie per mole. Then 1,3 migration is very viable where from minus 13 it can goes to give you the minus 25 kilocalorie per mole where 1,3 migration occurs. And then transmetallation followed by the reductive eliminations where you get a corresponding compound releasing close to 75 kilocalorie per mole. The catalytic cycle is so simple, so smooth, where end of the day you release around 78 kilocalorie per mole. That means this clearly tells us that reaction can be possible even at room temperature or at low temperature. Now, by extending this system, If you want to do same thing with a naked olefin, can you do the same kind of moiety where you can get a linear conjugated diene, aminodienes? Some of the people, 2 or 3 groups, they have used this kind of methodology where the corresponding ionamide has been subjected for alkylation, where they get only the alpha alkylations. Not a single report has been arised where the beta alkylations can be made from this type of species. What we have already shown here, when our reactions is, the first step is the arylation, so that undergoes to the free position and then 1-3 migration. We already set out this type of intermediate. If finally palladium intermediate can be quenched with the olefin and then followed by reductive elimination, then you get a beta substituted olefin where it is called aminodienes and 100% stereo regioselective. And this is also possible, in this case is possible where the corresponding palladium 0 and benzoquinone plays major role, because benzoquinone that doesn't allow the molecular here, the rotation of this molecule, the beta hydride elimination, where we can get explicitly the thermodynamically stable E product. The scope of the reaction again broad, picking many compounds where you can have a biological radioion motifs that can be attached at the end of this molecular scaffold to get very complex molecular skeleton from simple precursors. Moreover, we do a lot of competition experiments, and in that case, we always understand that how the reactions proceeds. Moreover, if you do these reactions in the presence of a corresponding diazonium salt and olefin and alkyne, the corresponding olefin undergoes insertion is very effective, leaving the alkyne ineffective. That gives a hope that there is a possibly chance that hydrometallation can undergoes to the corresponding alkyne, which can be done in the future. Moreover, if you have aryl boronic acid, a competition between the 2 species, the aryl boronic acid does not take part in the reaction, which is very large, where the olefin undergoes the reaction quite easily. Having this compound in hand, we can do peripheral decoration of this compound by trivial transformations. Lastly, we can see this one. Can we do these reactions, extend this reaction to make corresponding highly regio and stereoselective tetrasubstituted olefin, where tamoxifen is one of the leading drug candidates that has been used by Asian countries for breast cancer drug. Having this molecular entities in our mind, we thought that can we extend this strategy to a corresponding propargyl acetate. What one of the recent report by English group has shown that if you have a bidentate group that undergoes such kind of hydroarylations, as Mark just now explained, one of the hydroarylations, where this directing group can make a or can assist a arylation and then palladations and then get a corresponding hydroarylations. But non-report has shown that how you can make such kind of compound diarylations. Again, same, the Subham Datta. So if you take a corresponding palladium, propargyl acetate, if it undergoes if you just take a corresponding iridium palladium species, that can give you this type of aryl palladations, which is more favored compared to this one, because the corresponding palladium and ligated species that undergoes this paper because of the lone pair repulsion between the oxygen lone pair to the corresponding palladium species. So at low temperature, you can get this type of moiety that undergoes arylation, alkylation easy. So in that case, all are unsubstituted, naked molecular scaffold, and then this can be extended to the diarylation of the propargyl acetate or aryl alkylation of the propargyl acetate. The molecular scaffold once again shows quite good from simple propargyl acetate molecule, and then the yield of the reactions is quite moderate to good yield to provide such a large varieties of complex molecular skeletons without much trouble. Moreover, if you have a different alkyne on this, where it will be tetrasubstituted here, quaternary containing species, making such type of moiety is quite challenging in a trivial synthetic transformations. Wherever if you see, if you have any of these one moiety, there are complexities in the propargyl acetate, the rest of the reactions, although moderate, but making the corresponding this type of complex molecular scaffold, that turns out to be that a good strategy where you can make such kind of scaffold quite easy. If you extend the corresponding carbon chain length, you can get a mixture of the corresponding radioisomeric product that is quite expected, as acetate, this kind of moiety does not affect in the reactions. So you can do these reactions, again extend some kind of biological relevant motifs, you can attach into the corresponding aryl group, and then such kind of molecular scaffold can be made, although in moderate yield. In case of same thing, we can extend also aryl alkylation, where the arylation goes and alkylation followed by alkylations you can get a conjugated diene system where again it will be showing the corresponding stereo and regio selected. Only one of these products obtained. Moreover, in some cases, when you extend the corresponding this moiety or alkyl chain, you will get little bit of the regioisomeric mixture of the compound. Interestingly, if you increase the bulkiness at this proposed elicited center, that does not affect the reaction outcome, although little bit yield is less, but we can get a highly complicated molecular scaffold. We just studied that how this reaction is completely different than what is known or some of the Lara conditions reactions which has been shown few years before, in which if you use the corresponding Lara condition, you get such kind of compound, but regioisomeric mixture excess is around 50%. The same reaction can be extended under our conditions. It is also similar result. However, if you want to use the same thing with the corresponding diazoinium salt and the corresponding these conditions, we get 100% regioisomeric mixture. That clearly tells us that the reaction involves different type of reaction mechanism. Moreover, when you have a different kind of alkyl system, you get distinct ice of the corresponding diarylations where regioisomeric excess is little bit more, but quite comparable with the Lara conditions. But when you increase the bulkiness, this center where Lara condition completely fail the reactions, where in our cases we get 100% regioselective, 51% yield. This clearly tells us that how the reaction goes. Again, Vincent came to the play to showcase, to mitigate that what is happening in the reactions. Now, if you have a palladium 0 system, here palladium the two, in that case, there is an oxygen, there is an alkyne, there will be two coordination, either monocoordination of oxygen, monocoordination of alkyne, or dicoordination species. If it undergoes a monocoordination to the corresponding oxygen, the energy required for the first step is quite high, whereas in case of the dicoordination, it will be around -5 kilocalorie per mole. Rather, if you have a monocoordination of the alkyne, it will reach you to corresponding 7 kilocalorie per mole. Having this one in hand or the system in the flask, then this undergoes the corresponding migration or the corresponding carbopalladations, and the first step releases 20 kilocalorie per mole. This clearly tells us that you have different kind of molecular level of scaffold where you can get a monocoordination, dicoordination, and the monocoordination of alkyne. This is more favored, and then first step is very trivial, very challenging, but the release of 19 kilocalorie per mole in the first step that drives the molecule to go in that class. In the last, I will tell you about the corresponding methylations. The methylation reactions is quite challenging nowadays, where methylations in the molecule can modulate the solubility, hydrophilicity, and the conformational flexibility. So some of these people have been already discovered now, the directing group assisted methylations, and those methylating agent has been used. Moreover, the problem exists that what is the in case of methylation of the corresponding alkyne, there is called only one report called the allyl methylations with the nickel catalyst in the presence of a Lewis acid. Whereas other cases are nothing is known on this. Can you do the alkyne with the difunctionalism of aryl methylations? And if you want to make such kind of things, if you do the corresponding aryl palladations to the alkyne and then undergoes corresponding methyl boronic acid, there are some challenges. The first biggest challenges is that this binary palladium species always undergoes very fast proto-demethylations, and you will end up with a tri-substituted olefin, and which quite trivial. But if it undergoes, if it will have some stability, then if it undergoes a corresponding, the transmethylation to the methylation here, then this undergoes again protylation to get a corresponding methane gas. In that case, this also is quite challenging. So if it undergoes reductive elimination, then we can get the corresponding aryl methylations. Indeed, what we have thought, we could get this kind of compound aryl methylations, which is in ASAP. So this aryl methylation of enamide and the corresponding disubstituted propyl acetate, we could get it a highly regio and stereoselective aryl methylation of this compound. And then enamide under this condition where palladium TFA2 in the presence of a base. But water plays quite major role in this kind of reactions. The scope of the reaction is again one bird where the corresponding enamide undergoes aryl methylations, where aryl group is next to the corresponding nitrogen moiety and methyl the beta to the corresponding nitrogen system. Different protecting group have been survived under these reaction conditions, and you can get a large variety of such kind of aryl methylation product. Moreover, the enamide in case of different aryl moieties on the enamide can be can lead to the corresponding aryl methylations. Moreover, it is quite interesting to note that when there is an alkyl group, the reaction also provide the corresponding aryl methylation product. And the corresponding this kind of diazoam comes out with biological relevant motifs. When they use for this kind of aryl methylations, we could get the product, although moderate yield. The problematic challenging task is that we could not get the same reaction with the aryl alkylations. There is a big challenge. And in case of aryl alkylations, there is still some of limited variety undergoes only to the primary alkyl group when secondary and tertiary alkyl group fail to give the corresponding product. In case of to make the corresponding system more viable, we can do that how the corresponding deuterated boronic acid that can also undergo such kind of reactions where this type of molecule can be used for various drug candidates or maybe deuterated level experiments on that. The reaction is quite scalable. We can even do it in a gram scale quite nicely. And then oxyfluorination can give you the product. In oxidative cyclization, you can get such kind of molecular skeleton. Moreover, peripheral decoration of this kind of compound can be do oxidative cyclization. You can get such type of molecular scaffold. When you do corresponding reaction in the D2O, there is no deuterium incorporation. That clearly indicates that D2O is only halves for transmetallation. That word, the corresponding photodemetallations is restricted. Moreover, when you wanted to do the same reactions without no catalyst, there should not be any reaction. That means reaction with the different palladium zero also undergoes reaction. Clearly indicates palladium zero is a limiting reagent that can lead to the corresponding compound. The solvent plays a major role where if you have a mixture of the solvent that can lead to the corresponding product, other solvent is problematic. That clearly again testified that when you have a bidentate solvent that can make the corresponding palladium to the palladium zero, and that is helpful for your rate limiting step for corresponding aryl palladations. This is quite trivial mechanistic insight, what we have already demonstrated. And then if you have a corresponding coordinated corresponding nitrogen moiety, that did not give you the corresponding product with mixture of isomers. So in summary, what we have already shown that in the past, we have discovered many of the monocyclides, and now we are going to a more complicated molecules. We do a lot of CH activation chemistry where we can do now in a one step 16 bonds quite easily, and now stereoselective CH activation and very complex molecules. So this is the group we are proud to be here. I'm proud to be here, and this is my maybe fourth or fifth visit to Jaipur. And this is the people they have contributed to our group. What I have shown to the work is only contributed by a single person, Subham Datta, for this chemistry. So thank you for your kind attention, and I'm thankful to the Vincent Gando for assisting us whenever we need. Thank you so much for your kind attention.
On behalf of the organizing committee, we thank you, Professor Sahu, for his excellent talk. Please give a big applause to Professor Sahu. Actually, time not allowed me to for question answer, and during lunch time you can discuss. Okay.
Thank you, sir. Once again, I request Professor PMS Chauhan to present a memento as a token of appreciation to Akhila K. Sahu, Professor Akhila K. Sahu.
This one? Yes, sir, this one. Okay, okay. So, इनको देखो
Sir.
Yeah, one of me.
So next speaker, Professor Bhagwatullah Prasad from Center Nano and Soft Material Science, Bengaluru, and Physical Material Chemistry Division. And his title of talk, All-in-One Precursor for Preparation of Metal Sulfide and Biometallic Sulfide Nanocrystal. Professor Bhagwatullah Prasad is working as Director of Center of Nano and Soft Material Science, Bengaluru. He also holds the position of Chief Scientist in the Physical Material Chemistry Division of the NCL Pune, India. Now I request you, Professor Prasad, for his talk.
Thank you. Thank you. Good afternoon. And I thank the organizers for giving me this opportunity. I'm sure you are not really looking at what I will speak, but where my summary slide will come from, right? I will try to be as quick as possible. I belong to these two institutions right now at the Center for Nano and Soft Matter Sciences and National Chemical Laboratory, Pune. And I don't have to introduce NCL. I'm sure many of you have seen or many of you have studied there. But this institution where I am right now working is a new institution. So I will quickly do a small introduction. This was actually established as Center for Liquid Crystal Research, which they later rechristened to Center for Nano and Soft Matter Sciences recently. We have moved to our own campus very recently. Earlier, we were in a rented accommodation, but we now moved to our own campus. It's a nice small campus. I request all of you to visit this place. We are establishing still our hostel block just constructed. You know that what it means. So we are just establishing the center at this new location as we are speaking. So the areas of research of this center is in mainly soft matter and liquid crystals, which is a unique combination along with nanomaterials. And then we are able to look at some applications like energy and environment, of course, large scale. This is as many speakers previously also spoke about, and some health related issues as well. So again, it's a very small center, about 15 scientists that we have. And these are some of the facilities, and again, institutions like University of Rajasthan, please do use our facilities. Our facilities are available both on ISTEM and then this CRF, which is Central Research Facility. We have good facilities for a small lab like us. So please do use for your research as well, and we will be happy to help you. And we are doing good, reasonably okay for a small center. And one of the good things about us is that we also not only just do, I think there is a, yeah. So we not only just do science, we also do some translational activity. You can see that these are digital curtains. You can see the glass doesn't have any curtain, but you can at will, by clicking a button, you can convert that into opaque or transparent states. Or this is a curtain that you can rise and down. Just it is basically a liquid in between two glasses, which you can basically shift it at will. And of course, during COVID, we also have done some work in the area of electric masks, which is available on Amazon. You can buy it still, which is marketed, right? And of course, because I don't see much of students right now, but if anybody's student is interested, please come and join ours for PhD program. And good thing is even GATE qualified candidates can come here, and then we can provide fellowship with that. And last advertisement from this one, I recently took over as a editor-in-chief of Bulletin of Material Sciences, which is published by Springer and Indian Academy of Sciences. So I urge all the materials chemists, of course, who are working in the area of interfacial sciences, please do submit your papers to the journal. We want to take this Indian journal
much better. You can see that most of the American Society or RSC journals are becoming the kind of you have to open access journals, which means that you have to pay for that article fee. We don't do that, so please do. I encourage all of you to, so please submit good papers to this journal so that we can make it better. So with that, let me move to the topic of today. We basically work in these areas, but today I'm going to talk mostly about this large-scale synthesis of nanomaterials. I think I'm the first speaker in the area of materials, right? So that the interfacial sciences is justified for this topic, for this conference. So in the area of nanoparticle synthesis, we have just summarized our work and of course what is known in the literature in this Chemical Society review. I request all the students and others interested to look at this paper, which has just been, it's a tutorial review. We try to make it as general as possible so that everybody can understand what is happening in this area. So today's topic is not about the metallic nanoparticles that our group is generally interested. We are mainly talking about semiconductor nanocrystals. These are extremely interesting and important because they show very interesting properties. One of the properties that they show is a size-dependent emission. So look at these materials that are being shown here, all are exactly the same composition. The cadmium selenide coated by a zinc sulfide layer. But though the composition is exactly the same, the crystal structure is same, but by just changing the size of the particle or the crystal, you are able to modulate the wavelength at which the emission happens. So this kind of an interesting property is impacted on these materials because of quantum confinement, etc. So this is an extremely important area of research, and they have obviously have some other applications, many applications in different fields, including display technologies to bio-related applications. And for these reasons, the market requirement of these semiconducting quantum dots is quite high. You can see that the market is actually increasing, and by some projection, there is apparently about from 100 kg in 2015 to there will be a requirement of 2 metric tons in 2026. And when you want to, not only that, one more problem with this large-scale synthesis, when you're talking about large-scale synthesis of quantum dots, especially as a dispersion, is that there should be compositional purity, there should be monodispersity, which means that all the nanoparticles that you are preparing, all the nanocrystals that you're preparing should be of the same size. There should be minimum trap states. I will come back to that a little bit later. And of course, when you are synthesizing these materials, there should be lab reproducibility, batch to batch, and of course, lab to lab. So with these challenges, if you look at a standard synthetic procedure for a semiconducting nanocrystal, so this is a paper that is published in 2017. You can see that this paper has about 2 pages, right? 62 printed pages. That means that it must be a compilation of large number of synthetic procedures. And I don't know whether you are able to see it, but this is basically a synthesis of cadmium selenide zinc sulfide that I have just shown. And it requires so many steps. And then there is 300 degrees centigrade, 280 degrees centigrade, like that. So many reagents are needed, many steps are needed. Control is extremely important. So for all these reasons, it is very difficult to make large quantities, and therefore you see that the amount of material you are dealing is roughly about 30 milligrams. Right now, this is what we are making: 30 milligrams of the material you are making, but the requirement is somewhere around 2 metric tons. So it is not very easy to kind of bridge this gap if you want to think about it. So therefore, I don't know what is happening. Okay. The general route for this synthesis is to use a sulfur precursor. This is a hexamethyl dicyrathione. So this sulfur is very reactive, and therefore it releases when you do what is called a hot injection method. And therefore this is used to make variety of metal sulfide nanocrystals like lead sulfide, silver bismuth sulfide, etc. I'm sorry for this. I think due to the change in the laptops, these are getting overlapped. I'm very sorry for that. So these are the standard procedures, and this is the standard sulfur precursor that is used. But what is the problem? This sulfur precursor is actually not very easy to handle. It is pyrophilic and also is hygroscopic, etc., etc. So it is not very easy to handle this material. And again, if you want to use this precursor to make 2 metric tons, it's not going to be easy. And obviously, people have been looking at alternative sulfur sources. What are the alternative sulfur sources? One alternative sulfur source is thiourea. And Jonathan Owen from Columbia University, what their group has shown is that by using different thiourea as sulfur precursor, you substituted thioureas. The substitutions are shown here. So different numbers are basically different substituted thioureas. By using different substituted thioureas as sulfur precursor, you will be able to make lead sulfide of different sizes. Right? So for each size, you have to use a different thiourea as a sulfur source. This is one way of dealing with, and thioureas are not so difficult to handle. What we thought is, it's not so elegant, and it's not that all prasads are impressive instructions. It is just coincidence. Okay. So we thought, obviously I went to my friends in organic chemistry. How do you design a synthetic strategy for inorganic nanoparticle, taking inspiration from organic chemists? Since morning we have been hearing about the so-called retrosynthetic analogy. So if you take this molecule and if you draw some retrosynthesis, and I think he has shown this Martin's work in his list of references also, Professor K.R. Prasad. So what stuck my kind of imagination, or this one is, I was really to see this pyridine being kind of opened up and then use it in a molecule in such a fashion. It is really, really amazing how the organic chemist synthesis think. Whereas for us, to make this metal sulfide nanocrystals, if we were to draw, or if we were to do a retrosynthetic analogy, it's not so difficult for us. It's extremely easy compared to what the organic synthesis people do. So for us, a metal sulfide nanocrystal would have 3 components. It will have a metal, it will have sulfur, and what is called a capping agent or a protecting layer of an organic molecule. And again, this is how it is, right? So what we thought, or how we approach is that, is there a molecule or is there a class of molecules that contains all these 3 systems in it together, right? And our search ended in a class of molecules called metal thiolates. Metal thiolates were first made in 1935 and have been more or less forgotten after some time. So metal thiolates are layered compounds. There is a layer of metal ion capped by or attached to sulfur or thiol molecules on the top and bottom. And if you look at the X-ray diffraction, you will see a typical of a layered compound, only what are called 00L reflections. Like graphene or graphite is a layered compound, and you will only get 00L reflections when you do a X-ray diffraction pattern. So this is what is known about metal thiolates. And some have, for example, Professor Kulkarni from JNC have been looking at these molecules and they what to, how to use them for different kind of applications. What my student, Dr. Balanagulu, was interested in is this metal thiolates. One of the interesting property of them is you take these metal thiolates, add a little bit of solvent, and they become a clear solution, right? But what is there in this solution? Is the metal thiolate completely decomposing and becoming a metal 2-thiol molecule complex, it's individual molecular complex, or the sheets are delaminating and there are sheets floating in this particular solvent? So this is the question Balanagulu asked, and I don't want to really take you through, but believe me for today, because otherwise your lunch gets delayed, right? That what through a 2-dimensional X-ray diffraction and light scattering experiments, we proved that it is not a molecular complex that is present in the solvent. It is actually a sheet of molecules that are present floating in the solvent. Okay, so that we proved, and if that is the case, can we use these molecular sheets? And obviously, compared to Professor Kulkarni's work, we are now able to make a metal thiolate of many metals, right? I'll show you some more examples later. So using these molecules as molecular sheets, we could make metal sheets or metal sulfide sheets. by coating them on a substrate and heat treating them in an inert atmosphere or an oxygen atmosphere, we could convert them to metal sheets which are very thin, extremely thin metal sheets could be synthesized. And this thinness is proved by the transmission electron microscope images that are being shown apart from the powder X-ray diffraction. Again, like, for the lack of time, I don't want to go through all the details. But then this metal thiolates, now you can see it has a metal, it has a sulfur, it has an organic molecule layer. So can we use them as precursors to make metal sulfide nanocrystals? And this is where Abhijit Bera, next student, came in, and he indeed took this metal thiolate sheets in a solvent, dispersed and heated them. And indeed, you could get metal sulfide nanocrystals in one go, right? No more number of steps that I have shown previously. But is this good? The TM images, the transmission electron microscope images look good. But when you look at the optical properties, this is where I told you about the trap states. They are not so good. Ideally, you should be seeing only this peak in the emission. You don't want this broad peak. This was probably happening because the metal sulfur, the carbon sulfur bond is not so easy to cleave. And therefore, what is happening is in the nanocrystal literature, it is known, unless you separate the nucleation and growth, you will not get good quality nanocrystals. So maybe that is what is not happening here. So that's what the hypothesis is. So instead of metal thiolates, it slightly move to a new set of molecules. So using dithiocarbamates. Again, making them dithiocarbamates is not at all difficult. You have to simply add a primary amine to carbon disulfide, and you will not get a dithiocarbamate. You will basically get a salt of that, not a carbamic acid, but you will get a carbamate, an ammonium salt of that. So can this be used as a precursor to make lead sulfide nanocrystals? Again, you can see that lead oleate, this dithiocarbamate, and then oleolamine, and you can get directly nanocrystals. So I'll show you some examples. So this is how we did it. We can also tune, as you can see in Jonathan's work, they could tune the size of the particles. We could also tune the size of the particles, but not by changing the precursor, but by just changing the temperature at which the reaction was carried out. And obviously, you can see now that there are no two peaks. The emission is very sharp, and then you could tune the emission to different wavelengths at will. So what is exactly happening? This is where I will spend a couple of minutes. Otherwise, I don't have many slides. I'll close it quickly. So what is happening? So we are taking lead oleate, dithiocarbamate, and oleolamine. So what could be happening is that if you follow the green dots, the oleolamine and then this dithiocarbamate would be reacting, release the hydrogen sulfide and thiourea, which in turn will react with the lead oleate and lead to lead sulfide. And when we did some control experiments, we did find that just at oleolamine plus CaDTCA at 50 degrees centigrade is releasing the thiourea, but still the CaDTCA was intact to a large extent, even at 140 degrees centigrade. Whereas that's why we ruled out this possibility. The second part of possibility is that the lead oleate and then the CaDTCA are reacting, and this lead CaDTCA complex is self-decomposing. There is no necessity of the primary amine, and that is releasing the lead sulfide. Again, by doing some control experiments, we proved that self-decomposition does not happen at, even after 3 hours of heating at 90 degrees centigrade. So we ruled out that possibility also. The final possibility is that a light CaDTCA complex is forming, and to that, this oleolamine is attacking in an ascent-to fashion. Again, there is a literature precedence to that, and therefore there is an in situ formation of this lead CaDTCA complex, which is being attacked by the oleolamine, leading to these lead sulfide nanocrystals. And as I said, we could make different size nanoparticles, and not only lead sulfide. Lead sulfide is a test case, but we could make cadmium sulfide, manganese sulfide, zinc sulfide, copper sulfide, and we are extending this process to more complex systems, as I will show little later. And also good thing is that we are able to now make not 30 milligrams of materials, but 3.5 grams of materials. I think it is a good step. So of course, not the complete thing, but it's a good progress that we made. So the last three slides I will show about bimetallic sulfides like silver bismuth sulfide I have shown initially. So how to make that? For that, we wanted to make the mixed metal thiolate. when you wanted to make a mixed metal thiolate, there are two, three scenarios. So the scenarios are, when you want to make a mixed metal thiolate, it can form what is called a segregated stack. This metal thiolate one stack, this metal thiolate another stack. Or it could make a mixed stack. They like one metal thiolate, second metal thiolate, one metal thiolate, second metal thiolate. Like it's a mixed stack, alternating stack, AB type. The other one is both metals are present in each sheet. This is the ideal situation. We did not really design it. Again, I don't want to go through all the details, but we did not design, but very luckily, providentially, we got a metal thiolate where both metals are present in each sheet. So we made such metal thiolates, we characterized them. So we characterize them using extensive powder diffraction and powder X-ray diffraction and TEM also. Here I want to pay my homage to very bright students. Some of you who are from University of Hyderabad might know him. He is Professor Leela Srinivas Panchakarla from IIT Bombay. Unfortunately, at a very young age, he passed away. But he helped us doing this high resolution TEMs, which is very difficult on a soft material. So we could prove that indeed these materials have both metals on each sheet by doing this TEM. And using this now, we are able to make bimetallic sulfides using these mixed metal thiolates as a precursors. And these are very brightly emitting bimetallic sulfide nanocrystals. So these are just the proof that we have made all those things, and then some missing here. But the quantum yields are very good in these systems. So I think that's what I want to close. I hope I will not take more time that has been assigned to me. So we could develop some simple, generic, and scalable approaches for the metal sulfide nanocrystal synthesis, and also these are able to extend them to the preparation of biometallic systems. Finally, I would like to thank the students again. This is some mistake. These circles are not. These are not the people. This is the person who has made this work mostly, Abhijit Bera. And of course, he's not my student, but he's my guru, Professor T.P. Radhakrishnan. Thank you very much for your kind attention. Thank you, Professor Prasad. On behalf of organizing committee, I thank you. Please give big applause to Professor Prasad.
Thank you.
Thank you, sir. May I request you, Professor PMS Chauhan, to kindly present a memento to Professor Bhagwatullah L.V. Prasad, sir, as a token of gratitude. Dear participants, this information is for the poster presenters from serial number 1 to poster presenters number 60. So please fix their posters in the dedicated arena outside this auditorium.
May I also request Professor Ajay Srivastava, Professor Siddharth Sharma, and Professor Sandeep Murarka. So kindly they will be chairing the poster session, all the 3 poster sessions. So please help us to for evaluation of these poster sessions. Okay. Okay. Yeah.
Next speaker of this session, Professor Alkesh Visai, ISR Kolkata.
Pointer.
He is a recipient of several awards. CDRI Award 2022, Excellence in Drug Research, Silver Medal Award, Rasayan Sanstha, Bronze Medal Chemical Research Society, Serve Star Award, Star 2020. Title of the talk: the total synthesis of architecturally intriguing bioactive natural product via the naturally inspired oxidative strategies. Professor Visai.
Thank you, Professor Chauhan,
for the kind introduction. At the outset, I'd like to thank the organizer, particularly Dr. Satpal, as well as all organizing team. It's good to see that when country is celebrating Azadi Ka Mahotsav, and then, this institution, this university, which is established in 1947, is also completed 75 years of their existence. CRSI is going to complete 25 years next year. Thankful to ISCB for their association, and thank you for kind hospitality. So the question is why one should worry about natural product synthesis, and for this audience there is no need for introduction because you have already seen fabulous lecture by Professor Ganesh Pandey, Professor K.R. Prasad, Professor Vinod Singh, and many others. Already they talked about why asymmetric synthesis as well as natural product synthesis should be of highest priority. Then look at this slide. So if you look at this slide, so among 1562 marketed drugs, okay, so what they are, either they are biological macromolecule, unaltered natural product, directly natural product, botanical drugs, nature synthesize, natural product derivative, can have natural product diversification. Now synthetic drug, this S is actually this particular portion, okay, which is actually 27%. So if you look at except 27%, all are either natural product, nature inspired molecule, or what nature already make it. So what you see here, this 27%, today in 2016, it is 27%. Probably after 10 years, this will shrink. 10 years back, this was more. So basically what I'm trying to say here is that in order to have the drug discovery, natural product will have important role because the way nature actually participate and doing chemical reaction following principle of microscopic reversibility. So with that short background, this is one area where we have contributed MRDC alkaloid. Professor Ganesh Pandey has already shown very interesting synthesis of crenin type alkaloid, but this is also another type alkaloid where you can see that benzylic quaternary center is there, like in this particular position. So that we have synthesized very recently because this is marketed drug. Now, if you look at the future, some of the new isolated natural product has been isolated in 2021 is having again galantamine core, but they are also integrated with galanthindole core. So this clearly tells us how nature is utilizing integrating approach to make molecule, and therefore it is believed that this is the way forward for drug discovery program if you at all you want to synthesize a molecule of societal benefit, because the chairperson in my session already talked about 5 lakh molecules synthesized, 5 taken, out of 5, 2 goes to drug discovery program and 1 come out. So it's a vast area, but I think nature is the best guide to tell us what kind of molecule we should actually target for. So these are other natural products like the Wheaton type system, and these are again extended with another prenyl unit. So in this area we have also developed some of the strategies to make this kind of molecule. So these are other areas where we work on. These are basically L-tryptophan derived alkaloids, lysergic acid, clavin alkaloid. Now these are dimeric cyclotryptamine alkaloid. They can also rearrange. There could be many more which are coming from a diketopiperazine derived processes. So in today's talk, I will be mainly concentrating, half part will be concentrated like this way. So if you look at geamycin and oridamycin, they are nothing but diastereomeric relationship of each other, but there could be many oxidized version of this skeleton, leading to a number of congeners in this family of alkaloid. Now, these biological studies have already done, and you can see that these are having interesting bioprofile. And also recent study shows that this can be actually utilized for the in combating SARS-CoV. So which is very interesting. That is what is the inspiration we got. Not only that, they can dimerize to give ectopodiastereomer like this. These are natural product. And interestingly, this has been shown that these dimeric scaffolds are 10 times better active than their corresponding monomer. So there is another reason why one should worry about this molecule. Now, this kind of CN bond forming reaction lead to another pair of diastereomer, ectopodiastereomer. Now, there could be other type of CN bond forming reaction from this aromatic ring leading to another pair of ectopodiastereomer. So this clearly tells us what kind of strategy one should actually take in organic synthesis to develop something of societal benefit so that one can synthesize them and take it for biological studies. Not only that, moving ahead in this direction, you can see these two geomycins now separated by SO2 group. So this also tells us a lot of biosynthetic hypothesis, how nature is doing chemical reaction starting from cysteine or glutathione as a precursor, where this sulfur is transferring to this molecule. So chemical synthesis of these are not known. However, biological synthesis hypothesis said that it could be an in-center radical in carbazole. Now that can actually get stabilized in various aromatic ring, this para position and ortho position. Now they can combine, leading to digamycins T, E, F, G, C, A, B, and all. So now, as so far as sulfur digamycin concerned, so SO2 can actually incorporate in these two, in between these two radical, that leads to sulfur digamycins A, B, and C. So these are all, isolated molecule from nature, okay, or they have just, biosynthesis has been done, but chemical synthesis is yet to be synthesized because, you need to make more amount. That is where total synthesis of natural products come into the forefront in organic synthesis. So looking at this is the literature. If you look at Phil Barron in 2014 shown the synthesis of digamycin B, and Lee showed digamycin C, Mike Chris shown this natural product oridamycin, which is a diastereomer of geomycin. Then Sarpong showed unified approach to both these classes of alkaloid. So from our country, Professor Dethe from Kanpur also shown interesting approach, starting from Mr. Wellington, shown over here. So what Barron showed that if you take this molecule through electrochemical way, they can make this nitrogen-nitrogen bond, whereas they showed they can only synthesize this, not this. So this is where we ask a question, if these are ectopodiastereomer, why not, why can't we get both diastereomer? Of course, in this process, they could get an unnatural bromo derivative, which this is also very important in the context of its mechanism concern in electrochemical way to do the aromatic bromination. So this is our unified approach to this. So we thought this can be extrapolated to synthesis of this kind of alkaloid, and we started from here and we tried to do a delta CH bond functionalization reaction. So what we did with this, among all various delta position, we tried to functionalize over here with bromo so that we can do elimination and then utilize for natural product synthesis. So in practice, what we have seen, catalytic H2SO4 and acetic acid, we can actually isolate this, and when we took this, NVS can give this product. That clearly tells us it goes through this kind of intermediate, which has been characterized. So this is where the mechanism, once electron pooling is there, methyl can migrate, then generate a 3-degree carbocation, you can do elimination, now bromination, followed by 1-2 migration of methyl group leading to this kind of structure. Okay, and once it is done, then synthesis was rather very simple. We have done E2 elimination, allylic oxidation, hydrogenation, and then stereoselective reduction of this ketone, which lead to geomycin D. Now, from this geomycin D, what we did just chemoselective oxidation of benzylic alcohol in presence of secondary alcohol, leading to geomycin E. Now, upon saponification, it gave geomycin F. Further, a highly diastereoselective reduction leading to the synthesis of geomycin C. For digeomycins A, B, and C, we thought of utilizing a nature-inspired strategy where we can take this monomer and then do a single electron transfer mechanism leading to a formation of in-center radical. Now this N-center radical can actually get stabilized like this way. Now if you do NN bond formation, that is AB, if it is CN, that is what is diazomycin C. Towards this, we started exploring book wall chemistry, but what we have seen that book wall chemistry actually gave us mixture of product, where this CN bond formation gives us the product, but in addition, it would also give us, over oxidized product like this. So what we could see that upon prolonged, reaction condition of 18 hours, it can be completely converted to enone. So what we did then, we just did, protected the secondary alcohol. Therefore, we have both NH and OH is acetylated. Then we followed, book wall condition leading to this CN bond formation, and from there we make geomycin A methyl ester, which is a natural product, and we could make them more than 3.5 gram scale. And from there we have also synthesized geomycin A. Now from here, what we just utilize geomycin A monomer. We just did a orthogonal protection of this secondary alcohol with TMS, and then a copper catalyzed aerobic oxidation leading to NN bond formation. And then after the reaction is over, you just treat with K2CO3 and methanol. So therefore you can get diazomycins A, B, both atropodiastereomer, and this actually gives us the prove the nature hypothesis of forming NN bond forming reaction. So diazomycin A is the first total synthesis, B is the second one after filberon. So coming to other natural product like silazine dorfone, these are very interesting molecule. If you look at, these are having a lot of all carbon quaternary stereogenic center, various stereogenic center. So by looking at all these, this is isolated in 2018 till date, no synthesis reported, and these are having interesting bioprofile. So what we thought, can we have a unified strategy for making this kind of compound? By looking at this, one might think that it is cyclohexene, so therefore a pericyclic reaction could be explored in this regard. So what we thought, this diene as a homo and this this enone, dienone as a dienophile, we could able to do Diels-Holder reaction, right? Now, if you consider secondary orbital interaction, this would prefer for endo product. So out of all these four, we are asking this, and that is what should happen in principle. Now, if you think about normal demand Diels-Holder and normal demand Diels-Holder versus inverse demand Diels-Holder, the energy requirement says that a normal demand Diels-Holder is the operating pathway. Therefore, this as diene and this particular double bond as dienophile would give us the product. One might argue that why not an inverse demand Diels-Holder, where you take a diene which is electron poor and you take this particular double bond leading to the same product. However, if you look at the energy required for Diels-Holder versus inverse demand Diels-Holder, it is Diels-Holder which would actually give rise to the product, and that is what actually happened. So if you look at this electrosynthetic analysis, one can just do retro 4+2 leading to diene, and then you oxidize so that you get a dienophile like this. And what we thought, both can be synthesized from a common intermediate and which can be obtained from a polyene cyclization of this kind of epoxy alcohol, and which can be synthesizing utilizing literature procedure. We have made this compound, and from there we make this. In few steps, we have actually got our exocyclic double bond, and X-ray structure showed us the stereogenic center what is required for this molecule. So with this in hand, we did allylic oxidation. And this is what we showed why particularly it should give OH at the below position. The diastereomeric ratio is very high. And then we did a Rubottom type oxidation of this to functionalize, alpha position of this carbonyl. And we have seen this reaction can be done. Of course, a bit optimization is required. From there, what we did another Utic olefination. Ketone become double bond. Now, chromium oxide oxidation gave benzylic oxidation. Now, from TBAP treatment, we get this diene required for this synthesis, which was characterized from X-ray structure. And this is where most interesting thing happened. We tried to synthesize ketone from alcohol. But when reaction is over, what we could see is a new product. NMR was not of ketone, but it gives us something interesting. What is happening? Oxidize it, 50% of molecule is oxidizing and it is immediately reacting with this diene and disulfide is operating followed by oxidation leading to this product. Very interesting. So basically, as long as you get this ketone, it is establishing cutting hamid type condition where you have a ketone which is dienophile, is reacting with diene. Immediately you form and then you get the dual solder done. And in that way, whole molecule can be converted to this kind of compound, and which is very, very interesting. I think this is one of the rare example and that has been characterized through the X-ray. So now, as I said, there would be 4 different possibilities, and this is what exclusively forming. And reaction is very simple, student happy, guide happy, and we are actually in the process already submitted the manuscript for publication. So this is what exactly happening. A highly diastereo and regioselective dual solder reaction. So what we did another thing. We just convert this alcohol to do Mitsunobu conversion. We just converted this OH to the other diastereomer. And what we have seen again in the same condition, we could get the same product. And fantastic reaction. It's a spot to spot reaction. There is no other things are happening. So what we did basically, we took this compound where there is no ketone. We can do this. So expected product, but it is not isolated, immediately reacting, dual solder done, and then you get this product. Now, here is the problem coming. So we had to actually, differentiate these two carbonyl, enone and ketone. What we thought initially, we thought of doing mutual reduction condition to get allylic, this reduction done. However, it gives us a mixture of product which we are not able to, separate. And then what we did, we just had to protect this. And what we have found that this ketone can be selectively protected. And then with that in hand, we could actually do borohydride reduction, which give us perfect selectivity. Three, 4 minutes. So this is another alkaloid, natural products, tetracarbinoids. If you look at carbon, total number of carbon involved would be 40 carbon, and it leads to a lot of complexity. Now the other natural product like thianol, that's BCD, these are having little less complex because in the first one it is having more complexity because of 1, 2 plus 2. So we are not the first one. So there is one synthesis by Ang Lee for BCD. However, we thought, what about J? This is probably the most complex one in this family. So what we thought, this can be synthesized from a 2 plus 2, and which in principle can be synthesized from another dual solder reaction from these two partner, and both of these can be synthesized from actually thianoquinol E. And what we envision that these two partner can be synthesized from a common core, which is again AB10 core, and that can be extrapolated. So what we do here is that we use Coleridge well-established procedure, and we could synthesize this compound up to 91% of enhanced selectivity. I'm not going to discuss in details. Here you can see that hypercoagulation and all these things, no bond resonance play a very crucial role in this strategy. But what we did, we started from here and we converted to this. What we particularly did is cleavage of this aromatic ring. That was done by incorporation of one hydroxyl group. Aromatic ring become more electron rich. Therefore, ozonolysis can break this bond, leading to this kind of keto acid, and that was extrapolated to ketoaldehyde. And following 2 levels of utic olefination gives us this compound, and upon saponification we could make transoxic acid, which is also a natural product. So in other, what we did for the other partner, we again extrapolated this compound, and that was synthesized following a procedure reported by Brian Stolz in 2006, where aromatic ring can be functionalized and oxidized like this. Okay, with that in hand, what we did, we then form alpha diazo compound, and that was under heating gives us this compound. Now, in few step manipulation, we could actually synthesize this kind of secondary alcohol. So there are a lot of optimization is required. What I'm showing is the best result what we got, because this project actually started 4 years back. But here the interesting thing comes when we took this to unit. Now just under heating, one could actually able to get these two radioisomer. Those are not separable. However, interestingly, when we oxidize, we could able to separate them in column chromatography. And in fact, from here, we should able to complete thionyl adduct I and thionyl adduct H. So these are again natural products. So basically, what is happening? Two natural product combining, again another pair of natural product. Again, you take one, you do 2 + 2, and then get another one. So basically, unified approach. Therefore, once you reach to your simplest monomer, then it is actually nature-inspired strategy. Therefore, the chances of failure would be less. And where student happy, guide happy, I think this is win-win situation. And this is the last slide. What happened here is that once you have thionyl adduct I methyl ester in hand, and this is what we followed another pericyclic reaction, 2 + 2, because pericyclic reaction is the most sort of sustainable development if you talk. Which require either heat or light. And this is what exactly happened, what we wanted. After 4 + 2 done, we did a 2 + 2, leading to this particular compound, and which was again confirmed from X-ray crystallography. With this, what I like to conclude is that unified approach is very important. As Professor Ganesh Pandey showed, one particular intermediate, he can get a number of natural products. So unified approach. Development of nature-inspired methodology is very important. You start from simplest congener. First you synthesize, then extrapolate it. Okay, so that you can get a diverse number of natural products, and then you follow what nature is following. Of course, asymmetric catalysis is very, very important, very vital. As already, in the morning first talk by Professor Vinod Singh, already emphasized how important these are. Development of some CH functionalization also helps sometime to functionalize code, and nature-inspired pericyclic cascade like 4 + 2, followed by 2 + 2, gives us the complex structure of thionyl adduct J. So with that, I would like to thank all of you for your patience. But before that, let me thank directors of IISER Bhopal as well as IISER Kolkata, because some of the project already started at IISER Bhopal when I moved to IISER Kolkata. Thanks to all this funding agency for their generous support, particularly ACRB in the form of ACRB Star Award, as well as special call, MOES, ACRC. My first track was from ACRC, DAE, CSIR, and of course, all the students for whom I am here to explain some of our chemistry. Thank you very much.
Thank you, Professor Visay. On behalf of organizing committee, I thank you all. And I request you, please give big applause. Excellent. Yeah.
Thank you, sir. May I now request Professor P.M.S. Chauhan, chairperson of this session, to kindly present a memento as a token of gratitude to our invited speaker, Professor Alakesh Desai. Thank you, sir. Moving further, I request Professor Meenakshi Jain, Head of the Chemistry Department, University of Rajasthan, to kindly present a memento to the chairperson of this session, Professor P.M.S. Chauhan, for his kind cooperation and coordination. Thank you, sir. Thank you, ma'am. To take over the session further, may I request Professor Satpal Singh Batsra to carry over.
Yeah. So now we will be moving for lunch since already we are almost 1 hour delayed. So we will try to and done with our lunch by 2:40. And then there is slight chance that we have a tea break. Earlier we had a tea break of 35 minutes. So we will be managing with it 10 minutes. So that's what we will try to manage. I humbly request for your kind cooperation. Thank you. So we'll be back here by 2:40. Thank you.
I request the presenters of the next session to kindly submit on the stage to Dr. Praditi Pagaria. Once again, I request the presenters of the next speakers of the next session to kindly submit the PPTs to Dr. Praditi Pagaria.
Oh, 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 oh. Oh, 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 closer to you, further from me, getting lost in between. Just take everything you need. I'll be getting lost in between. Close me, just get lost in me. Just get oh, 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 just get lost in me. Oh, just get oh, oh, closer to you, further from me, getting lost in between. Just take everything you need. I'll be getting lost in between. Just, just oh, 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 just, just oh, oh. Just, just, oh, just, oh, oh.
जिसको जो पढ़ना है वो पढ़ सकता है। मेरे को 5 बजे एक और मीटिंग में जाने का है।
जी जी सर।
Ladies and gentlemen, if you can hear me outside this hall, please come back and join us for the next session. Dear participants, please come back and join us for the next session. May I request you all, we are already running late. Please come back and join us for the next session. May I request you all to please be back for the next session.
वॉइस जा रही है पीछे राकेश जी जा रही है
I also request the leader of this conference, Dr. Satpal Singh Batsara, to please reach to the stage. Dr. Satpal Singh Batsara, if you can hear me, you are required on the stage.
Hello.
Good afternoon.
Ladies and gentlemen, we have with us retired Professor, Head and Dean of Chemistry Department, Central University of Rajasthan, Professor R.T. Pardesani. He will be the chairperson of this session. May I request him to please coordinate this session, take this session further.
Oh yeah. Thank you, Dr. Sharma. I'm Professor Sahu. Will you come and speak? Not yet. Okay. So we have a distinguished list of speakers in this session, third session of the day, and we are looking forward to a very exciting chemistry. And the first speaker of this afternoon is a very distinguished professor, Lutz Ackermann from August University, Göttingen, and he has interest in the areas of catalysis, CH activation, as well as electrochemistry. And he's honored with Lidnick Prize as well as Orchem Prize. So welcome, Professor Ackermann, to this afternoon in India, and I hope it's very pleasant in Germany. And we look forward to he is going to talk about today on what is the topic? Can I see his topic?
Yeah.
Okay. So he is going to speak today on metanoelectrocatalyzed bond activations. Okay.
Fantastic. Thank you very much. Can you hear me actually?
Yes, it is loud and clear, sir.
Excellent. Thank you very much. Thank you for the kind introduction. Thank you very much to the organizers for giving me the opportunity. I'm very sorry that for different reasons I cannot be present. Göttingen is nice, but it's gray and cold, and I miss to be in India, not only for the nice environment, but also for the beautiful people, for the nice food and the culture. And so I'm very sorry that I cannot be present there today, but I hope we can have many interactions. Also, congratulations to the organizers for what I've seen this morning. That is already an excellent project, excellent conference. So without further ado, we can controversially discuss if there's an energy crisis, but what we cannot controversially discuss that recent trends have shown that there's a drive towards using sustainable forms of energy. And that could be particularly a green hydrogen economy that could use renewable forms of energy, such as wind and solar energy, which is easily available, of course, also in India and in Germany. We would like to contribute to this, to a decentralized hydrogen economy, also to use it for chemical feedstocks. To do so, we engage in understanding how energy is converted from one form into another, how this can be more efficient, so how we can minimize energy dissipation. And we would like to merge this with electrocatalysis. So that would lead to organic synthesis with potential, or electrifying organic or molecular synthesis, as you wish. Now, there are different aspects why this can be important, one of which is cost of goods. If you, this is a little bit small probably, but basically on the right is electricity, on up to the left is different chemical redox agents, oxidants, finishing here with hypervalent iodine, so PFA or silver 1 salt. So they are very costly. Same holds true for reductants. And basically, in terms of renewable forms of energy, they could be almost for free. Investment cost, but otherwise you could use sunlight and wind. I should mention there's a long history of electrochemistry, starting from the recognition of electricity, Volta, Galvani, Faraday, Kolbe. The Kolbe reaction is the this decarboxylative dimerization, and there are many new forms of this, which, for example, Kevin Lamb is studying. But we are very fascinated. Professor Kolbe was actually a student at the University of Göttingen. He started his career here. There are many important contributions throughout the years. Just a few names are listed here. But what we wanted really to do is merge it with 2 times CH activation in a dehydrogenated fashion, so that we provide means how to do a CH activation without chemical waste, but just delivering hydrogen. So this was our goal. And as has been kindly mentioned, so we have a long-standing interest for more than 20 years in CH activation reactions. Many groups have contributed to this area, so just I would like to highlight maybe some recent references where this has been broadly summarized. Also, of course, Professor Zahu, who's, I guess, in the audience and whom I've seen this morning. So congratulations to your work, has also contributed very nicely to this field. So we would like to contribute to late-stage functionalization, medicinal chemistry, but in this case, merge it with electrochemistry. And we coined the name metalloelectrocatalysis because it combines electron catalysis, as defined by Amido Studer and D.P. Curran, with metal catalysis. And that would allow us to go from reactions that are controlled by bond dissociation energy to reactions where we can leave strong bonds. Now, this sounds very simple. There are many obstacles in the ways, one of which is controlling the overpotential at the cathode. Therefore, sometimes you need some divided cells, but the same holds true for controlling the anodic oxidation of a metal catalyst, for example, such a ruthenium zero complex, to reoxidize it to the catalytically relevant ruthenium bis carboxylates. It's a simplified picture because here you typically have the electrical bilayer, which could be described as the Helmholtz layer. And how the protons and electrons are moving and the catalysts are moving through this is still a very hot topic in my opinion. So in this regard, we studied these ruthenium zero complexes. We isolated them in 2015 for some CH activation reactions, and we could show that you can see the reoxidation to the ruthenium 2 catalyst, and that there's indeed a sort of enhanced shift depending on the addition of this carboxylic acid. That allowed us throughout the years, and also others, so Haichao Xu and others joined this field of metalloelectrocatalysis. I won't lay Haichao Xu, so particularly early days in China, but also very nice work from India and other countries to do these catalytic reactions where we have a ruthenium catalyst. So maybe let me guide you through. It's an interdisciplinary audience as far as I understand. So we have a non-divided cell, so we don't need a special membrane. We don't have a problem of overpotential control if we have a platinum cathode. We have a high surface area carbon-based anode. And importantly, so for this electrochemistry, we don't need any specific supporting electrolyte. So the sodium pivalate, which I showed you before, we can use both to adjust the conductivity, but also to regenerate this ruthenium bis carboxylate complex. It tolerates a variety of different functional groups. So in this case, we start with a benzoic acid and we get these cyclic lactones. You can have a bromide or chloride and ester. But more importantly, these reactions actually preferentially occur in an aqueous media. So a protic solution is particularly good for these electrochemical reactions to adjust the conductivity. Now, conceptually, the catalytic cycle we have studied before for chemical oxidants, but conceptually we reoxidize the ruthenium catalyst, so probably a ruthenium 0 to ruthenium 2. And we couple it with what you would call a PCT, or better multi-site CPET, in which the proton reduction, so the hydrogen evolution reaction, occurs at the cathode. We love ruthenium for a long time. We're interested in ruthenium CH activation, but we also feel obliged to study the use of rhodium catalyst, iridium catalyst for CH activation, and even in more recent times, osmium catalyzed electrochemical CH activation. Let me just give you highlights of what this can serve for different communities. For example, in terms of material science, you can use this approach to combine metalloelectrocatalysis with an electrochemical Scholl oxidation. The first reaction occurs with high Rieger selectivities in terms of the addition of these alkynes. This can be explained by NCI plots or non-covalent interactions, basically by computation. But then you can take these molecules and appreciate the chemoselectivity of the electrochemical synthesis versus copper-2 or silver-1 oxidants. And then particularly for this highly sensitive, otherwise sensitive iodo-arrow-boronic acid, where the iodo-arene is remaining untouched. Now we can take these molecules with these 4 aromatic groups and make polyaromatic hydrocarbons. by a DDQ catalyzed Scholl reaction. So you can see here, you can make these polyaromatic hydrocarbons for materials applications. You can have an iodide here, you can have an ester here for further manipulation. And you see that these show a deviation from planarity. And recently we summarized sort of the field of electrochemical synthesis of PAH compounds in advanced materials. You can also do a triple alkyne annulation, as you can see here. We can by mechanistic studies find out which alkyne inserts at which position. It's already again so it tolerates the chloro, bromo, and iodo and ester. You can have 6 OH groups if you want to, or Nobel Prize winning click reaction. Of course, you can do electrochemical CH activation in the presence of a protic solvent. Potassium acetate is the only supporting additive, and you can tolerate these 6 azido groups. So there's no side reaction between the azide and the alkyne, for example. So you can use this, for example, for dendrimer synthesis. Well, if you want to have a scalable process, probably you would do it by flow. And therefore, we engaged into flow rhoda electrocatalysis or metalla electrocatalysis. And this is shown here. So it's again an alkyne functionalization. We use this commercially available cell to improve mass and heat transfer. We modified it with a 3D printed implement, and this allows both inter and intramolecular reactions. Now, as I said, so you can, for flow chemistry, you can improve heat and mass transfer, so more efficient catalysis. But what is also important, you can do online and in operando studies. So we could isolate these cyclometylated rhodium complexes. So these are the 5-membered metallocycle. And here we have the 7-membered metallocycle after alkyne insertion. So here the alkyne with the one substituent, with the other substituent. This was isolated, and this, in addition to experiments with and without current, online monitoring and the dependence on the current, the formation of this 7-membered rhoda cycle, and cyclovoltammetry was speaking in favor of that this rhodium-3 species undergoes additional oxidation. So an oxidation-induced reductive elimination. And this is what we see is of relevance also to the CC cleavage reactions, which we have a long-standing interest in, also within some collaboration with our friend Ilan Marek in former times. We arrived at a system where you can do CC activation by metalla electrochemistry. So it's not only CH activation, but also CC activation. The mechanism can be as complex as you wish, but the key feature is also that here, basically, the sacrificial oxidant is the hydrogen evolution reaction. So protons and electrons, and hydrogen is the only stoichiometric byproduct. And by using this approach, you can make these 1, 2, 3 tri-substituted arenes. So this was our move actually from sort of ruthenium to rhodium, and as I said, also osmium and iridium. But if you take a look at the prices, they are changing, and these are some older numbers from our review from 4 years ago. And we and many other people, of course, also in India, very nice contributions to cobalt, particularly chemistry, have been interested in moving to less expensive, if you want, less endangered, but for particularly also for less toxic metals. And that is important. If you see here, so these are the GSK trace metal allowance for metal impurities. We have our own ICP-MS at hand. And here you see that ruthenium, rhodium, iridium, osmium, palladium, gold would be in the range of 10 ppm. If you have a silver oxidant or a silver catalyst, actually, this is still 15 ppm. And so you would need to have at least a distillation step in the final step before you could administer the drug to a patient, a human being. There is, of course, difference if you move to these benign catalysts. Well, I will focus today largely on cobalt, maybe one example from manganese, because that actually predates the work on ruthenium and rhodium that I've shared with you before today. Cobalt is relatively inexpensive, and as a proof of concept, we could show that you can use a cobalt catalyst. Now, this has actually, I think this paper has inspired a number of people, as we see in the literature. So let me explain this a little bit. In the first study, we used again a high surface area, a carbon-based electrode and a platinum cathode. The system is obviously, it's a CH to CO bond transformation, so it's fully tolerant of protic solvents. We don't have a special electrolyte, so there are no costs by some special BF4 or PF6 salts. We can do these reactions in a divided cell or undivided cell. So in the first paper, we have one example, the gram scale reaction, which we did in undivided cell. Otherwise, we were very cautious to do it under divided cell conditions, which at the end is actually not required. So this is a CH oxygenation, which works on arenes. It also works on olefins, and I should mention that Jiangshang Mei has had later some nice work on rhodium and iridium catalyst also for olefin functionalization in JACS published. But this was a sort of a proof of concept that cobalt could be compatible with this metallo-electrocatalysis for CH activation. And for the experts in the audience, it's notable that we don't need a specific CP star catalyst, CP star cobalt, but simple cobalt acetate is sufficient. And we've seen this also later in the work of many other groups, including Ai-Wen Lei, Bingfeng Xie, and other people who have used this system for their own purpose. The goal was to combine it with renewable forms of energy, and we'll come back to that later if you're interested in how we do this. So we wrote this nature protocols to compare the home setup system with commercially available ICA system, so they can find all the information of the different electrodes and how they work. It's pretty much comparable. And the first catalytic cycle was proposed as such that we have a cobalt-3, cobalt-1 cycle, and the cobalt-1 would be re-oxidized to cobalt-3. That was the first proposal. And again, the cathodic side this cathodic sacrificial reaction would be hydrogen evolution reaction. You can store the hydrogen, you can do hydrogenation reactions, you could potentially use this as an energy carrier. Now, this is for CO bond formation. We were also engaged in CN bond formation. And here we used biomass-derived solvent, GVL, gamma-valerolactone. We did some in-operando react IR studies, and this was also around the time when Ai-Wen Lei joined the field of this type of research. As we can see, we can also make CC bonds, alkyne annulations. For instance, here we chose to use this hydrazide because actually you can do an electrocatalytic removal of the hydrazide. So we combine an electrooxidation and electro removal. And interestingly, it even works with simple acetylene. So it tolerates a variety of functional groups, a nitrile, an iodide, and so on. But you can also have a triphasic system where you have the solid electrode, the homogeneous catalyst, and the gaseous. Well, what is this? Excuse me, can you still see the slide? Let me check. Okay, I will just continue, probably. So for this alkyne annulation, you can still hear and see me? I think so. We could propose a catalytic cycle in which we have a cobalt-1, which is re-oxidized to cobalt-3, and we have the hydrogen evolution reaction. And just to give you one idea on how we do this reaction. Okay, now I can see myself again. Perfect. Let's see. So here we have the alkyne annulation. Sorry, we studied this by high resolution mass spectrometry, by computation, as well as DFT. Now let me just check that actually I'm still sharing. Because I understood. Okay. Yeah. So these are the tools we used, and we can do DFT to study the dispersion effects. Well, this cobalt chemistry actually turned out we can use it for CO bond formation, CN bond formation, CC bond formation, also with carbon monoxide. And so we studied in more detail the mechanism. We took a closer look at each step. So we went through the catalytic cycle in a stoichiometric fashion, if you want. So this is now coordination chemistry. This is electrochemical inorganic chemistry, if you want. And so we take the cobalt acetate, we mix it with the substrate, and we can isolate this cobalt-3 complex. This is an X-ray structure, so it's an octahedral cobalt-3, which shows by cyclovoltammetry evidence for cobalt-3, cobalt-4 oxidation. And there has been some beautiful work also in this area, of course, of cobalt, CP cobalt-3 chemistry, by our good friend Baska and Deb Mighty, of course. So this speaks for oxidation-induced reductive elimination manifold. Okay, maybe in the interest of time, I would just briefly mention that we also studied some manganese catalysts for metalloHAT. You can do azidation reactions without any directing group. But what I would like to focus here is that the mechanism is similar. You have a manganese 3,4 oxidation, and you can do late-stage functionalization without directing groups by this approach. But on the last few slides, I would like to talk about selectivity, because this is our recent interest. We try to merge it with machine learning to have full selectivity control. So these are a few papers on this topic, but more importantly, we were able to introduce the transient directing groups pioneered by Roithoff and Sokolov for palladium catalyzed asymmetric electrocatalysis. Now here we have atroposelective reactions, olefination reactions. Third leucine is the only sort of ingredient which forms the imine. We can do CC axial chirality, NC axial chirality with reasonably high yields and very high enhancer selectivity. So this was a proof of concept that this electrochemistry, metal catalyzed electrochemistry, can be merged with enhancer selectivity. Yeah, you can do allylation reactions. You can actually use the formed hydrogen for hydrogenation reactions in a paired electrolysis, and you can use a solar panel to drive these reactions completely. Now, the goal was not to stay here with palladium or also some rhodium chemistry, but if we can actually use cobalt for this purpose. So in 2017 and 2018, we were interested in developing asymmetric cobalt-3 catalyzed CH activations. There was some earlier work from Yoshikai on low valence systems, but for Grignard-free systems, we were pleased that indeed we could devise different kind of either amino acid derivatives with lower EE or these C2 symmetric acids to do redox neutral addition reactions, but with cobalt-3 in enhancer selective fashion. You see here also this is the typical CP cobalt system. And this has actually led to a number of important discoveries. So we reported this in 2017, 2018, later Matsunaga reported this amino acid derivative. Nikolai Kramer used the Haltermann type, so his nice approach to chiral CP stars, and Bingfeng Shi, he developed a few other chiral acids, Salox based or these kind of acids. Based on our findings from 2017, 2018, we're actually pleased to find that we can merge this asymmetric cobalt catalysis, but now with CP star free system, to do different kinds of enhancer selective metallo-electrocatalytic reactions. Interestingly, here this simple vinyl derived phosphoric acid, which was much better than this spiro species, We did some mechanistic studies, which again was in favor of oxidation-induced reductive elimination from cobalt-3 to cobalt-4. And this proved to be broadly applicable. So here we have a spiral cycle that is built up by this relatively inexpensive chiral acid. We can do these annulation reactions, and I should also mention that we developed 6 of these type of reactions, and very quickly after our developments of cobalt catalyzed electrochemistry and asymmetric versions, and other groups in China further developed this kind of system. But what Tristan, and as a first co-star, co-first author, Suman did, so very talented Suman Dana, very talented postdoctoral co-worker, they developed 6 of these reactions. So therefore it took us longer time. We didn't want to publish 1 or 2 reactions, as you've seen in this previous contribution, but we developed 6 first in isoselective electrochemical transformations. So conceptually, we can therefore use earth-abundant cobalt for an isoselective electrochemistry, and the only byproduct here is hydrogen evolution reaction. This is scalable, so Suman and Tristan showed that these reactions can be done in more than 10 gram scale. And we could also do these reactions as we did previously in these papers here, in this ChemSys paper. We used a solar panel, which is shown here, to drive these reactions. Okay, therefore I would like to close. I'm sorry for the technical interruption, I guess. But we compare favorably, I think, this field of electrocatalysis with the photoredox, because we can dial in the potential we would like to have. They have their own benefit, of course. Photoredox catalysis is very important. And today I talked about the use of 3D metals, a little bit biomass-derived solvent, GVL, on one project. We developed flow conditions for the electrochemistry. I didn't talk about the meta-selective transformation or the para-selective transformation, which we have enabled by electricity, but about a little bit late-stage diversification and enhancer selectivity. In addition to just contributing to renewable energy usage, we also uncovered a novel reactivity manifolds. With this being said, I would like to thank my co-workers for their dedicated contributions, for their intellectual input to all of these. Without them, I would not be able to talk about anything here. I would like to thank these funding agencies as well as our collaboration partners. We love international collaborations, and we love to see that other people are actually using this type of electrochemistry for their own purpose. And again, I'm very sorry that I cannot be with you in India. I would love to, for many good reasons, to meet, of course, old friends and to make new ones. I have always enjoyed to travel to India, and I hope I will be able to do so soon again. So thank you very much for listening, for your attention, for inviting me, and all the best wishes from Göttingen.
Thank you very much, Professor Ackermann. We also missed you at Jaipur, sir, and I hope there will be another opportunity to see you here.
For sure, yes.
We can have 1 or 2 questions.
Yes, of course, for me.
So the session is now open for the questions. Any, please? Okay.
Thank you, sir. And accept our sincere gratitude for sparing your valuable time with us. And so we may have for the second.
So we thank Professor Ackermann for a very fantastic lecture on CH activation and electrochemical hydrogen evolution. And we hope we will meet in India some other time. Thank you again.
Thank you very much. Thank you. I hope so too.
Next, radio. So I welcome all the audiences into in the auditorium. We started this new Journal of Chemistry session with the lecturer Professor Ackermann. And continuing, the next speaker, our next plenary lecture is by Professor Vincent Gendon. He obtained his PhD in 2002 from University of Reims in Paris, in France. And then he went on to pursue the postdoctoral research at University of California in Riverside. But he came back to join University of Pierre at Madame Curie in Paris in 2003 and became full professor at Paris Sud University in 2009. His research interests are development of homogeneous catalysis for organic chemistry. And I think he's today going to speak on recent developments of Lewis acid catalysis, applications of gallium, lithium, and calcium in CN bond formation. Professor Genon, please.
Well, thank you very much. Can you hear me well?
Yes, loud and
okay, good. Great. So just like Lutz, I'd like to apologize for not being here and to thank you very much for the honor that you do me in organizing this virtual talk. I have enjoyed Jaipur in 2019. It would have been a thrill to come back, but unfortunately I am stuck here. And anyway, so I am located here in Orsay, so it's 30 kilometers south of Paris. The difference between the last time I came is that we have moved to a new building, which is named after Henri Moissan. He is the first French chemist to receive the Nobel Prize in 1906 for the discovery of fluorine and other things. And down there in this building, we still care about the development of new synthetic methodologies, fueling that with computations and coordination chemistry. We care about metal catalysis in the broad sense of the word. So in fact, regarding computations, our interests span from biology with copper signaling pathways to total synthesis by trying to rationalize the stereoselectivity, for instance, with organolithium reagents. And of course, on metal catalyzed reactions, especially in collaboration with Professor Sahu from Hyderabad. He delivered a talk in the early afternoon, so I will not talk about what we have done together, and I will focus on our modest contribution to organic synthesis. So let me come back 10 years ago. We have been interested at that time to develop new practical procedures in gold catalysis. So it's a project that refers to pi acid catalysis, the activation of CC pi bonds, alkenes, allenes, alkynes towards nucleophilic attack. And the thing is that when you do such reactions, you use a gold chloride and a ligand. Usually, people tend to use silver salts to generate the active cationic species, but this cationic species is relatively fragile. It undergoes redox process that leads to gold zero nanoparticles or a gold mirror. And so we have demonstrated that by using copper salts instead of silver salts, then this problem is solved and you can really lower the amount of gold in processes like hydroarylation or cycloisomerization reactions. And the second way we worked on to make this pi acid catalysis more practical was to get rid of gold and to focus on another element that would be redox silent, that would not undergo such decomposition. And so we focused on gallium. Of course, with gold, you can, thanks to the d orbitals, stabilize classical intermediates in cycloisomerization chemistry like non-classical carbocation. We don't have the same thing with gallium. The d orbitals are not available, but we have a specific geometry and the chlorine ligand are still there. And so they can participate to the stabilization of the intermediates and give rise to similar products. So by using either gallium trichloride or our own catalyst, displaying here an NHC ligand and 2-chlorine and an SBF6 moiety, we were able to do some pi acid catalysis as well. and imitate, for instance, reactions that were specific of gold chemistry. Yet, gallium is a very oxophilic element, so we have also some incompatibility issues compared to gold, like some protecting groups like acetals are not compatible and will be cleaved. And never mind, sometimes we have found reactions that we have worthy of being developed nonetheless, like the cleavage of these esters here to generate the corresponding carbocation, which can be trapped by an arene to lead ultimately to beta-aryl aldehydes. And this reaction has a name, it's a scriabine reaction. We have developed the first catalytic version of this reaction. It's an important reaction for the perfume industry. We have also found, and this is something I'm going to develop, that carbon sp2 bromine bond in bromoaldehydes can be cleaved and give rise to CH propagylation products. The problem of gallium species is that they are usually not compatible with the presence of free alcohols or amines. So for reactions like this with alcohols and amines, we are focused on calcium or lithium complexes to develop new approaches towards heterocycles. And this is something I already presented during my lecture tour in India, but I'm going to show you some new applications in this regard in the field of the Haza-Payanketeli reaction. But the story of gallium finally met isofluoroisopropanol as a solvent, which is a quite trendy solvent nowadays. And we found that the association of calcium Lewis acid and HFIP is actually able to activate pi bonds as well, to make cycloisomerization reactions, or even more simple hydrofunctionalization reactions of alkenes. And what I presented in 2019 was that we can work with styrene derivatives that are electron poor, which was completely new to the field. And I'm going to show you that we have pushed a little bit this chemistry further. So let's start with gallium. This is the kind of reaction we have developed recently. It's a cascade that involved first the activation of an oxygen group. So it's sigma Lewis acid catalysis, and then the activation of a pi bond. So gallium is just perfect for that because it is really at the border between sigma and pi Lewis acid catalysis. The first step is the carbonyl olefin metathesis. Corinna Schindler has worked a lot on that, and she has showed that iron trichloride is an excellent catalyst for such transformation. But if we couple that with the activation of a pi bond, then it's not the perfect catalyst. The perfect one is gallium, especially our catalyst here. And the second step is the transfer hydrogenation from cyclohexadiene. So it's typically something you can imagine, for instance, with ruthenium catalyst, starting from a diene, making a olefin metathesis, and then an hydrogenation or a transfer hydrogenation. But we do that in the absolute absence of transition metals. So this is a kind of substrate we can use, acyclic or cyclic ketones like this, and we get the 1,2-cis cyclopentane working either in 1,2-DC or HFIP, and we get a pretty decent scope for these compounds that are obtained as single diastereoisomers, so 1,2-cis. We can also work with gem diester groups here and obtain either 5-membered or 6-membered rings under the same conditions. So it's a pretty good scope. And for the mechanism of this transformation, when we have an ester group here, so we activate the 2-oxygen and we have this Lewis acid here. What we have found by computations is that 1 Lewis acid is not enough to make this activation. And this is also consistent with the work of Corinna Schindler on the fact that a second Lewis acid is sometimes necessary to activate the first one to give rise to a super electrophilic homodimer. And once you have this super electrophilic activation, then you can trigger the addition of the double bond and in a 2-step fashion make this oxetane, and then in a second 2-step fashion, the elimination of acetone here to give the carbonyl olefin metathesis product. Then there is an exchange between acetone and cyclohexadiene. The activation of cyclohexadiene is necessary to make it acidic enough to give a proton. And then a hydride is transferred on the less hindered face, hence the 1-to-cis stereoselectivity that is observed. When we are working with Lewis acids such as gallium, there's always a question that remains, which is it really metallocatalyzed, or perhaps is it protocatalyzed? It is true that with very electrophilic species like this, you can imagine many ways to generate branched acids, like the activation of a water molecule or the activation of the solvents. All this is well known. And what people tend to do to discard or confirm the possibility of protocatalysis is to use, for instance, ditertiobutylpyridine, which is supposed to catch only protons and no metals. But the problem with gallium catalysis is that, in fact, you can form an out-of-plane sigma complex between ditertiobutylpyridine and gallium. This has been shown by our friend and colleague Ingo Crossing from Freiburg. And so this test is irrelevant when you do gallium chemistry. So what we have done here is to use bromoaline. We have reported in 2018 a method to do them, a new method. We have reacted them with arenes using gallium trichloride. And that gives this hydroarylation product. And in fact, this step is really protocatalyzed. If we use no base, this is what we get. If we use ditertiobutylpyridine, we have no reaction at all. But we have found that, in fact, potassium carbonate is compatible with this reaction. It switches off the protocatalysis and gives rise to a completely different product, which is a CH propargylation product. And such propargylation are usually not easy to make with allenes. They tend to give the allene substitution. And the only method we could find, which is the same as that one, is the one described by Frank Glorious. He has reacted bromoalines with compounds like this. So we have a directing group here, and the reaction is catalyzed by manganese, and it works only on heteroarenes such as indoles or pyrols. So our method is really complementary to the one described by Frank Glorious and has a different regioselectivity, as going to show you. This is what we can do. So with gallium and potassium carbonate, so we have to use relatively electron-rich arenes to capture the cationic intermediate, but the scope is quite nice. We can work with heteroarenes such as indole, but in this case, the regioselectivity is different from that observed with the directing group. And if you look at this regioselectivity compared to the pyrrole, we can understand that we are in a typical Friedel-Crafts regime here. So, of course, on the allene, we can also make some different substitution patterns like arenes, alkyl groups, and various groups also at this position have been used. Just one word about the mechanism. So we've studied it by many ways: kinetics, conductometry, DFT computations. I'd just like to highlight the results obtained by gallium-71 NMR. So the gallium NMR of gallium trichloride is a broad peak at 220 ppm. It's a quadrupolar moment that makes these peaks broad. It's normal when the symmetry is quite low. And if we had potassium carbonate, there's no change. But if we had now substrate, the bromoaline, then we see sharp peaks. And these 5 sharp peaks correspond to these high symmetry tetrahedral anions with a shuffling between the chlorides and the bromides. So we have all the 5 possibilities of an ion here, which is diagnostic of the abstraction of the bromine group. So we really believe that we are activating the carbon sp2 bromine bond here. And the possibility of abstracting a halide or a triflet on a carbon sp2 on an sp2 carbon led us to turn our attention to vinyl carbocations. The question was, can we generate such cations? Vinyl carbocations have been described a long time ago, and in fact, Peter Stang and Anderson reported in '77 that if you just boil vinyl triflate and an arene, you get the coupling product. There's no need of palladium here. It just works like this, but the reaction works at elevated temperature, for a long time. The scope is very low, and it works by solvolysis of this bond. In 2018, Osea Nelson reported a catalytic version of this reaction using a Lewis acid. The trick is to make this reactive, more reactive. In fact, Herbert Meyer has coined these cations as sluggish electrophiles. They are not very reactive unless the counter ion is a weakly coordinating counter ion. So it's a carborane in the work of Osea Nelson. Since there is a silane used here, so it's not exactly the coupling product that is obtained, but the reduced version. Okay, so on our side, we have again worked with a salt reported by Ingo Crossing, which is very easy to make on a multigram scale. It's lithium aluminum hydride, and you mix it with the corresponding alcohol here. So it's a perfluoroterbutanol, and you get that compound. And you can use it as a catalyst to get the coupling product between arenes and vinyl triphlates. The counter ion is very weakly coordinating. It's an aluminate, so it's a ball surrounded by a lot of fluorine atoms. So, and we have a base, lithium hexamethyl disilazate. The scope is quite nice, so we can work with a variety of R groups here or there. So we can work with cyclic compounds. We can make some analogs of isochondrostatin. These compounds have nice biological properties, so we made several of them, like with electron donating groups. And so it's a method that has an interesting scope. And we can change a nucleophile. The arene can be replaced by, for instance, a difluoroenoxysilane under the same condition, except that this time we need a ligand, which is a squaramide. We can make such difluoroskipped enones. And again, thanks to this tamed vinyl carbocation with weakly coordinating an ion, get a nice scope for these transformations. Now, I'd like to switch to calcium, just to give you some brief information about what has been new in our lab. Since 2010, the azaperencateli reaction has been described by Javier Real-Delanis from UC Santa Barbara. It's the condensation of furyl carbinol and aniline to give aminocyclopentanone with a trans-stereoselectivity, because in the mechanism we have 4-pi electrocyclization of one of the intermediates. Delanis has used dysprosium triflate to make this reaction, and on our side we have worked with calcium triflimide, which has shown a very large scope, and we have coupled this reaction with in a cascade fashion to make heterocycles. The last type of reaction we have reported in this area is from such furyl carbinols here and anilines using the calcium catalyzed approach. We make the corresponding aminocyclopentanone with the trans-stereoselectivity, and then we had triphenylamine in the second step to make the bridge here where you still have the trans-stereoselectivity. So we make tetrahydrobenzo-B-azepine in a stereoselective fashion. This reaction has a very broad scope. We've made like 60 compounds like that. We can work with aniline that are para-substituted or meta or ortho-substituted. We can work with secondary anilines. We can work with hydroxylamines. It's possible to have quaternary centers. We can modify here the heteroatom for an oxygen and get tetrahydrobenzo-B-oxepine. It's a really faithful reaction. The possibility of introducing hydroxylamine is interesting because we can cleave the bonds here by hydrogenolysis and get the NH2. So we somehow mimic the reaction with ammonia, which is not possible under the catalytic conditions. Still with calcium, as I said in my introduction, when we use such Lewis acid in hexafluoroisopropanol, then it becomes possible to activate styrenes displaying electron withdrawing groups. For instance, to make diaryl methanes, which was not described before because such styrenes tend to be completely unreactive under Lewis acid conditions. And we could nonetheless make react a variety of arenes to styrenes displaying like 4-fluorine CF3 groups. And this is something I already presented when I came to Jaipur in 2019. The new thing is that we have used this strategy to functionalize anilines. So it requires a higher temperature, but this reaction works with a very broad scope of, let's say, any kind of alkene. But in particular, it's still possible to use electron-poor styrenes and to make this variety of compounds with ortho CF3, meta CF3, 2 CF3 groups, 4-fluorine, cyano esters. A lot of different electron withdrawing groups have been used, and they are all compatible with this strategy, which allows to make industrially relevant anilines, because such compounds are used as dyes or antioxidants. Okay, so in summary, so this is the new things we've made with gallium. Gallium remains one of the best catalysts when you are at the border between sigma and pi acid catalysis. We have found interesting conditions to avoid protocatalysis, which triggers new research areas in the group, especially regarding CH functionalization. With lithium, we have played with vinyl tripletes that are reactive toward arenes or difluoroinoxysilanes. And with calcium, we've pushed a bit the boundaries of this chemistry by reporting new complex heterocycles or new reactions involving the functionalization of previously unreactive substrates. All right, so I'd like to thank the organizers once again for organizing this remote talk. I'm especially thankful to Professor Sahu, with whom I have a long-standing collaboration and friendship, and to Satpal, of course, for all his help in the organization of this meeting. I'd like to thank the senior researcher I work with, or used to work with, some of them are gone, and the students that have been involved in the chemistry I've presented, and you all for your kind attention. Thank you very much.
Thank you, Professor Gendon, for the exciting lecture. And I also appreciate for closing in time also. So thank you very much, sir. So if there are any questions, please. Any questions? So none, I think. So once again, thank you so much for a very wonderful lecture. And
thank you.
Thank you, sir, again on behalf of the organizing committee. Thanks again.
Thank you very much.
Close this now.
Yes, sir, you can close. We may go for the third lecture.
Okay, so let us close this one probably. Okay, so now we move to the third plenary lecture of this session, and it is by Professor Ramanna. He did his PhD from the University of Hyderabad and went on to do the postdoc at ETH Zurich with Professor Andrea Verse. And then he moved to NCL Pune in 2001, and where his main area of interest is in catalysis. And he has very long list of awards, you know. Some of these are I'm going to cite here. CSIR Young Scientist Award 2003, NCL Scientist of the Year Award in 2009, CRSI Bronze Medal 13, A.V. Ramarao Foundation Prize 2016, CNR Award, and many more. And besides large number of publications, he also has 17 patents. So we look forward to listen to him now, interrupting the nitro azido alkyne cycloisomerizations. Professor Ramanna, please.
Yeah, good afternoon. I hope I am audible. Yeah, always actually giving a presentation after the lunch, it has its own disadvantages because you have to keep the audience asleep. But at the same time, actually, it has a lot of advantage because many of your peers will be speaking about the same topic and making a platform for you where you can skip some of the introductory slides. You agree that actually today morning we have two contrast presentations, one by Professor Ganesh Pandey, Professor Vic Singh, where he developed actually how much pain it will be to develop a methodology. Almost he says that 70% of the work is unseen. But at the same time, actually, you have another presentation by K.R. Prasad, where he took nearly 30 minutes to convince you how difficult it was to establish a sequence of 7 steps in your total synthesis. After that, you have from Professor Ganesh Pandey, where he made actually a total synthesis is very easy if you have really a good transformations in your hand. But anyway, these are some of the important aspects that our group deals with. We work on many areas. The major area is actually the total synthesis of complex natural products, where we have almost completed more than 50 total synthesis. And in most of the cases, what we try to do is we try to keep as many catalytic transformations as possible in a total synthesis. So it becomes really simple. Here you can see actually almost we employed all the metal complexes in dealing with the total synthesis. In addition, actually, we have established many catalytic transformations in the context of total synthesis. And today, what I would like to present is 2 simple transformations, the nitro-alkyne cycloisomerization, which we started almost 12 years back in dealing with one of the total synthesis, and still we are continuing with the same transformation because of to understand what exactly it happens, and also to prove that actually how this simple reaction can lead to diverse heterocyclic scaffold with really with very increasing complexity. So the title of my presentation is Introducing the Nitro Azido Alkyne Cycloisomerizations. Maybe before I go, actually, I have to really tell what is this nitro alkyne cycloisomerization, or what in azido alkyne cycloisomerization, and why we want to interrupt it, in what context. So here you can see the nitro alkyne cycloisomerization, which involves, is it all right? Yeah. So which involves the transfer of a oxygen from the nitrogen to the adjacent alkyne with the aid of a metal complex. Then it leads to a alpha oxo metal carbene. This undergoes subsequent cyclization to lead to giving a cyclic nitrogen, which is trivially called as estrogen. And you have another possibility in the same cyclization where the oxygen will be transferred in a endo fashion. Then you are going to have a isomeric alpha oxo metal carbene, and this undergoes again actually a electrocyclization followed by reductive elimination of the metal, leading to a anthranil, which is isomeric to the estrogen. When it comes to the corresponding azido alkyne cyclizations, here what happens is you have most of the times actually these cyclizations are carried out by gold complexes. We will be getting a alpha immuno of gold carbene. This can be trapped by various nucleophiles to get actually indolent derivatives. So in the last 2 decades, actually, this whatever the alpha immuno gold carbenes or alpha oxo gold carbenes, they have gained wide popularity, and also you have more than 2,000 papers that appeared in the 2 decades. So how we entered in this area is in dealing with the total synthesis of a group of natural products where you have a, I think this is, yeah, where you have a three indolent skeleton, which is trivially called as pseudo-indoxyl. And if you see actually, these are all actually highly oxygenated indoles, indole natural products, and you have a spirocycle at the C2 position. So generally, whenever somebody wants to construct a pseudo-indoxyl in the context of your total synthesis, what methods are followed is you take a 2,3-disubstitute indole and treat with peroxide followed by a base and heat it. You will be getting this indolin 3,1. It goes via a 2,3 epoxide that rearranges to give the indolin 3. When we started the total synthesis of one of the members of these natural products, what we have asked the question is whether we can use this estrogen, add a nucleophile to the cyclic nitrogen, which is very common, so that actually you can have a lot of flexibility in terms of the groups to be added at a later stage. Unlike actually first you make the 2,3-disubstitute indole, then go for the epoxidation and rearrangement. However, we realize actually one major bottleneck in this context. First, I would like to show actually some of the reports that have appeared for making these estrogens. This is the one which is by Bayer almost 100 years back. Now, 140 years back, where you take this nitroalkyne and take it in either concentrated sulfuric acid or actually in pyridine and heat it, you will get this estrogen. And later in 1916 and also in 1914, people have reported that same nitroalkyne cycloisomerization where this carboxylate has been replaced by a aryl ring could be carried out under photolysis or actually by heating in pyridine at high temperatures. And in 1952, again, actually the same pyridine delta, but in 1969, Hooper, he reported actually whatever the Chadwick coupling you do with iodonitrobenzenes, the copper acetylides, they directly lead to the estrogens. But one of the problems here is actually you need to have a copper acetylide. And again, it also works only when you have a aryl group at the end. So in 2000, on similar lines, Rosen has reported that the Sonagashira of this nitrobenzenes with a terminal alkynes leads to estrogens when you heat this Sonagashira mixture at 100 degrees. But the problem is actually the yields are really bad. So in 2003, actually, Yamamoto has really reported a catalytic method by employing gold complex. When you have the aryl ring at this position, it leads mainly to the estrogen, 73%, but at the same time, actually, it also gives some amount of anthranil. In 2005, Crabtree have reported that when you have R is alkyl, actually I forgot to tell you, in the 2000 Yamamoto's report, what he got is when your R is alkyl, it always gives anthranil exclusively, and also the same thing has been observed with the iridium complex by Crabtree. So in Crabtree's publication, what he proposed is actually the reaction proceeds via iridium a nitro stabilized iridium complex. Earlier, actually, whatever the Yamamoto he has proposed be a cyclization followed by proto-demineralization, then actually a enolate and cyclization. But Crabtree is one actually who proposed for the first time that actually there is the formation of a alpha oxo iridium complex. So anyway, if you see all our whatever the natural products that we have selected here, you have actually the alkyl groups. So considering this, actually, one of the major bottlenecks that what we have realized, we need to establish a method by which you can make the two alkyl estrogens. To make the story very short, here you can see when you have your alkyl group with iridium or with gold, actually it leads to anthranil, and we have come up with a simple palladium complex where we can get exclusively estrogen, and this is very general. And what we have proposed at the time is, in case of the gold, the cyclization follows a 6-endo path, whereas in case of the palladium, you are having a 5-endo mode of cyclization. And in these cyclizations, we will be getting a alpha oxo gold carbines, metal carbines, something like this. Whereas with iridium or gold, actually, we propose that you will be getting an isomeric metal this alpha oxo metal complex. And in order to prove actually whether we really have these two isomeric metal alpha oxo carbines in these cyclizations, we provided an internal nucleophile in our substrate and carried out the cyclization with palladium and also with gold. You can see here clearly actually how complementary products we have got. By this simple experiment, actually, we propose that actually whatever this nitro-alkyne cyclization, either by gold or palladium, actually you are going to have the formation of this alpha oxo metal carbines. And on similar lines, actually, even R.S. Liu also in one of his paper, which appeared during the same time, he also proposed the same thing, that actually the gold catalyzed cyclization proceeds in the same fashion, whatever we have proposed in our publication. Anyway, now if you see the carbene chemistry, the formation of alpha imino or alpha gold carbines, you have a plenty of reagents that can be employed. For nitrogen transformations, you have azides, imino-pyridine halides, and also very recently this anthranyl and isobenzoxazole. And when it comes to oxygen, you have very few limited reagents. One is pyridine oxides. Then actually you have nitro and nitrile oxides and also sulfoxides. Now, after establishing whatever the formation, whatever the involvement of these oxocarbines, what we have developed a project where actually we really want to understand how we can interrupt these oxygen and nitrogen transfer process, this whatever the cycloisomerizations, by employing actually external carbene reagents. Because if you see these, whatever the nitrogen transfer reagents, these azides, anthranyls, or the benzoxazoles, they not only transfer the nitrogen, but at the same time they can also trap the intermediate carbene. So the idea is actually, that actually when these cyclizations happen, you are going to form a oxocarbene by the transfer of either nitrogen or oxygen in an intramolecular fashion. If you do the same reactions in presence of these carbene trapping reagents, what happens? Whether the nitrogen transfer will happen from these reagents, or whether they can complete with the intramolecular process, or actually they will be trapping the carbenes that are formed during this process. For example, if you have a nitro-alkyne like this, we have proposed that actually you are going to have a carbene like this. If this carbene is trapped by this azide, you are going to have this imine, and this imine can undergo a Davis-Burut reaction, something like this. But the problem is actually when we try to see the feasibility of this transformation, we always end up with whatever the established route. This undergoes actually intramolecular electrocyclization and leads to a anthranil. So then we try to see whether the same process can be integrated by a anthranil. So if you have a anthranil, this carbene will be transferred to the nitrogen, then the anthranil ring will be broken, and you have this intermediate, and this should undergo a Davis-Burut reaction to get this N oxide, and then this N oxide will be undergoing reduction to get this cyclic compound. So this reaction worked as we expected, and this is very general, and you can see actually the yields are really good. And in order to proceed further, actually, if you use benzoxazole, here first you will be transferring the carbene to this nitrogen, then you have a phenomethite that is formed, and this phenomethite, what we thought is actually this nitrogen will be adding in a Michael fashion to this phenomethite, then followed by aromatization, should lead to a phenazolene ring with an oxide. Yeah. Anyway, the reaction proceeded as we expected, and to show actually whether really this carbene is involved, what we tried is actually we carried some control experiments like keeping a phenyl ring, because these reactions work only when you have a alkyl substituent at the alkyne end. So we carried out with a phenyl ring where you see that actually we exclusively got the estrogen without any interception of the nitrine, and we employed a benzoxazole having a deuterium here, and there is no deuterium transfer. And also when we looked at the competition between the anthranil and also this isobenzoxazole, we found that actually this isobenzoxazole competes for the carbene transfer against this anthranil. And now I would like to move to the next part, that is the azido-alkane cyclization, where which was first reported by Toste in 2005 with the acyclic systems, and then later by Gegos with the cyclic systems. And here what happens is, first, as I told you in the beginning, you have the nitrines, intramolecular nitrines transfer leading to a alpha immunoglobulin carbene. This will be trapped by various nucleophiles. So our initial idea was if you have this intramolecular transfer, you are going to have a immunocarbene like this, which will be where the carbene transfer will happen to this nitrogen, and this should give some product like this. But in case of this anthranil, even if you have the nitrine transfer from anthranil, it leads to a gold carbene, something like this. And again, actually, you are going to have the carbene transfer from this carbene transfer to the azide, and again, it leads to the same product. So this reaction proceeds as expected, and only the thing is actually it won't work when you have alkyl substituents here. And then actually we looked at the possibility of trapping the same carbene with the benzoxazole. In case of benzoxazole, you have three possibilities. One is the intramolecular transfer followed by intermolecular carbene transfer to the benzoxazole, which leads to a spiroderivative. And same thing actually when you have the intermolecular carbene transfer from the benzoxazole to the triple bond, and then actually this nitrine can undergo CH insertion, which leads to a penicillin ring, whereas actually the same nitrine in a different conformation, this can lead to a carbene transfer to the nitrine, this azide, and then actually you will get the same spiroderivative in this case. So when we did this reaction, so in most of the cases, we got exclusively the penicillin derivative, but only in few cases, like when you have electron withdrawing substituents on the anthranil, we got the spiroderivatives in small amounts to almost in exclusive. So which reveals that actually if the nitrine transfer is not facile from the benzoxazole, then actually the intramolecular nitrine transfer is operating in competition. So anyway, in order to prove actually what is happening in the cyclization, what we did is we did the reaction in presence of the O18 labeled water, where we can see that actually this water, the carbonyl is O18 labeled 60%. That tells that actually finally the carbene, the gold carbene is at this position, and also we can trap the gold carbenes with styrene, and when we employed this deuterated isobenzoxazole, there was no deuterium incorporation. The same reaction when we tried with anthranil, we got again actually the O18 labeling at this position. It tells that actually we are getting this immunocarbene. Now moving to the third substrate, that is the azido-alkanones. Here actually when we want to, you have two possibilities, but one is actually intermolecular nitrine transfer leading to this gold carbene, then actually the intramolecular carbene transfer to the azide, giving this actually indolinone derivatives. But whereas actually if it goes in a intramolecular fashion, you will be getting a carbene like this, then actually this carbene will be trapped by this nitrogen of the isobenzoxazole, and you will be getting some intermediate enolate like this, and this this after the rearrangement of the electrons, you will get a immunoketone. But however, when we did this reaction, what we got is actually we got a cyclic benzoxygenone derivative, and this we presume that actually this undergoes via, you will be found getting a intermediate product like this. This undergoes a 6-pi electrocyclization, then a proton migration should lead to this benzoxazole. But when we looked at the literature, we were really, the reports are interesting. The latest paper that appeared in 2007, actually, where they reported a similar electrocyclization. And in 2015 also, there was a report on the similar type of electrocyclization leading to the benzoxazoles. And in 1996, there is a report by Torres. Again, actually, it's almost close to whatever we have observed, 6-pi electrocyclization leading to isobenzoxazoles. But the interesting fact is, none of these people know that actually somebody else is reported the same. Neither he cited him or he cited this fellow, or even this fellow didn't cite. There are 2 more reports that appeared. In 1976, Whitman reported the cyclization of similar, whatever the aminohydrines leading to this benzoxazoles. In 1976, in 1935, somebody else reported where he took actually the orthoquinone of this this orthoquinone and heated it in acetic acid, and he got this cyclic product. But in these 3 papers, nobody knows that actually this type of cyclization is already documented earlier. But anyway, this reaction is very general. And then next we proceeded to see actually how this anthranil will trap this carbene. In this case also, we got the exclusive the product resulting from the first intramolecular nitrine transfer followed by a intermolecular carbene transfer with this isobenzoxazole. And here you can see. So to conclude, actually, this whatever the azidonitroalkyne cycloisomerization, in most of the cases, the reaction proceeds via intramolecular nitrine transfer, except in case of the benzoxazoles, where this benzoxazole ring is substituted with electron releasing substance or without any electron withdrawing substance. It prefers to go for a intermolecular nitrine transfer followed by a intramolecular carbene transfer. And finally, to conclude, I would like to show you what we have done. We started actually, we entered in this area in dealing with the total synthesis of isorecine A in 2012. Actually, we published where we got the challenge of to make these 2 alkyl substituted acetogens. And then as a part of this, we also have to establish some methods how to add a nucleophile to these acetogens. In the beginning, actually, we have employed indium chloride in dealing with both acetylcysteine A and acetylcysteine 13-deoxyacetylcysteine A. Then later we have used a gold version for adding the same indole to estrogens, where we use the same method for completing the total synthesis of this trichlomin C. Then very recently we have employed a ruthenium for addition of the same indole to the estrogen, and we could complete this total synthesis of helichrome A in one step. And this we have not yet published. Again, actually, this portion deals with actually how we can really trap these carbenes or nitrines, or actually how you can combine these transformations along with some of the other nucleophiles or the dipolarophiles, and where we have established a 1-part cyclization and a 3+3 cyclization or intramolecular cyclization to giving a tetracyclic systems. And then this you have seen the intramolecular trapping of these carbenes. And this one actually what we are, this thing is actually when you don't have any group on the substance, when R is H, we have found that actually this undergoes a dimerization leading to tryptanthrene, which is also a natural product. With this, I would like to thank the audience and also the organizers for the kind invitation and also for the kind hospitality. Thank you. If you have any questions, I'll be very happy to answer.
Any questions? Well, then On behalf of the organizing committee, we thank Professor Ramanna for a very informative lecture. Thank you again, sir.
Thank you so much, sir. I now request Professor R.T. Pardesani, Chairman of this session, to please present a memento as a token of appreciation to the eminent speaker. Thank you, sir. We may have the next lecture.
Yes. Yeah. Yes, that's आपका टॉपिक बहुत इंटरेस्टिंग है देखिए साइकोलॉजी और साइकिल फुल स्लाइड कर दीजिएगा
Okay. So our next plenary lecture is by my colleague, Professor Maya Shankar Singh, who is J.C. Bose National Fellow and C.N.R. Rao Chair Professor at BHU Varanasi. Apart from doing the research work in diverse areas, he has a very distinguished list of awards to his credit, some of which are T.R. Sheshadri Memorial Award, Lecture Award at University of Delhi, Most Productive Research Award, Institute of Science in BHU at 2020. He is also fellow of the Indian National Science Academy, FNA, in 2019, CRS Gold Medal 2017, as well as he also did UGC UK IRI partnership in 2013 with University of Loughborough University, UK. And most interesting, he is going to tell us about chemical psychology of heterocycles. Professor Singh.
Yeah, thank you, Professor Pardesani, for your nice introduction. At the outset, I would like to thank organizing committee and in particular Dr. Satpal Singh Bansara for the invitation, so that whatever little bit chemistry we are doing at the Banaras Hindu University, we can share with audience. Can I know how many MSc students are there? Can you raise your hands, please? Yeah, maybe 15, 20. Why I asked this question? Dr. Satpal did his MSc from BHU in 2006. And when he joined in 2004, after first semester, he came to me one day around 4:30 and told, "Sir, मैं MSc नहीं कर पाऊंगा यहाँ से, मैं MSc छोड़ना चाहता हूँ." Okay, I told something to him and मैंने उनको एक किताब दी. And you see his hard work and his devotion. He earned MSc from BHU with a very good credentials. And in the first attempt, he cleared the JRF and joined for PhD, one of the outstanding synthetic chemists of the country, Professor Basroya at Hyderabad University. सिर्फ मैं आपको यह बताना चाहता हूं, just for your encouragement and motivation. If you have honest approach and hard work and devotion, you can achieve your objective and target. Today I am going to share the wonderful chemistry of dithioesters and thioamides. Before sharing the chemistry, I would like to acknowledge my former and current students. As you know, whatever I am going to discuss, that's a very simple chemistry. Very, very simple chemistry with very simple molecule. We know 1,3-diketones.
This molecule is the simply dithioanalog of the 1,3-diketones. That is the dithioester. That is, see the beauty of this molecule. As we know, in the whole realm of the organic chemistry, broadly there are three kinds of reactions. That is the polar reactions, the recyclic reactions, and free radicals reactions. All the major class of reactions in the organic chemistry has been controlled by again three ways. Reactions have been controlled by either reagents or catalysts. Catalysts may be transition metals or organocatalysis, which are covering a very broad area of the organic synthesis. But now I am going to discuss with the substrate controlled reactions how one can modify the functional group presence in the molecule. As we know, the chemical reactive center in the molecule are the functional groups. If the molecule is monofunctional or bifunctional or multifunctional, and if the functional groups are situated far apart, they display their one and only own chemical and physical characteristics. But if the functional group are closely situated, you see, apart from their individual characteristics, sorry, it's not moving. Yeah, no, yes. So you see, this molecule is very simple and having many electrophilic as well as nucleophilic centers. And
equally good hetero and dimer, but we prefer to carry out the reaction with H3PO4. And these are the shows which you see a lot of variations have been carried out at the R1 moiety, R2 moiety, as well as the R3 moiety. The only limitation of this reaction is that in the case of isothiocyanate, when we put the reaction with aliphatic substituted, no reaction at all. A very close overlapping trailing peaks on the TLC. Of course, a little bit unused starting materials remains, but it's a highly complex reaction. That is the limitation of our discourse. And as far as mechanism, again, very simple mechanism. Simple first addition, followed by ethyl tautomerization, followed by, since reaction has been carried out under open air, no external oxidant is required, undergoes area oxidation to give this thiol radical. Again, this thiol radical has been oxidized by the superoxide radical anion to give this dithiol radical, which upon radical coupling in one part, give the desired 1 to 5. Again, we have detected during our HRMS study the PhD product of the intermediates. This is the large scale synthesis. Of course, parallel in 80% with 5 millimole of the reaction. Again, then we derivatize the dithioester with hydroxyimino at the alpha position. When this one is treated with simple, you see, triethylamine or equivalent in acetonitrile at 60 degrees centigrade, formation of two, that is the highly useful valuable heterocycles, thiazolines and thiazines, that is the 6-membered and 5. Again, you see our the beauty of our reaction is that our whole strategy is highly, very much focused. We concentrate only dithioester or its derivative thioamides or N-acetal, and we are trying to diversify these 3 starting materials or precursors under highly sustainable conditions. So in this way, we have been able to synthesize again 5-membered and 6-membered thiazolines and thiazines in good yield, almost up to 95% and 90%. Not only that, after synthesizing the thiazolines, we tried to oxidize this free carbonyl group. We thought, let us see what happens, which is more reactive, C double bond O or C double bond N. Then when treated with this species in the sodium hydride under DMSO, this carbonyl undergoes epoxidation, and this epoxides almost we have obtained in 80 to 83%. So this is the again some control mechanism of the reaction, and in most of the cases we have determined the absolute structure of the molecule with single crystal structure. And this is the simple conventional mechanism, because you see mechanism proceeds via 4-member, this one, and this has been detected in the HRMS and followed by that's a very N-hydroxyimino thiazolide. Only limitation of this reaction is that, as in the case of thioamides and dithioesters, there are all kinds of alkyl, aryl, heteryl, extended aromatics like biphenyl, alpha-naphthyl, beta-naphthyl. But in this case, what happens? Our that biphenyl is working nicely. You see 72 and 73%. But when we carried out the reaction with extended aromatics, that the alpha-naphthyl and beta-naphthyl, as well as with the alkyl substituents, reaction did not proceed at all. That is the limitation, that is the unsuccessful substrate of this reaction. And again, This is the graph scalability of both the ring 5-membered and 6-membered systems. Again, you see very simple reaction. You see, for the starting materials, we are choosing easily available, cost-wise very economic, and our optimized condition is also highly sustainable and green in most of the cases. K2CO3, no metal or external oxidant, again under open air. In this case, a little bit higher temperature, so 60 degree, we can say the moderate. And again, we have 28 examples that you see 2-aryl amino 2H bromine in one part, in one step, utilizing highly accessible and easily synthesized starting materials, and yield is also up to 88%. The beauty of this bromines derivative, again, there is the exocyclic amino and carbonyl group, which can be further functionalized, and late functionalization possibility of this molecule also exists. So, you see, this is the conventional reactive sites of the thioamides and diethioesters. Already we have done all the previous. In that particular case, we tried to explore the carbon and sulfur, these two center at the reactive center. And after hectic optimization, we became able to use this as the electrophilic center and this carbon as the nucleophilic center and formation of the cycle. And this is the mechanism. You see, here not stereoselectivity, but in our all the reactions, we have been able to achieve the regio and chemoselective. Because it's very small molecule having 5-6 functional groups and different nature, both electrophilic as well as nucleophilic. So here you see highly selective, regioselective reaction gives this intermediate, which have been again detected in the HRMS study, then intramolecular aldol reaction to give the cyclic compound followed by dehydration to give the desired compound. Again, we functionalize the alpha position of diethioester with the allyl group. And then we had, you see, diethioester, ketone, allyl, enol, IR, more than 6-7 functional moieties in this molecule. So you treat it with simple, you see, NBS or NIS, and we got again 2 compounds, that is the dihydrothiophene and thiophene, that is the tri-substituted thiophene, again in one step, and thiophene having the thiomethyl, thioalkyl, thioaryl. It's really very, very difficult to synthesize. Otherwise, in one part, utilizing other substrates rather than diethioesters derivative or thioamide derivative. These are the simple mechanism how dihydrothiophene under this condition, KOH, DMF, and RT temperature is the thiophene, that is the aromatization. These are the some substrate scope. And then this is the simple mechanism again, that you see highly selective addition in all the cases, because there are so many nucleophilic centers. So again, highly chemo as well as regioselective addition gives this exclusive here X may be bromine or iodine. That's why I have mentioned 2 or 3 exclusive products. Again, possibility you see this NBS or NIS increases the electrophilicity of this alpha exocyclic allyl double bond. And this double bond, there are 2 electrophilic center. One leads to the 5-member and other leads to the 6-member. And as I told, we did not carry out the theoretical calculation, energy calculation, but our analytical study, spectral studies support this mechanism. Again, then we thought, in spite of using our thioesters and thioamide, we have been able to synthesize 5-membered, 6-membered, and huge heterocycle. Then we thought, why not we should go for the very small heterocycles having more than one heteroatom. So again, we succeeded in our approach. Simple hydrazide when treated with the iodinium compound, you see formation of that is the diaziridine. Again, fully substituted diaziridine, which can be further functionalized into a variety of systems. Again, mechanism, we have this intermediate A1 and A2 have been detected during our HRMS study. So these are the scopes. We have so many diaziridines, a huge library of the compounds we have synthesized, even having some biological importance also, that is the late stage functionalization of the pharmaceutically relevant compounds having from D-glucose and menthol, from lithocholic acid, from aspirin, as well as from the proline. Again, you see this molecule, that is the phenyl hydrazone derivative of the thioamide. That is the electrochemistry, as we know. The current theme of the organic synthesis, rather than conventional transition metal catalysis or organocatalysis, leading to the photochemistry as well as electrochemistry, because both the weight, both the path are highly sustainable and green. So in this case, we have been able to synthesize again 1, 2, 3 thiodiazoles, starting with our phenyl hydrazone derivative of the thioamides. Under you see DMF, nitrogen, again room temperature within 3 hours. This is the traditional conventional mechanism of electrochemistry, nothing unusual. Then again you see this molecule, our thioamide, when treated with diazo compound. That is the here combination of catalyst and photochemistry. That is the ruthenium second and 470 nanometer UV light under open air at room temperature. And this is the simple setup of the reaction, nothing very difficult or complex. And then these are the some control experiments. Again, we have identified the reaction intermediates and some radical scavengers added during our SRMAT studies. And these are some again gram scale and some other derivatization, further functionalization of the molecule. This is the simple mechanism. First one added two to give this addition product, which undergoes isomerization. This addition product one reacts with the ruthenium 2 to give this thionyl radical, which isomerizes to this thionyl radical, which undergoes deprotonation, which is the further that recycling oxidized by the superoxide radical anion to give the desired compound. These are the substrate scope, again having aryl, het aryl, extended aromatics, even aliphatic also is found to be compatible very well in this particular case. These are the scope of some of the further than we thought, since in this molecule again there is two exocyclic C double bond N and C double bond O. Then we thought for further functionalization, what could be done? Then we just simply oxidize with the metachloroperbenzoic acid, you see, at room temperature within 4 hours. What happened? This exocyclic double bond, C double bond undergoes oxidation, that is the highly in a selective way, leaving the internal C double bond and giving again a cyclic amide. When treated with sodium borohydride, again at the room temperature, you see, again in this case what happens? Reduction occurs again of this external C double bond N, because that C double bond is more reactive than the internal C double bond N. This is the again simple reaction utilizing you see the tricyclic, that is the tricyclic 666 tricyclic scaffold, that is the formation of thiaxothiopyrano T3 coumarin derivative, and reaction is very much simple. Starting with this pyron, First reaction is the Bills-Mayer-Hack formulation, well known. And this is the in situ generated, and simply we treated with our dithioesters at 60 degrees centigrade. And again, the specialty of this reaction is that in that particular case too, we did not need the column chromatography. Simply purification by the mixture of co-solvents. So now this is the, just I am going to take further 1 or 2 minutes. This is the simple mechanism. Again, this is the some of the photochemistry of our dithioesters or thioamide. Again, this is the dizo compounds. Means in a variety of ways. So finally, I would like to highlight our group just utilizing very simple molecule. And it contains 2 sulfur atom, but it's smellless. No smell, bad smell. And preparation is very simple. So you see, cheap and easily available starting materials, operationally simple 1-part cascade processes, part stem and atom economy, most of the cases very clean reaction, normally under open air, easy isolation and purification procedures, good to excellent yields, highly selectivity in terms of chemo and regio, and wide substrate scope, and most of the reaction have been found to be scalable. So finally, I would like to thank you for your kind patience and peaceful hearing. And these are the funding agencies which are supporting whatever the chemistry we are able to do at the chemistry department of Banaras Hindu University. As you know, in organic synthesis, financial support is mandatory. Without financial support, we cannot do anything. So thank you very much.
Thank you, Professor Maya Singh. Any quick comments, please? Any quick comments? Well, our session is not becoming interactive, you see. So anyway, so on behalf of the organizing committee, I thank Professor Maya Shankar Singh for a very lovely lecture. And I think psychology is difficult to understand, but some was clear.
Thank you so much, sir. Now I request Professor R.T. Pardasani to present a memento as a token of reverence to Professor M.S. Singh.
So our next speaker is Dr. C. Malla Reddy. He is professor and head of the department at IISER Kolkata. He did his PhD at University of Hyderabad, and he has many publications and awards to his credit. And noticeable is Swarn Jayanti Fellowship in 2015. He is also associate editor of Crystal Engineering and Communication and co-editor of Acta Crystallographica Section B. Dr. Malla Reddy, please.
Okay, am I audible? Okay, fine.
Yes.
Yeah, first of all, let me thank Satpal for the invitation. And I can say that, it is almost my first visit to Jaipur. First, I came as a student here to Jaipur for sightseeing when I was in MSc. And so it's really great to be here. So I'm going to talk about adaptive soft molecular crystals. And I promise you that there won't be any chemical reactions here. So although my students basically do the reactions to make the molecules, but what I will show you is, so all of you basically synthesize the molecules, but when you basically allow these molecules to come together and then slice, and what wonders they can do, most people actually don't explore it. So in our lab, mainly we explore single crystals. And so I'm going to show you some, physical properties of the molecular crystals. And then I'm sure you're going to enjoy some of the videos, which I'm going to show. And so I thank all my students and former students, collaborators. It's very important to collaborate because in solid state particularly, you need a lot of techniques and sometimes, you need to collaborate to explore the application. So we do that regularly. And also if you have something related to properties of slide materials, you can look at this journal and then you can submit if you have some nice work. And so I'm going to talk about the soft crystals and what are soft crystals. So here I will basically try to cover two things. One is on the self-healing crystals. Okay. And I hope all of you know what is self-healing. And then mechanically flexible semiconducting crystals. Suppose if you make molecule, which could be a semiconducting material in solid state, so you can actually make the crystals flexible, then you can use it for flexible electronics. So these are the applications which you can take from synthetic chemistry to the next level where people, work in this area. So what is self-healing? So if you look at liquids have high mobility, right? So if you take a liquid, even if you cut it, so it is always together. So for liquids, self-healing is basically natural. So we don't talk about it because it is obvious. But if you go to crystals, so once you cut any solid, so it won't come together because it is a solid material. You don't have any diffusion of the molecules at the surface. So they never come back normally. So they are brittle. And once you break them, they are broken forever. So that's why if they can come and then repair themselves, that becomes something interesting and which is non-obvious, right? So here, when you go from here to here, there are many other forms of materials, for example, liquid crystals, which have some properties of liquids, but they are actually like crystalline. They also have some sort of order. So in the molecules can actually freely move. It almost behaves like a liquid, but there is also some local order. So that's why they are special. And liquid crystals, and then you have plastic crystalline materials where in solid state molecules rotate. So that is why these materials are also very soft. Then there are variety of materials. So from here, if you go here, so they become harder and harder. So the materials in between have a lot of interesting properties, so one can explore. And then our group mainly tries to explore some of these materials in this region. So then self-healing also become very difficult once you climb this, right? So if you have to achieve self-healing in crystals, which is extremely difficult, and that is why it becomes interesting if you can actually achieve self-healing. So what is self-healing? Right? For example, if you look at bone, we all know that, if you break your bone, so after 1 month or 2 months, then it becomes normal, right? So what is happening there? So when you break it, since it also has collagen, which can give kind of, piezoelectric effect. So because of that, it generates the charges at the surface. And then because of these charges, osteogenic cells are attracted and then they deposit the calcium. That is how bone heals in the nature, right? So there are different types of mechanisms. It's not that only this mechanism works for self-healing, but there are many variety of mechanisms. For example, if you look at it, so this is a polymer gel. Okay, it's a soft material. Since it is a gel, it is very soft. And then there is a lot of solvent in it. If you cut it and then put them together, and then nicely they heal. Okay, if you pull, they don't come out because it nicely heals. That is because you have some side chains which can form hydrogen bonds. At the interface, molecules can easily move because there is a lot of solvent. So there is a lot of mobility. Because of that, they basically come together and heal. So then there are many other materials. So for example, this is another material where again synthetic chemistry is important here. You put a bulky group here, and then because of that, basically this bond becomes very weak, and then you break it and you form basically ketene and then amine. And then when you put these together at the surface, these groups basically come together and then again rejoin. So this is a trick of synthetic chemistry where people used it for self-healing, right? There are other ways. So slides are not moving. Oh, there's something. Right. So in crystals, for example, if you look at crystals, single crystals, so there are not many examples. And what you see here on the slide is only the literature that you have in single crystal. So here also, if you look at The self-healing in single crystals here is only 7%. And here, if you see, the crystal actually does not heal properly because there is a big crack you can see still, right? So for crystals, crystallinity is very important. So here they achieved some kind of self-healing, but the crystallinity is totally lost here. And then there are also some other examples. So where in solvent, if you dip this crystal, so cracks generate, and then within the solvent, the crystal actually heals the cracks. So this again, this entire thing can only happen when there is a lot of solvent. So crystals can do a lot of things when they are in solvents because the surfaces are very dynamic, so it can work. What is the challenge here in crystals? As I said, crystals are very rigid, so you cannot achieve self-healing because there is no diffusion, and you also need some kind of a high temperature or solvent or something else if you want to achieve any self-healing in single crystal. That is why it is very, very difficult. So then we came across this molecule. My student was working with for some other reason. Then he found nice crystals. It forms beautiful crystals. And then he was playing with the crystals because we work with the we work on the mechanical properties. Then he found that these crystals can actually, when you crack them, the crack generates, and then when you release the stress, again they pull back and then heal. As you can see, the crack is totally gone, right? Once it heals, the crack is totally gone. Then we were wondering how it is able to come and then put the two pieces together and then heal completely. Once it heals, then there is no crack line. You don't see anything. It looks like perfect, right? So we were wondering what exactly is happening. For example, if you see here, this is a slow motion video, and this is the crack, this is the crystal, this is a kind of a forceps, and you have a needle here. This is done under microscope. The big crack develops, and then once you release, then it is clean once it heals, right? Then again, you can see here, then we realize that when you break and then put the two surface crystals away, when you push the other one, so you see that the crystal actually jumps. This tells that there is some attraction on the surface. So what is this? So why there is an attraction? So then we went into the details and we looked at the crystal structure. We realized that this is a P4 space group, P43. This is actually a piezoelectric space group. So piezoelectricity means if you press any piezoelectric material, so basically it generates charges on two surfaces. Okay, so that means there is a piezoelectricity. So that can lead to surface charges. That is why probably it is able to put two surfaces together. That's what we expected. And then we did more studies and we looked at the single crystals after perfect healing. We found that there is no problem. This is totally comparable with the proper single crystals which are freshly grown. So we did not see any difference. That means at least at the level of crystallography, it is a perfect crystal. So healing is perfect. That's what we understood. And my student Somnath did all the X-ray crystallography studies. And then the the data was perfectly matching with the pristine crystal data. And then we wanted to understand and then prove that there is actually a charge on the surfaces. Then we use this Kelvin probe force microscopy from the IISc Jaipur. Then when we measure the charges here using this technique, you can basically map the surface charges. We realize that there is actually a lot of charge. As you can see, the maximum is 9 volts, which is very high. Then the minimum here is 2.2. Then the average is something like 4 volts, which is very high. And then on some other surfaces, we randomly measured many crystals. On some surfaces, we saw positive charge, and the other surfaces, we saw negative charge. So then when we took a crystal with a crack line, so healing was not perfect. So when we measured the data here, and one part was actually negative and the other part was positive. This tells that without any doubt, it proves that you have actually opposite charges. So then why do you have opposite charges? So if you take any piezoelectric material, for example, if you see this, if you basically compress from the top, basically your charges separate. Okay, you are distorting the material. This is a non-centrosymmetric space group. Okay, so then you have charge separation. If it is a purely elastic material, then it should recover completely and then there should not be any permanent charge. But if it is not fully recovering, as you can see here, if a recovery is not full, there should be some remnant charge on the surfaces. So that is what we proposed, and then we proposed a mechanism. So here all the molecules in the crystal are actually aligned in one direction. Molecule has some net dipole moment, right? If all the molecules, if they have heads on one side, tails on the other side, right? Then when you break it, on one surface you have all the tails, and in the other surface you have all the heads. So that means if you have dipole moment, then one side will be positively charged, other side will be negatively charged, and that is how we get these charges, and that is what we actually proved using the Kelvin probe force microscopy. So we see clearly the charges, and after breakage, since we still see some charges, that tells that deformation is not 100% reversible. So there is some fatigue in the system. That means there is some slight remnant deformation in the crystal. That is why you see the charges, and that is why they attract. This is what we proposed. And then in our group, we also use mechanically flexible crystals. We have been working on the mechanically flexible crystals for almost like 12 to 13 years. So then we wanted to actually show some applications of the flexible crystals. So then my students actually, so there are now many examples, many groups across the world actually prepared many types of flexible crystals. I'm not going into the details. From our group also, we have reported many examples, and this is now a very popular topic in crystallography. And so here there are a couple of types of examples. One is plastic type of crystal. And as you can see here, if you have molecular stacks like this, and if you have weak interactions between them, so if you push from one side, basically the columns move, and because of that, you have this bending. If that is not clear, you can see here, right? If your molecules are stacked like this, and then if you move, the molecules can move. So that is how you have plastic deformation in the crystals. And so this you can see here. So these are the crystals which can bend. So here it is called plastic deformation. That means the deformation is not reversible. So it is permanent once you deform. Then there is something called elastic deformation. As you can see here, this is a single crystal. You bend it, release it, then it comes back. So this is a elastic deformation. So then we thought of taking some elastically deformable crystals. So we designed them, and my student Ranita actually made these crystals. And so she did a lot of synthetic chemistry here. I'm not showing. This is basically, for many of you, this might be a trivial synthetic challenge. So what she did is she put some methyl groups here, and here ethyl group on both the sides. And then we found that after formation of the crystals, so these crystals form elastically deformable crystals, and these crystals form brittle crystals. So both have some semiconducting properties. Okay, when you take these crystals and then measure the semiconducting properties, they both show semiconducting property. And we wanted to see, since this is elastically bendable and this is basically brittle, we wanted to make flexible electronics using this, basically a transistor. So Satya Prasad basically made these devices, and then we explored the characteristics. So he basically made the devices. I don't fully understand everything, but what he says is that in the case of flexible crystals, the device, if you bend it many cycles, so the performance basically does not go down. But if you take the brittle crystals, the performance actually, even just after a couple of cycles, the performance actually goes down drastically. So this tells that the flexible crystals basically form better durable electronic materials, devices than the brittle one. So this tells that if you have flexibility, then you can basically use the crystals for flexible electronic. In most of the cases, if you take brittle crystals and then even if you have a flexible substrate, if you bend it, the crystals actually may break, okay, or they may actually come out. So it won't be basically compatible. So suppose if you want to implant them on the skin, or there are now a lot of research is going on. Okay, there is something called biomedical devices. In all those cases, your materials have to have similar kind of mechanical properties to that of the tissue. So in those kind of cases, these might be useful. So then we also mechanistic study. I'm not going into the details. So we collaborated with Sharmarke, who is a computational chemist, and then he looked at these two molecules, took the crystal structures, and then he compressed theoretically, he compressed both the cells. We could see that when you basically compress the unit cell of the flexible one, without raising the energy, without basically decreasing the stability, you could easily compress them and then expand them. But for brittle one, it was very difficult, and the energy rises very fast. if you basically take a brittle one. So with this, I conclude. Self-healing is very interesting, and we are now trying to find out how to actually design the self-healing crystals. Now we have almost a dozen self-healing crystals in the lab. We're trying to find out the full length mechanism for this, and then we will basically, we should be able to find ways to design them. And if you can do that, you can, for example, you can make semiconducting self-healing crystals, for example, right? So these will be again very useful. Or if you can find some other material, so where the mechanical durability improves, that will be very good. And soft crystals are again also very important, and we also find ways to design them. So with this, I complete my talk, and I will be happy if you have some questions.
Nice talk. No, any comments, please? Yes, sir.
Mike.
Yeah.
वो दे देगा ना?
For example, if you have greater humidity or something
Yes,
like that,
you're absolutely right.
yeah, it may be lost.
Right.
Yeah.
So if we do this in solution, even silicon oil, we see that still it works. But if you do it in polar solvent, it's very, very weak. So this tells that, this is basically there will be, but under humid conditions, even in Kolkata, where we have 98% humidity, still these crystals show charge for almost like, a couple of hours. Yeah.
Anyway, great. Wonderful. Thank you.
Okay. Any questions from students? Have you ever found any crystals which are long and needle type? I know most of the synthetic chemists also who are here, they just get the R-type diagram, they just throw it away. And that was precisely the reason because of which most crystallographers did not find many of these interesting mechanical properties, because they were not interested in any physical properties of crystals. I mean, if you look at, there are 10 millions of single crystals reported in the CDC. So that means people have handled the crystals, but not many have them paid attention. Thank you very much.
Okay. On behalf of the organizing committee, let us thank Dr. Amit Kumar. And
Thank you so much, sir. I now request the chairperson of the session to kindly offer a token of appreciation to Professor Mala Reddy. We may have the next speaker.
so let me introduce the next speaker of the session now. He is Dr. Amit Kumar from IIT Patna. Amit did his PhD from IIT Kanpur and postdoctoral instincts from City College in New York and University of Constance, Germany. And earlier this year, he has been awarded CRSI Bronze Medal. And he's going to talk about today on synthesis of simple to complex heterocycles using amides and imidates. Dr. Amit Kumar.
Yeah. Good afternoon, everyone. Is I audible? Okay. Thank you, sir, for your kind introduction. And let me thanks to organizing committee member, particularly to Satpal, for giving this opportunity to come here and present the work that we are doing in IIT Patna from last 8 to 9 years, and some of the work that I'm going to talk. As you can see that my title of today's talk is a simple to complex, and using the chemistry of amides and imidate. Basically, our group in IIT Patna is involved in the 3 aspects of the chemistry, where we want to develop a sustainable synthetic methods for making the important functional organic molecules. And for this purpose, we are using the chemistry of amides, chemistry of imidates, and as well as we also work in area of sugar chemistry. And today we will show you that how the simple basic precursor will be used for making the important classes of organic molecules. So as we know that organic molecules play various important role in our day-to-day life activities, and one of the important activity includes in a term of a medicine. So as the organic molecules are the fundamental building blocks of several important
medicinal as a core molecules. These are some of the selected examples, as we can see, of the amide derivatives, which is used for the treatment for the various diseases. For instance, if you see the molecules like this is nothing but we'll see that benzamide derivatives, where the certain functionality has been introduced and which became a very important drugs for the treatment for your hypertension related problems. Similarly, this is the dermatized derivative of you can say the benzene compounds, and this is a heterocyclic compounds which is used for the treatment for the cancer related problems, Parkinson disease problems, and there are the several well-known molecules which is either drug or drug-like candidates. These are the only representative examples of the functional organic molecules which play important role in the term of medicinal chemistry. So now questions come that how to make these classes of functional molecules. So there are generally two classical way. One can go by the functional group transformation strategy, which required a multi-step step. And then after that, the cross-coupling strategy come into the pictures. That is also very alternate important tools for making the important functional molecules. However, from the last 2 decades, particularly around the world, the chemists became very much interested to utilize very omnipresent and very unreactive CH bonds. If you have every organic molecules has a CH bonds. If you directly introduce your functionality as per the requirement, as per the need, it will be great because you have to be sustainable. You are avoiding certain protocols, unavoidable steps. So, but however, the problem lies with these classes is the reactivity and selectivity. So now questions come, what do you mean by the reactivity? Reactivity, as obviously we know that the carbon hydrogen bonds are the very less polarized, so it is less reactive. And obviously we have so many carbon hydrogen bonds present into any organic molecules of the similar nature. So it will, if you want to differentiate them, it is not very easy task to differentiate. So reactivity and selectivity become two important constraints for the direct functionalization of the CH bond. So for this purpose, the chemist has started introducing the certain groups which has the ability to coordinate with the specific positions petrol-fused isoquinoline derivatives. And this compound will be the important heterocyclic compound, might be used for the other purposes. However, when we started doing the work and when we see the NMR, it was not expected product. We got the, instead of this compound, we got the dimeric products. Obviously, up to this stage, its reaction is happening and then immediately go for the dimerization process. And we compare with the literatures with the secondary bidentate based directing groups with the malenomide as a coupling partner. And we, in the most of the cases, you can see they got either alkylated product, spiro product, and 4+2 annullated product. Till date, no one has reported like a dimeric product with the amides. So we started optimizing the reaction conditions, and we found that rutheniums in the presence of a silver tetrafluoroborate and copper state as an oxidant, it worked very well at 100 degrees Celsius, and we got the corresponding dimeric petrol-fused this heterocyclic compounds. And as you can see, we have able to stabilize the structure, including NMR, as well as through the single X-ray analysis. And then once we got the optimized yield, obviously, as an organic chemist, we do for the various, we want to check the scope. And it turned out to be the very good for the most of the substituted systems. And we have synthesized by varying that both part. And these are some of the only selected examples I have represented here. In order to understand that basic how reaction works, we did few control experiments, like how this Ruthena cycle has been formed by treatment with one equivalent, which is well characterized through the single X-ray also. And then we did the control experiment with for 30 minutes. And then we analyzed the crude reaction mixture, the HRMS. We found that the three intermediate is forming here. Obviously, as expected, first the CC bond is forming, then condensation, and then immediately go for the dimerization. So all three isomers has been appeared in a HRMS peak if you are doing for the control reaction times. As well as this was well supported through the KH and KD as well as the exchange. And based on this, we propose the reaction initiated with the formation of this ruthenium active species. And once you have this active species, this go for the cyclometallation, 5-member ring is forming. Followed by you have a alkene which will coordinate with the rutheniums, and then it will go for the insertion to form the 7-membered cyclometallic species. Here, since Heck reaction is going to be possible, so here E2 elimination happens because acetate is in situ generated from the copper acetate, which act as a base to get like a Heck-like products. Once Heck-like products we are getting, it immediately, because of the close proximity, it go for the condensations. And then it might be because of this CH bond is highly acidic natures, immediately go for the dimerization process in the presence of the rutheniums. And followed by reductive elimination, it is a folding. We expect that it is following this pathway and with regeneration of the ruthenium catalyst. So this was our expected reaction mechanism. Since the compound was highly conjugated in natures, so most of the compound when we isolated, it was very red in color. So we became interested to basic photophysical phenomena we studied. As you can see that this compound absorbed at the 320 nanometers and emit at the 620 nanometers. So it is a quite a high Stokes shift difference is there, which is a quite remarkable Stokes shifts. And then we studied about their lifetime, their oxidation potential, etc., in order to understand their photophysical behaviors. As in continuation of the exploring of the simple chemistry to making the complex molecules, we started working with the same partner like malenomides, aryl iodide was treated, and we want to make up to this compound, not the unsymmetrical substituted, phenyl substituted phenanthrin derivative. Our expectation was up to this, where we expected that the reaction will work with the diarylations, then it will go for the CC bond through the intramolecular cross dehydrogenative coupling process. And then obviously one step happens extra. So we expected that the reaction is working with this line, palladiums start with the 0 followed by oxidative additions, then coordination to form the organopalladium species. Then again, because we are taking the excess of the aryl iodide, it go for the another CC bond is forming. So up to this stage, already 2 bond has been formed. And then because of here, palladium again go for the insertion in between the 2 hydrogen, it is forming another interesting carbon-carbon bond. And this eventually it is now a cyclic systems. And once this cyclic systems, now this carbonyl group become acting as a directing groups in the presence of the palladium through the cyclometallation process to activate one of the CH symmetrical system. It's not activating other part of the CH bonds. This might be once it is introduced, some electronically it become a differentiated from the, it is no more symmetrical systems. So it never works for the other part of the this position for the CH activation. In this process, we have made the 4 bond in one step. So that is a remarkable job, if you see. And once we optimized and understand, we started exploring. And as you can see also, our structure has been well characterized and well supported through the single XRD. As you can see, only one part of the CH activation occur here after the cyclization and 3-bond formation. And it varies from the low from 31 to up to the, we got around 55 and in some cases 73. It will vary for the varied systems. Then we thought that can we make this important compound phenanthridine, which is very important heterocyclic compounds present in various natural products as a core structures from the simple precursor from the aryl and either your aryl or as well as your alkyl nitriles in the presence of aryl iodide excess amount. And we expected that reaction should work with the oxidative addition followed by the coordination with the nitrile, and then 1,3-aryl migration is going to be happen to form this organopalladium imino complex. And then this will go for the CH activation to introduce this another CC bond. And then there is a possibility because this amine is left, it can go for the CN bond elimination within a system to introduce the carbon nitrogen bond. So this worked as per our expectation. So here we will first able to form this bond, and then carbon nitrogen bonds. So in one part, we're able to synthesize very interesting compound, very naturally occurring compounds of the phenanthridine derivatives from the simple precursor of nitrile and aryl iodides. And again, we were able to support the structure of the compound through the single XRD analysis. And as you can see it here, again, the range of from alkyl nitrile to aryl nitrile, it works for the most of the systems. And we got the yield in the most of the cases was good to very good yield. So this chemistry, we became interested. We thought, what will happen if instead of using the slight modified condition, palladium, and if you will instead of imine, and you will take acid, will give the hydrolyzed product that is nothing but keto compounds. And then if we'll go for the second cycles, we will able to introduce the benzalic oxidation can be happen, and we can synthesize this 1,2-diketo compounds. And again, we followed the expected mechanism was the same up to this step. And then since we have used here the camphor sulfuric acid and water as a solvent, it turned out it is hydrolyzing to get the keto compounds, and then this keto compound go for the second cycle to go for the copper oxygenase, which is well known for the benzalic oxidations, followed to afford our desired 1,2-diketo compounds. And this was the reaction mechanism. And in order to support Okay, so then we have synthesized various substituted diketo compounds in good to very good, including the heterocyclic including system. It turned out to be very interesting molecules for the 1,2-diketo functional molecules. In continuation, we, as I told you earlier, we are also interested in the immediate chemistry. We thought if we'll take appropriately substituted immediates, and we'll treat under the certain conditions which can go for this cyclic like transition state, which can form the 1,5 hydrogen atom transfer, and then we will be able to make this carbon nitrogen bond. And then that compound is a 5-member nitrogen containing compounds that is known as a prolines. However, we were able to make carbon nitrogen bond, including the carbon iodine bond has been also formed. And this bond has been formed with this expectation mechanism. Ni bond is forming from this reagent systems which go for the cleavage in the presence of light to generate this immediate radical. Once you have the immediate radicals and hydrogen and benzalic particularly, go for through the 6-member hydrogen transfer happens, you are generating the carbon radicals, and then carbon radical is trapping the iodine to form the carbon iodine, which because of this imine which act as a nucleophile, we are able to make this carbon nitrogen bonds. This was up to our expectation. What is happening after what product? Based on the product, we believe that once this imine is forming, cyclic imine, it immediately go for the tautomerization to the enamines. And because of the presence of the excess of the iodine ions, it is trapping this species to carbon iodine is formed, and we are able to make the carbon nitrogen as well as the carbon iodine bond in this process. And we were able to synthesize that 5-member ring will have very high diaster selectivity in the most of the cases. You can see 9:1 and even 19:1 was observed in the cases. Few cases it was a very, you can say the moderate diaster selectivity was observed. Indeed, it works not only for the benzenic systems, we were able to introduce on the aliphatic systems. However, you can see yields was quite poor. Not, you can say average yields was there 38%, 32%, but that was very good for in terms of the reactivity because it is aliphatic system, not a nobody, it is a benzenic. So this chemistry worked. Then once this chemistry works, so we thought now we can take it a little bit more challenging. The sugar is, we work from, I'm trained from the sugar part. So we utilize this chemistry. We thought if we substitute this immediate appropriately onto the sugar systems, which has so many sp3ch bonds, and it can go for the properly, if you treat under the suitable condition, we were able to introduce this oxazolene ring system onto the sugar part. Expected the same line, we should form the ni bond. Once ni bond will be formed, here the hydrogen transfer will be happen from the one phase which is to the syn to each others to form the carbon radicals. Then it go for the aerial oxidations, and then carbocation will form, followed by the nucleophilic addition to this imine to form this carbon nitrogen. And eventually you are introducing this heterocyclic system to the sugar parts, which is containing the different functionality, which was indeed a very, very happy moment for me. And we were able to synthesize differentially substituted compound, oxazolene fused compound in a good to very good yield in the most of the cases. And then this compound we further explored for the glycosylation. We thought we were able to introduce this quaternary center, not quaternary carbo, but quaternary center at the C2 position, which will also come under the branch of a glycodiversified products. And last, we became also a slight change. We thought we should make another interesting class of the molecules, which is a spiroxazolene system can be introduced onto the sugar by just manipulation of your immediate from anomeric position to the 6th position. And we did the certain, obviously various optimization has been done. And we found that the best condition was with this condition by using the 12 watt of blue light, it turned out to be really good. And in the most of the cases, we were able to synthesize we were able to synthesize the compound in a good to very good yield. So finally, I can say that our group has utilized very simple chemistry from the amide imidates to convert to make the various important heterocyclic. So we can say from the simple to complex, we can make into our labs. These are some of the representative examples I have kept here. And finally, I have to acknowledge Department of Chemistry, IT Patna for the infrastructure support, my job, CRB, CSR for their generous funding, my students, these 2 students are MSc, and I have 3 students. 2 students are working in a catalysis, 1 student is working in a carbohydrate. And again, thank you very much for your kind attention.
Any comments, please? Questions are welcome now. Yes. Okay, over there. ऊपर ले जाइएगा. ऊपर ले जाइए.
Sir, in starting slides, you have mentioned KH by KD.
Yes.
So how we you have calculated the KH by KD, and what type of information we have get from KH by KD?
KH by KD, you give you the isotopic that how much it should substitute hydrogen with deuterium. that your CH bond is a rate determining step or not. So once you substitute with the hydrogen with deuterium, their rate with the time, you will see the yield, or either you can calculate through the yield, or if you can calculate through the NMR ratio also, if it is the different. And they, which indicate that is real the part of the CH activation, or CH activation happens sometime later. So this is the major aim of all the KH by KD experiment that we do.
So in some papers, they have mentioned like KH by KD is less than 2.
Less than 2, Germany considered as not a rate determining step. Germany, if it is more than 2.5, or even people a lot of times say there's a more than 3, that will be the rate determining steps. Yeah. If it is less than 2, then it's considered as the might be CH activation happens somewhere in between, but not in your transition state where you say that it is a rate determining step.
Thank you.
Any more comments, please? Okay, then on behalf of the organizing committee, we thank Dr. Amit Kumar for a nice talk.
Thank you so much, sir. I now request the chairperson of the session to kindly present a token of appreciation to Professor Amit Kumar. We can have the last lecture of this session.
Okay, so with this, we come to the last talk of the session, and it is by Dr. Debashish Banerjee, who is from IIT Roorkee. So he did his PhD from IIT Kanpur and postdocs in Germany and Sweden. And in 2015, he joined IIT Roorkee. And he is recipient of, apart from SERB and DAE, he is also recipient of a research grant from Evonik Industries, Germany. Yeah? So Dr. Debashish Banerjee, please start.
Yeah. Good afternoon, and thank you for a kind introduction. And on the outset, I'd like to thank, I think I'm audible. Yeah. So I'd like to thank Dr. Satpal and the organizing team for giving the opportunity to present our just a few research work here. And I'd like to discuss today this hydrogen bonding catalysis application and some of the interesting mechanistic studies. Basically, last 5 or 6 years, we have working on this alcohol chemistry, and this alcohol will just maybe independently sort some of the reactions, or starting from other past example and how it's create a base for the further development of our laboratory. So initially, as I mentioned, that we are working in hydrogen bonding. So this hydrogen bonding catalysis, basically we work only in homogeneous catalysis. Apart from that, our group also work in different areas like sustainable development and the development of new reactions and their applications in biological activities, some important natural product, and also some mechanistic studies. And doing all these things, we try to utilize the non-precious metal catalyst, iron, nickel, and manganese-based reactions. So I think it's needless to mention that the importance of the non-precious metal catalysis, because nowadays, in last decade, this is a surge in the catalysis research that you need to develop or maybe replace the non-precious metal, precious metal catalyst by non-precious metal catalysis with equal efficiency. So in try to doing this, if you look at the importance of non-precious metal catalysis highlighted in various important reviews as well as some important books. Maybe if you are interested for the young researcher, you can have a look in these books. So we utilize this non-precious metal catalyst, but our focus is quite very specific. We try to utilize the more sustainable development, and whenever we try to develop a new reaction, we look for most importantly the side product. Because most of the cases we utilize only this utilization of renewable raw material. As you can see that we have utilized only all the reactions. Today I'll be going to discuss are the alcohol. And I will show you that how you can tune the activity of the alcohol through hydrogen bonding process for the synthesis of the various CC and CN bond formation. Sometimes you can also develop some important natural product where earlier it was
synthesized in a multi-step synthesis, but I'll show you that you can make it in 1 or 2 steps if you have a suitable two coupling partner. Apart from that, I am also going to discuss some of the important reactions where you can show that the newly which is strained heterocycle can also be synthesized using this process. So we are basically interested to avoid this waste generation and avoiding the use of multi-step synthesis process. So further, today I'll just going to discuss about the two important reactions, the hydrogenation and dehydrogenation reaction. So if you can look at this, for example, if in the laboratory, if till now, if we try to develop a new reaction, for example, I have to develop a reaction, amination reaction. What we basically look for, and we have a preassumption that alcohols are not a good living group. So what we try to do, we generally protect the alcohol for more easy, or maybe you can say the most sustainable, the most easy living group like chloroacetate or carbonate, so that you can get the good deal and the reaction could also be faster, or maybe it is less time consuming. But in other way, if you look at this, in this two process, you can generate stoichiometric waste, and which are in the two processes for industrial application. This is really a challenge that if you have to generate the waste and remove the waste, so this is very, very cost effective process. So therefore, if we target to develop a reaction, so you can use only alcohol and you can get this the suitable coupling partner. For example, I am in here and with only generation of water as the byproduct. That reactions are more sustainable, and also you can look for that industry valuable reactions also. But during this process, if you can know that this alcohol is not really a very suitable substrate, that's why this hydrogen boring catalysis come into the picture. If you have alcohol and then you try to find out, then the first step, this alcohol get dehydrogenated to aldehyde, and if you have a suitable coupling partner, you are going to get the condensed product. Here it is imine. Thereafter, you have this borrowed hydrogen can be borrowed. But here, the important role of metal is metal get this hydrogen. From alcohol, metal can store this hydrogen transiently with this coordination sphere, and later on, this hydrogen can again be borrowed to this unsaturated double bond to get the desired product. So this is the story of hydrogen boring catalysis. But what happens if you have the dehydrogenation reaction? In this case, if you will be having your intermediate product generation, but in such case, your hydrogen will not be transformed into this unsaturated product, whether you can get the dehydrogenation. So this is also a new technology where we are starting through, where you can develop the new or green hydrogen. So we have also taken up some collaboration with IUCL, where you can develop some new hydrogen generation in this process. This metal catalysis and heterogeneous technology also. So ultimately, our challenge is to utilize renewable resources and application of hard-to-handle metal catalyst. So let's have a look some of this important reactions. So why we are more interested in this hydrogen boring catalysis and what is really known in the literature. So if we look at the brief update, this metal catalyst reaction, early 2015, this metals only populated by this work, manganese, iron, and cobalt catalysis. But if you look at the catalyst process, these catalysts are mainly based on the pins catalyst. These are highly expensive in nature, multi-step, also ligand synthesis and air sensitive. The storing is a very difficult task. So therefore, we try to find out some important technology where we can have this commercially available metal source, and you can directly utilize this for the multi-scale reaction like industrial application oriented synthesis. In such case, we try to find out that what about the bifunctional of the nickel catalyst. So I will not go in the whole details of this story we have come across, but we try to observe that the nickel has a big issue, and this issue lies at the nickel hydride species is highly unstable and you cannot trap or detect by proton NMR spectroscopy. So therefore, the bifunctional catalysis nature of the nickel was quite unknown before 2015. So we have taken up this challenge and we try to find out this how this nickel catalyst can be useful for our synthesis. So we try to plan the fast reaction, initial studies with the alcohol amination, and you have find that this process is quite, we stabilize this process that this can be utilized for this bifunctional nature of the catalyst. Now let's look at this bifunctional transformation of the nickel, how it works. Initially, as I mentioned, that we are trying to lies this ligands. So we have tested the various ligands, but ultimately found that only phenanthol ligand has a better activity within this condition. The initial stage we observed that tramthol in presence of nickel dibromide, it forms a strong complex, is like catalytic in situ complex A. And further, when it's come into the contact with alcohol, this forms the nickel alkoxide. And believe me, this nickel alkoxide is very, very stable. And sometime you might have read also the textbook that nickel alkoxide basically poisoning the catalyst. So that is the reason this drawback that nickel has not been developed till earlier days, year 2015-16. So we try to look at these studies and we find out that if you utilize a little amount, higher equivalent of little base, so you can have this beta hydride elimination from the salt and you can end up with aldehyde. But the issue is this challenge is not completed yet. So you will be ending up with nickel hydride. And this nickel hydride is quite unstable. So if you want to utilize the bifunctional nature of the nickel catalyst, so you need to focus on the stability of the nickel hydride species. So therefore, we have also established that in nickel hydride can be getting stabilized with a different kind of ligand. So further, we have succeeded in this task by having stabilizing the nickel hydride species. So when you look back, I just subset scope of the examination is quite working well for electron withdrawing and donating agent all the substrate utilizing from the amine and the alcohol part. But our main focus was the synthesis or utilization of this more of alcohol substrate. For example, it will utilize also diol, diphencanamine and dimethylamine, and all these cases we have observed a good, excellent to good look for the mechanistic studies. And as I showed earlier, that we have developed this intermediate synthesis, this nickel catalyst, and this catalyst we found this is working for the intermediate species. And just I mentioned that initial studies we have showed the nickel hydride species is quite unstable. So we try to find out that different kind of spinning of different ligand, and we were lucky enough to get this highly electropositive tricyclohexyl phosphine can be stabilized the nickel hydride, and it has a lifetime near about 2 hours. So we try to isolate this one and do some little characterization. And further, we have stabilized that this is the nickel hydride species responsible for this catalytic reaction. So this is the first report where we show that nickel can be utilized for the bifunctional metal catalyst. Thereafter, we have done several deuterium leveling experiment also. This deuterium leveling experiment to stabilize that hydrogen borrowing catalysis, which is a hydrogen sampling, as well as also it will be useful for this micro reversible transformation of the process. We have done a lot of mechanistic studies here, but I am just showing a couple of interesting only example where you can utilize the CH and CD, both the reactions, and you can observe that this benzyl CH bond activation is the rate determining step, or you can say that is the slowest step for the reaction process. Further, we have as I mentioned that we'll be going to very specific examples, not all the studies. So further we try to develop this elongation process of N-heteroarine. This N-heteroarine is quite interesting in biological system, and if we elongated the chain using alcohol, then in such cases we will be ending up with this derivative where you can find interesting drug molecule based on N-heterocycle. So here we have shown that we utilize the pyrazine and other heteroaryl derivative, and we try to couple this with the bis coupling, and also some cases we have other heteroaryl derivative I have not shown here. So these derivatives are also shown quite interesting example in the medicinal as well as the material chemistry processes. Further, we utilize this process to introduce this one-step synthesis of this antimineral drug angiosterin, where our target is to develop the C2 to C4 base alcohol. As we know that these alkyl alcohols are quite challenging, and you cannot make this alkylation process so easily. And so as you can see, we have utilized that C4, the butanol, and we have ended up with only 27% of the product yield. So thereafter, we have gone through the routine steps, and we find that this drug can be obtained in 86% isolated yield. So in this process, I will show you that this new reaction leads us to development some more interesting results. For example, that when you have the N-heteroarine, this is, as you know, this sp3ch bond is not that easy to activate or functionalization. So what we observe, if you have a suitable base, you can be end up with otherwise that this N-heteroarine can be participated in presence of base condition. This is the equilibrium reaction, and you can have the dearomatization or enamine. This enamine is quite challenging to trap in NMR studies also. So what we try to do that in situ this reaction, we have done this deuterium we have added, and we have isolated this product using GC mass, and also we have studied in the NMR. So this also a proof that this is the intermediate product is forming throughout the reaction. But later on, what we tried that we have utilized this aldehyde. In this case, what we observe that when you have alcohol and this aldehyde, so aldehyde, this enamine can get and trap the aldehyde very fast. Thereafter, we can get these two products. One is your intermediate, basically olefin, and another one is alkene. When you add a little bit amount of the more alcohol, where your iron hydride can get and reduce the double bond. But in this process, it's very interesting that you can end up with this dehydrogenation reaction, where when you try to observe the product formation, it is exclusively olefin. For example, this reaction, if you can see, and a very important classical reaction, the Julia olefination, or maybe you can get the Wittig reaction. And these cases also, there is a very high chance that you will get the mixture of E and G olefinic product. But in our cases, we have observed this exclusively E derivative, and this is also confirmed by single hexachestal structure. So further, we have utilized this process for development of the new reaction. For instance, that we have utilized this the suitable coupling partner to end up with this garapinine, another antimalarial active drug, which was earlier synthesized in 5 to 6 step process. But we find out that if you utilize a suitable alcohol, you can end up the reaction in a very good in a short step synthesis. So after having this olefin synthesis, then our target is to develop a more general process. If you can extend this reaction for the synthesis of different kind of diene or maybe mono the terpenate kind of molecule. So we utilize this alcohol in these cases where you can have these two different alcohol. And let me tell you this in the literature till now, though we have only the report this the homocoupling of this alcohol is present, but the cross coupling when you have two different alcohol, it is a really challenging task. And I will show you that diene is also again more challenging when you have to control the selectivity of the alcohol and the diene process. So thereafter, just before that, I will show you the mechanism, what basically is happening in this reaction. We have an alcohol, and as you know that dehydrogenation of this alcohol will be end up with this aldehyde, and we detect all this intermediate reaction through GC mass and as also NMR studies. Thereafter, as the system contain equivalent amount of the sodium hydroxide, so in presence of sodium hydroxide, that's undergo the aldol kind of condensation, or you can get the homocoupling of this intermediate, and then you can get the intermediate one. Further, this intermediate in the equilibration with the sodium hydroxide is end up with intermediate 2 by followed by 3, and thereafter the deformylation is taking place, but unfortunately not able to detect this intermediate 4, and we end up with this product formation, this 2A. So in this reaction, we have to note it that we are getting the olefin with one carbon less. So thereafter, we have modified this technology, and they try to utilize the reaction when the two different alcohols are present. And let me tell you, when you have the two different alcohols, we have chances homocoupling from both the different alcohol, as well as we have the cross coupling. Apart from that, we are using also the higher equivalent of sodium hydroxide. So you will be getting this aldol condensation product, side product apart from there. So we have controlled the selectivity of this process, and you can see that we have different selective alcohol from a different aryl variety. Then we extend this methodology to the cross coupling of the unactivated alcohol. So you can see there are two different alcohol. I think the color is not showing in this properly. So these two different alcohol, you have the aryl as well as alkyl. Both the counterpart can be participated in this, and you can extend this alcohol from C4, C2 to C12. So further, we have also extended this process to the different type of fatty acid derived alcohol like stearin alcohol, mistral alcohol, and palmitic alcohol derivative. And we also utilize this process for the functionalization of the late stage drug molecule like naproxen and the ibuprofen. Further, we have extended this process to the synthesis of the dyes. And the very interesting that if you choose a suitable count two different alcohol, you can end up, you can design the 2H like 210 and 24 dyne substitution product. And one interesting observation here, if you look at, for example, you have the citronellol in this double bond is basically the E substitute E double bond. But here, if you take, for example, oleic alcohol, this double bond is a cis. And earlier also I have shown you that when you utilize the nickel as a catalyst, it's known this is a hydrogenation catalyst. But in our case, we control the selectivity. So this double bond is not changing, and also double bond is not getting intact throughout the reaction condition. So this is the beauty and the selectivity of these conditions. Further, we have tried to make this homocoupling of cinamyl alcohol. Our basic target was to synthesis of the triene derivative. However, when we look at this study, we are now in, we find this, though it is forming the triene, but as you know, this double bond is very, very active. So it is nickel hydride is reducing the double bond is in no time. So therefore, we will fail to get this triene, but now we are developing the more new catalyst to find out this more interesting example on this. Just I'll take 1 more minute. So thereafter, we have tried to develop the synthesis of the alkane. Now the process is why we are using the alkane. You know, if you look at the biofuel in the fuel industry, that's what we get the attention from this IOCL, that if you utilize this process, you can use a suitable alcohol and you can get the alcohol in different processes where you can utilize this fluorinated alcohol. We are also working in the organofluorine chemistry, which is the past couple of examples we have shown that you can activate the fluorinated alcohol also, which is abundantly more available. And apart from that, you can utilize 1-propanol ethylene glycol throughout the process. So overall, the message is that you can have two different alcohol and you can plan your reaction to synthesize the olefin, dyne, as well as the alkane in a different manner. So this example, just I'll show you that we have looked at this derivative, which is also independently this analog NDG analog, this calls, and we have utilized a single suitable alcohol, ethanol, phenylethanol, and we can homocoupling this product is going to have almost more than 90% yield. And this is a very important drug utilized in multi-ton scale, these people selling drug. So I'll not go for the mechanistic study, but I'll show you some interesting example that this process, this hydrogen borrowing process is still working here. We can utilize the substituted deuterium and you can find out that rate of the reaction as well as other important mechanistic investigation through the process. So in summary, I just want to highlight that these are the drug molecules. So far, we have synthesized through hydrogen borrowing process, and we have utilized a suitable two different counterpart from our target to synthesize those drugs. Apart from that, we have also synthesized, as I mentioned, this is the process where dehydrogenation you can also utilize for the synthesis of interesting heterocycle derivative. So here we can have some interesting heterocycle because this is also one of the major part of our research. So though we have not discussed this one, so this heterocycle can be synthesized through all these dehydrogenation technology using suitable alcohol, amine, or the other counterpart. So I'd like to I'd like to thank you for your patience, but I'll also invite you. So please visit IIT Roorkee. This is our administrative building, and this is recently celebrated 175 years. And this is our, basically this building looks like that. It is a evergreen lawn, and you can see anytime if you visit, this is basically the James Thomson building. This building looks at the evening. So it is really wonderful, and you please write to me anytime. We'll be happy to host you. And finally, I'd like to thanks to my group member and the funding agencies. Without their efforts, maybe I should not be here. So it is their efforts who are doing performing all the reactions. And finally, I'd like to thank you for it.
Okay, so do we have any question quickly, please? Any quick question?
Yeah.
Yes, sir.
So nice talk.
Yeah.
So
thank you.
How about primary amine and also aniline have been used in CM bond formation. So how about ammonia?
थैंक यू सर आपने अपनी बात को बहुत ही अच्छे कहा कि जो इथेनॉल की बात है बायोफ्यूल की बात आती है वो काउंटेबिलिटी होती है कैलोरीफिक वैल्यू ऑफ द रॉ मटेरियल कैलोरीफिक वैल्यू ऑफ द रॉ मटेरियल उसमें क्या कौन सा सब्स्टिट्यूट किया जाए जिससे कि कैलोरीफिक वैल्यू बढ़े और जो इथेनॉल की प्रॉपर्टी है इथेनॉल का जो एनर्जी कंटेंट वो बढ़े ऐसा कोई प्रोसेस है
The process, shall I speak in English also? Fine.
Oh, okay. My point is how to
understand.
How to increase the calorific value of the ethanol for the biofuel production?
No, actually, no. This might be tell you in chemical engineering might tell you in much better way. So you are a chemist, but I can tell you the solution.
Okay. I think we stop here. We have another question from our
yes,
Professor.
Please. Yeah. Yeah.
So in the CM bond formation, you always use a primary amine or aniline. So how about ammonia?
Yes. No, this is the example we have shown in primary amine, but we have interesting example ammonia surrogates basically. I'll tell you that ammonia what happened if you use the ammonia gas. Sometimes we try to this ammonia reaction need little high temperature and you need to very special setup. So if you really want to follow the ammonia gas, so we are trying to utilize this reaction in basically the water medium. Like if you have the mixture of ammonia, water or ammonia dioxide, so we have some interesting result on that starting from alcohol. But we are trying to develop in a heterogeneous catalyst, not the homogeneous.
Okay. Yeah, thank you.
Okay, thank you very much. So, well, then we, on behalf of organizing committee, we thank Dr. Banerjee for a wonderful talk.
Thank you very much, sir. I once again request the chairperson to kindly hand over a token of appreciation to Professor Debashish Banerjee.
Well, finally, to conclude the session, we will have last speaker, Professor Akhilesh Sahu, who will be reflecting on the new Journal of Chemistry journal for which this session is organized. Professor Sahu, please.
So this one?
I don't know. I just send it.
That one only. Yes, only.
Okay. No problem. Okay, good afternoon to you all. So this session, on behalf of NJC, I thank the organizer that NJC supported some part of the symposium program. New Journal of Chemistry is a hybrid journal, sister journal of ChemCom, and it used to publish all facets of chemistry. And then, if you see here, the impact of this journal has been subsequently increased from last few years to close to 4, and we are expecting this year the impact will be close to 4.3 or 4.4. And here, you will see the decision of this manuscript has been taken maximum, within 2 to 3 weeks' time. Okay, so in this NJC, we are 2 people generally, that myself and Andrew Carr, taking care of organic chemistry related work. And then this Dr. Suman from India, she looks looks on the sustainable chemistry program. Interestingly, the NJC has a very broad associate editor group. Around 20 people are associate editors in this journal that compasses from chemistry and physics, biology, environmental, energy, many sources. So we publicize communication, full papers and perspectives. I think during COVID time, many people from India has published many perspective. And it is now started from this year, the best paper in the NJC. So they choose almost 25 papers in NJC and then they give some funding for research purposes. Moreover, there will be award for best reviewer awards. I think in the audience, I think Dr. Lakshmidhar got last year award. This year, I think where is Dharmendra Tiwari is there or left? Okay. So he got this back, the NJC Best Reviewer Award. So I'm thankful to all the young people, all young researchers, those are from India, and take a lot of help from them for reviewing the manuscript. And whenever it is rejected, it is not very much intentional, but whenever accepted, credit goes to definitely your work. But when it is rejected, that also you take the blame because we all depends on somebody's the reviewers' comments, and that is very essential. And moreover, if suppose sometimes the papers have been rejected, it's not by with any intention, you can appeal. And when there is appeal, and there is a lot of properly addressing the appeal, and it is maximum time it goes through because we are all human beings. And NJC, we have committed that we respect the researchers with their good intention. With this, thank you.
Thank you, Professor Sahu, for reflecting on NJC. So with this, we come to the conclusion of this session. And finally, I thank the Dr. Satpal and the entire organizing team for giving me opportunity to chair this session. Thank you, Satpal. Thank you all. So thank you very much indeed.
Thank you so much, sir. It has been a wonderful session. I once again thank all the speakers of this session for sharing their pool of knowledge with us. I now request Professor Asha Jain from the Department of Chemistry, University of Rajasthan, to kindly offer a memento as a mark of gratitude to Professor R.T. Pardasani for his valuable time and cooperation in coordinating this session. Madam, please. Thank you, sir. Thank you, ma'am. May I now hand over the session to Dr. Satpal Singh Batsara. He has some announcements to make.
Wait. Actually, due to time constraint, it is decided that we must continue without a tea break because tea already served outside and we are continuing out there. So we are not going for a tea break. So that next session will start here, and for that I may request Professor Dilip Kumar to chair the session. Over to you, sir.
Thank you.
Hi.
This. Sorry, fifth. Ladies and gentlemen, please allow me to introduce you our eminent and distinguished professor, Professor Dilip Kumar. He is a senior professor of chemistry at Department of Chemistry, Birla Institute of Technology and Science, Pilani. He received his PhD degree from Kurukshetra University. After his doctorate, he worked as a postdoctoral fellow at Sam Houston State University, TX, USA. He has been involved in research for the last 25 years, and in result of which he has a rich experience of 17 years, and he has published more than hundreds of research articles in the journals of national and international repute. He has one US patent, one Indian patent, and handles several projects from DST, DRDO, UGC, CSIR, DBT, and DST. He has been awarded with Burpedy Commemoration Medal and Prize 2015 by Indian Chemical Society. For 2018, he has been chosen to deliver Platinum Jubilee Award lecture by Indian Science Congress Association. And dear all, I may keep on reading this, but that will be a waste of time. So instead of coming between you all and Professor Dilip, I would like to hand over the session to Sir. Dilip sir, I request you to kindly take the session and coordinate. Thank you very much.
Thank you. Very good evening for giving this opportunity to chair the session 5. And we have two speakers, prominent speakers. The first speaker is Professor T. Punyamurthy from IIT Guwahati. And briefly mention about Professor T. Punyamurthy did PhD from IIT Kanpur. And you know that he is well known among students and researcher, well respected, and is associated with many journals and national, international bodies. And particularly his research focus on cross-coupling reactions, asymmetric catalysis, natural product synthesis. Therefore, you know, with the paucity of time, I'm not just with brief introduction. I invite Professor Punyamurthy to deliver this lecture. Yes, Professor Punyamurthy, please. Maybe. Yes, yes.
Sir, which one? Sir, this one?
Yes, 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 yes. I was thinking, but anyways, they start this. Let's try to read up to the
Chalo. Sound. You have to on it. You have to on it.
Thank you. That's very kind. Yeah, thank you.
It's working. Yes.
Yeah.
Shall we start?
Yes.
A very good afternoon to all of you. It is a great pleasure to be part of this symposium. I would like to thank Satpal and the other colleagues for the kind invitation and for excellent hospitality. I am going to speak about a regional selective CH functionalization of medicinally important heterocellular compounds. We had very excellent lectures today on CH functionalization, several lectures. And as all of you know very well, CH functionalization is a fundamental and important transformation both in academia and chemical industries. We use them to make fine chemicals, materials, drugs, and natural products. Already we had an excellent introduction. I don't want to again repeat so that we can save time. And these reactions can be divided into three types. Metal oxo insertion into CH bond, metal carbonide, nitinide insertion into CH bond. These two approaches have been well explored. At present, we are focusing direct metal insertion to CH bond, which can be further divided into two types, non-directed and directed. When you have the substrate more reactive CH bond that you want to functionalize, you can use non-directed. On the other hand, if you have more than one CH bond with a similar reactivity and you want to selectively functionalize, you have to use this approach, directing group assisted approach. And if you look at after 2000, much attention has been made using this approach to selectively functionalize a particular CH bond. And how will you do it? The substrate should have a functional group which can chelate with your metal catalyst and activate the CH bond through cyclometallation, and you can have a carbon metal bond. This way you'll be able to introduce a functional group. Now, if you look at the literature, the first report appeared in 1963. You can look at here, and where the nitrogen lone pair makes chelation with the nickel and activate the ortho-CH bond to form the organometallic complex. It's basically CH activation reaction, first report. And this is a directed one. And 1965, another report, non-directed one. Here, this CH bond is more reactive, therefore ruthenium reacts with this one, you will be able to form this complex. Following that, in 1989, there was a report and CC bond formation, reaction of this carbon with this propene to give this isopropyl methylpyridine, and using this zirconium complex, the presence of hydrogen. You can look at the Hadley cycle and how the reaction takes place. The real breakthrough happened in 1993. You can look up here how you can selectively activate the ortho-CH bond with the alkene. You will be able to fall into this alkyl group, alkylation. And there, what happens here, this carbonyl oxygen acts as a chelating group, and the real breakthrough happened here. Since then, people started looking this directing group assisted CH functionalization, which is emerged as reliable in the tool, and some progress has been made. Still, a lot of studies can be done. I would like to, my talk will focus on three types of reaction. The first one, I am going to show you some of our recent result on the directed CH functionalization, in particular medicinally important heterocellular compounds. The second part, I will show you a dual catalysis where first stereospecifically nucleophilic opening will take place as a Lewis acid. The same catalyst will act as a redox catalyst in the next step, and in this way you will be able to form medicinally important heterocellular compounds. Basically, first you form the nucleophilic opening followed by CH functionalization. In this way, you'll be able to form di, 5, and 6 member heterocellular compounds. At the end, I also would like to show you how you take place and, if possible, and metal catalyst with light. So let us look at the indole. As all of you know very well, indole is a very important heterocellular compound, and we have two types of CH bond, and the C2, C3, they are more reactive, which is present in the pyrrole part. And if you look at the benzenide part, we have the 4 CH bonds, which are less reactive. And as you can see here, there are so many compounds have indole core unit. And if you look at the currently marketed drugs, out of top 100 drugs, 24 have the indole unit. Therefore, much attention is made to functionalize, and this CH bond, therefore, will be under with the library of compounds, which will be very useful. I would like to show you and some example on the C4 functionalization, which is current focus. And when you go for C4 functionalization, you can do selectively if you have the directing group here, and you can try to functionalize. And one can expect, and you can also try to functionalize C2CH bond through 5-member metal cycle. On the other hand, if you want to functionalize C4 position, you will be able to form the 6-member metal cycle. And we always think that 5-member is more favored compared to 6-member, and therefore competition will be there. It doesn't happen here. And if you simple look at here, the electron density at the C2, C4 almost same. As soon as you introduce carbonyl here, the electron density here is reduced, here is intact. Using this as opportunity, you can try to selectively functionalize the C4 position. And why C4 functionalization? As you see here, there are many alkaloids have C4 allyl functional group, and for particularly this compound have been synthesized from the C4 allyl indole. Therefore, if you try to develop a method, C4 allylation, which will be very useful. Can you do it? Yes, you can do. If you have the allyl acetate, you can try to react in the presence of rhodium catalyst. You'll be able to introduce allylation here and the redox neutral condition. That means you don't need any accident. And the rhodium, I will show you in the next slide. The reaction starts with the rhodium 3 and also end up with the rhodium 3. And you can also further extend this strategy to react with allyl alcohol, and where we will be able to introduce alkyl group or alkyl ketone here, ketone, this one, allyl ketone. And this depends upon the OR substituent here, as well as what kind of additive use. Based on controlling the reaction conditions, you can end up with both kind of compounds. I think there is some problem. Yes. For allylation reaction, you can look at here. You start with rhodium 3. As one can expect, the activation takes place. You are able to form the metallocycle, then chelation, insertion, this beta state elimination, give the product. You end up with rhodium 3. You don't need any external oxidant. And the reaction can be carried out redox neutral conditions, and you can carry out the reverse crop reaction. You can easily remove the directing group, and you can also you can do the Michael addition here, or you can do other reactions. You end up with very useful compounds. Now, you can use also this strategy to introduce the aryl group. And for example, if you have this keto function chelating group, you can try to couple with this aryls via dehydrogenated decoupling reaction using palladium catalysis in the presence of trifluoroacetic acid K2S2O8 at moderate temperature, and you can try to introduce aryl group here. This depends upon the aryl substituent. For example, when you introduce this one and you get a single compound, on the other hand, if you introduce this kind of aryl substituent, of course, you end up with a mixture of regioisomers. And when you look at the reaction pathway, what happens here? And the palladium acetate reacts with the trifluoroacetic acid, and you are able to form this active catalyst, which can make chelation, CH activation, and you will be able to form the metallocycle, which can react with the arene. First, the CH activation takes place, then you react with the arene, and you are able to form this intermediate, which can give the product by reductive elimination, where you generate the palladium 0, which can be oxidized to palladium 2 to complete the catalyst cycle. And as just we have seen, you can also try to do various other functional transformation with these products. For example, you can try to react this one. For example, you can do again CC bond formation, these known reactions, and you can do reverse parallel reaction. In this way, you'll be able to remove this directing group. And also you can as just somebody has mentioned, you can also do the oxide decoupling reaction. In this way, you will be able to make a variety of functionalized molecule. And you can also extend further rhodium catalysis for the alkylation using the cyclopropanol and using this carbonyl donating group. And for example, you can end up with useful compounds. Here, what you do here, you do both CH activation as well as CC bond activation, both taking place, and so that you can end up with a very useful compound. And when you go for the mechanism, and just to form the rhodium metal cycle, it reacts with the cycle of propanol, open up, and with hydrogen elimination, chelation, then insertion, then reductive elimination, you get the product. And by oxidation of the rhodium 1 to rhodium 3, you can complete the catalyst cycle, and you can also couple with the commercial drugs, you can end up with the very valuable compounds. And as just we have seen, you can also remove the directing group. And you can also further extend to quinolene. As all of you know, this is also a very important molecule. And for example, you can react with the mineral cyclopropane, and in this way, what you do here, and you can couple this carbon with this one and reduce selectively, and then you can migration takes place. By the time the opening of the 3-member ring takes place, you will be able to end up with CE alpine as a product, and you can also use very useful. For example, you can use this molecule and try to functionalize. And this some of the applications. When you go for the reaction pathway and chelation, and you can see here and open up, and you get this intermediate further open up, and you will be able to generate this intermediate, which can be converted into product. And in the presence of acid, you generate the rhodium 1, which can be further oxidized to rhodium 3 to complete the catalyst cycle. And these some of the examples for the regioselective CH functionalization. And one more example, and this also we can also couple this vinyl cyclopropane, and in this way you can form a one-part multiple carbon-carbon bond formation, and where you can generate the 6-membered as well as 3-membered cycle system. And for example, nicely you can make variety of scale codes, and you can also use this approach to couple with these drugs, and you will be able to end up with very useful compounds. And when you go from the reaction pathway, and as one can expect, you form the metal cycle, chelation, and you have this one just we have seen, and opens up. And here this is very crucial, and then it can lead to the formation of this tricycle system, and proto-metallation give the product, and you regenerate the catalyst. And this also can be further functionalized to end up with very useful compounds. These are some of the examples how you can use the chelating group for the regioselective functionalization of medicinally important heterocyclic compounds. Now let me go for the second part, where the 5 functional catalysis, and so you can see here that you can use as an advantage to make variety of heterocyclic compounds. And this idea we got about 10 years ago, 12 years ago, we were able to find out the role of copper triflate as Lewis acid redox catalysis, the rearrangement of this hydrazone, and to give these heterocyclic compounds. And there also we found that also copper acid also can act as a 5 functional catalysis, Lewis acid followed by redox catalysis. And having this in our mind, we wanted to expand the scope of this catalysis. For example, this kind of compound, tetrahydropyridazine, if you look at the review, and they have very interesting medicinal properties. They use several methods to make steps to make these compounds. We thought that can we use the 5 functional catalysis approach? In one part, we will be able to make these heterocyclic compounds by carbon-carbon-carbon-nitrogen bond formation. And with this in our mind, we started this chemistry. It works very well, and the chemistry is still specific, as you can see here, and you can end up with this heterocyclic compounds. What we do here, we form a nitrogen-carbon, carbon-carbon bond with high optical purities. When you go for the reaction pathway, regiospecific and stereospecific nucleophile opening can lead to the formation of this compound, which can further undergo conversion, as is where copper to triflate as a redox catalyst can convert this carbon, that is a double bond to triple bond, which can undergo intramolecular cyclization to give this compound. You generate a copper 1 triplet, which can be reoxidized by molecular oxygen, regenerate the copper 2 triplet. And what happens here? The copper plays dual role as a Lewis acid and redox catalyst. You can also extend this strategy with the epoxide. So you will end up with this heterocyclic compound, and the reaction is stereospecific. You can also do it coupled with the natural product to end up with a very useful compound. And as just we have seen, what happens here, when you will be opening, you get this alcohol, which can be further oxidized by redox process to the iminium ion. Then you get this, which can undergo intramolecular annulation, cyclization. There should be cyclization, can give the product. And you can also extend this chemistry. In place of hydrazone, you give aniline, and you can couple with the donor acceptor cyclopropane. You'll end up with very useful compound, tetrahydroquinoline. Otherwise, it's very takes several steps to make. With high optical purity, you will be able to make. And you can use these compounds to convert several medicinally important hydroxylic compounds, 1 or 2 steps. When you go for the reaction pathway, as just we have seen, nuclear opening, then redox process, you generate a radical which will undergo additional reaction with this, then you form the aryl radical, which can be further oxidized, where copper triplet is reduced to copper 1 triplet by single electron transfer process, then this can lose the proton to give these bicyclic compounds. And you can also extend this strategy, and you can also react with N-methyl or related compounds, and you will be able to form the oxysolidine with high optical purities. And you can, when you go for the reaction pathway, you have the amino alcohol oxidation, keep this radical, this ion, which can undergo oxidation. Now, the tertiary butoxide radical can react with this CH bond, and you form this CH2 radical, you form the iminium ion, which can undergo intramolecular cyclization to give this product. And you can also react with acidity and this N-methyl aniline chemistry, and in this way you'll be able to form the imidazolidine with high optical purities once again. And here what happens, and you can also extend this chemistry with propylamine. You can open up and you can undergo cyclization. In this way you'll be able to form either piperazine, tetrahydropyrazine, which depends upon the OR substrate here. And I will show you the reaction pathway, and you can, the reaction is specific. For example, this is not CH activation, and first nuclear opening takes place, addition reaction. The previous reactions involve CH activation. When you go for the reaction pathway, and nuclear open can lead to the formation of this 1,2-diamine derivative, and if R is hydrogen, it undergoes the X by 6 exotic cyclization to give this compound, which undergoes isomerization to the give the product. On the other hand, if you have the aryl alkyl substrate and chelation, you have to use a silver salt to make chelation with the triple bond, activate the triple bond, then it undergoes intramolecular cycle addition reaction with this one, cyclization, to give this intermediate, which can give the product, and in the present base, and you regenerate the silver salt. So these are some of the examples you can see here. Using bifunctional catalysis, you will be able to transform simple substrate into more useful compound with the structural diversity and high stereospecific reaction. And the last part of my talk is the reaction of this cyclic amine and react with acidity. And you can, the reaction works neat, you can open up, and specifically will be ended with 1,2-diamine, which in the presence of light. And this photocatalyst, this has been developed by our group, and you can try to cyclize, and you will be able to form this imidazolidine with the high optical purities. And Professor Pandey is not here, he is very well known for the photocatalysis single electron transfer reactions, and so it works very well. And we also have compared with commercial catalyst. I think there is some problem, the structure is not coming. And but this catalyst for the particular reaction works very well. And when you go for the reaction pathway, as I just mentioned, you don't need any catalyst. Nuclear opening can lead to the formation of 1,2-diamine. studio specifically. Once if you have this one, you have the catalyst, the presence of light, and then you can oxidize and to cation radical. And then you have this one, this can react with molecule of oxygen. You form this intermediate, which can pick up this hydrogen from here, hydrogen atom. You form the iminium ion. And now you form the hydrogen peroxide anion, which can remove this proton, which undergoes intramolecular cyclization, annulation, to give this heterocyclic compounds, where you generate hydrogen peroxide is the byproduct, which has been identified by titration. We can also further extend this strategy in the case of acidity. You can also use donor acceptor cyclopropane, and in this way you'll be able to form these 5-membered heterocyclic compounds. So once again, this is also very important molecule. And so you can see here, this you'll be able to construct this tricyclic compound also with high optical purities and mild reaction conditions. And when you look at the reaction pathway, here you have to use the Lewis acid, the nickel to triflate, helps to activate this donor acceptor cyclopropane by chelation. And now this nucleophile opening takes place selectively, and you will be able to end up with this amine derivatives. Once if you have this one, now you can use this photocatalysis and to oxidize this nitrogen. Here you can see here, you can the pale light, and you form this one, you can oxidize this nitrogen lone pair, you form the cation radical intermediate. And this can, as just we have seen with the molecule of oxygen, you can convert this. This can help to form this radical intermediate. This now can react with the hydrogen peroxide radical, and by you form the iminium ion by single electron transfer process, and you have the hydrogen peroxide ion, which can deprotonate, then which can undergo intramolecular addition reaction with this iminium ion to give this cyclic compound. So this is my group. As you can see here, I am just presenting. They work very hard. All credit go to them. And I would like to thank ACRB and CSIR for their generous kind of support throughout my career. And finally, I would like to thank you for your kind attention.
Thank you, Professor Punyamurthy, for a wonderful lecture. We can take one or two quick questions. Yes, please.
Can you just wait? He's taking. Please hand over the mic to him.
I can hear, I can speak. In this way, they can listen. Yes.
But there are audience.
Okay. Okay.
Great talk, Professor Punyamurthy. I just have a quick query. That couple of reactions you showed enhances like asymmetric, but I was just wondering, is it the ligand you have taken, the chiral ligand?
No. Stereospecific reaction. We start with chiral cyclopropane, chiral
The donor acceptor cyclopropane is chiral.
Yeah, chiral.
Okay.
And you get inverted configuration. Once you have this one, then you do the cyclization.
Okay. So is it, did you also try taking like racemic donor acceptor cyclopropane?
Yes.
And box
That is, I have not shown here because then it will mix up.
Okay.
And parallel, the chemistry is going on. We also do that one.
Okay, fine. Thank
we
you.
have done a lot of, Lakshmi also did a lot of chemistry on that.
Right.
I don't want mix up, then confusion will come. I kept all the stereospecific reaction one side. And yes.
Okay, thank you.
Any other question? I think Professor Punyamurthy, your lecture was nicely explained. So let's say if there is no question, let's thank speaker Professor Punyamurthy for wonderful lecture.
Thank you so much, sir. Before the next speaker, I would make a request to Professor Dilip Kumar, chairperson of this current session, to kindly present a memento to Professor T. Punyamurthy as a token of respect and appreciation. Thank you so much, sir.
The next speaker of the session is Professor Srinivas Hota from IISER Pune. Professor Srinivas, he did the PhD in 2001 while working at NCL Pune and IICT Hyderabad. And post to that, he had a postdoctoral fellowship at Rockefeller University in Newark, US. And since 2010, he is continuing as a professor and Dean of Planning and Communication at IISER Pune. And his main interest is gold catalyzed glycosidation methods. Over the last many years, he is focusing. So with this brief introduction, I invite Professor Srinivas to deliver lecture. Professor Srinivas.
Thank you very much, Dr. Dilip.
20
Yeah, I need, yeah, sure. Definitely. I'll complete before that one. So could you please give me the pointer somewhere? I think you have the pointer.
Do you have that? The pointer?
Ah, okay. She has that.
Thank you, sir. Thank you, sir.
Okay. Thank you all of them for giving me the stage for talking. And at the same time, I would like to thank Professor Badsara. This is not working. Professor Badsara for giving me the opportunity to speak here, and all the organizing committee members for keeping us alive, and at the same time for keeping us engaged for a whole day. Okay, today I'm going to talk about the topic that is very dear to me. But I think I realize that I'm the only one who is going to speak about this aspect of organic chemistry, which is nothing but carbohydrates. Okay, so what we do is that we try to use carbohydrate templates and we use sugars and try to make a variety of different molecules. And then in 2006, we chanced upon a few observations that led us to observe that we will be able to activate the triple bond so that we will be able to activate this particular, oh, I can't see this pointer. 1 second. Okay. So we'll be able to activate this particular triple bond so that it kicks out this propargyloxy group and then resulting in an oxocarbenium ion that can be trapped by different types of alcohols. Having said that, what is the benefit of doing this one, or how we do it, is at 65 degrees Celsius with 5 more % of AuCl3, and we'll be able to make O-glycosides, and it will not be suitable if you have electron withdrawing groups or some things which deactivate the anomeric center. Okay. Later on, what we did is that we tried to accommodate those which have got benzoates or acetates here in the form of we trapped the intermediates so that we'll be able to make the orthoester. And then if you do conduct the same reaction, we will be able to get the same reaction with 5 more % of AU, X3 at 25 degrees centigrade. So the temperature came down from 65 to 25. And because of that one, we were able to accommodate both O-glycosides and S-glycosides, and we can make pyrimidine nucleosides. I'll show you that. And some oligosaccharides too. However, still the problem of activating benzoate containing glycosyl donors is challenging. So we were in search of that. And to do that, we thought that we have to reduce the temperature, and at the same time, we shall be able to conduct reactions with the benzoates too, with a wishful thinking that we made a lot of library of these appendages around this propargyloxy group, and ultimately we identified that whenever we have the gem dialkyl group, we will be able to activate the propargyloxy system with 5 more % of AuCl3 at 25 degrees centigrade, but still we could not do that benzoate containing substrates. Okay. So in 2016, after a lot of frustrating things, and then finally we identified that if you have an alkyne which is adjacent to a carbonate, then we will be able to activate using a AU phosphate salt. This time it's not a AU halide, alone, but it has got a phosphide ligand also. So because of that, the oxophilicity of the molecule got, AU decreased, and at the same time, the amount of HCl that is generating in the reaction also decreased, and because of which it's increased in phenomenal increase in terms of its reactivity. And we now can comfortably say that we can do reactions anywhere from -78 to room temperature. And we can make O glycosides, S glycosides, C glycosides, and then you name any kind of a glycoside we'll be able to make. In addition to that, we can also now activate those glycosyl donors which have benzyl groups or benzoates too. I'll tell you what is the importance of benzoates in a minute. Please bear with me. Okay, so with this kind of a protocol, what we did is that we could develop protocols for making variety of different oligosaccharides to the range of something like 10 sugars which are being adjacent to each other. We joined them, or 15 sugars, or we also made a 25 mer, and then we have completed the synthesis of a 250, not 250, but 54 mer with a wishful thinking that we'll be able to make it up to 131. I don't know why it is moving. I've not done anything wrong. Yeah. Okay. So having said that, then we also have developed a process for Arixtra, which is nothing but the pentasaccharide, which has got about 5 glycosidic linkages and then sulfation and all that. We will be able to demonstrate to you in 35 steps with 12 pots, and then we can do that. Okay. Having said that, now I have to go back to this. Okay. And we also have developed in such a way that we can adapt our protocol to the solid phase synthesis too. Having said that, now what remains for me is what is the next thing that is important is we thought that we'll make this particular molecule, which is present in some natural product. Do not worry about where it is and then what is it important. For us, what is the most important thing is that there is a fucose, and every single hydroxy group which is present on the fucose ring is being glycosylated. So which has its own inherent problems of installation of these particular sugar residues onto the central core L-fucopyranosyl system. So for that, what we did is that we have synthesized this entire glycan. And then finally, after having all the protocols for making the CO bond, we failed to install this particular CN bond. If you look at in the nature, there are different types of CN bonds. One is nature uses something like CN bonds are seen through either the asparagine way or the purine or pyrimidine get connected to the glycan, or there is one which is emerging as a medicinally relevant molecule. So that means that if we try to develop a procedure for making CN bond, we shall be able to make attach glycan to all these three ones. So we thought that earlier methods were by making use of this. Most popular one is the Warburg process for the nucleosides. And for attaching the asparagine, people were using different methods, including the glycan, or otherwise they make a glucol, or otherwise they make a glucosylamine and then connect that one through a regular organic transformation to get the amidation done. And for this one, they have used palladium-mediated CH activation procedure. So we thought that if we have to adopt our procedure and check our procedure, what is the challenge is there will be a competition between the glycosylation and the competitive neutralization for that one. So we have to find a way to go around that. We got interested in this problem, and then this is how people were making nucleosides for a long time. If you make any time nucleosides with this kind of Warburg-Johnson procedure or Warburg procedure, the yields are not beyond 30%. If the isolated yield, but they report maybe 50 to 60% in the literature. But where are we losing the entire yield is because of the tedious isolation procedure involved in that one, and then multiple products, and then removal of the product from the reaction mixture is a tedious task. So with that particular thing, there were several recent developments. One is this particular one where they activate this triple bond, or otherwise you can also, you have been familiar with this one because I have already shown that orthoester, which if you activate that, then the nucleophile can come from the other sterically feasible phase, and thereby we'll be able to get 1,2-trans-glycoside. So having said that, then if you look at our procedure, okay. So then since we know that how to make orthoester, so we also have checked with these uracil, thymine and cytosine so that we could get 1,2-trans N-glycosides, which are nothing but pyrimidine glycosides. But we failed to get any kind of addition of, when we tried to do with the purine glycosides, then we failed to get the corresponding purine nucleosides. The reason for that one is to do with the nucleophilicity of the amine which is present. Purine nucleophilicity is different from the pyrimidine nucleophilicity of those nitrogens. Nevertheless, we failed to get any product in that. So that 1,2-trans selectivity is because of this neighboring group participation or ankymeric assistance that popularly is taught in most of the MSc courses, and then where the intermediate can be attacked by the nucleophile from the opposite face of it. So having said that, then what we did is that, okay, we could make these things. What is so important about that one is, so one can saponify these C2 prime, 2' benzoates, and then one can put alkyl group, or you can do variety of different things with in an orthogonal fashion, so that we will to make nucleosides which were otherwise a bit difficult for them to get them in real large quantities. Okay. So I have already shown you this particular appendage. So where the beauty of this one is the leaving group that is coming out from the reaction mixture is non-participating in the glycosylation reaction. So we were able to make all sorts of glycosides, but we could not, at that point of time, we did not explore the utility of our procedure for making nucleosides. So for that one, if you take salient features of this one is the yield is roughly between 80 to 95%. Most of the reactions complete in about 15 to 20 minutes time. And the tolerance is almost every functional group that we use in regular carbohydrate chemistry are all tolerant for the reaction procedure, and it's applicable for furanosides and pyranosides. Having said that, then we have done this particular reaction with both purines and pyrimidines with a little bit of adjustment. We were able to get the 76% of the purine glycoside or the pyrimidine in 90%, which is quite a lot of demonstration for them. And then at the same time, we could also do for we demonstrated with by synthesizing variety of different nucleoside analogs. Having said that, now what we can do is, if you can start with a ribosyl derivative, which is 1,2-trans in nature, and you can saponify that and then make hydroxy here, desmortin paradenine to oxidize and then reduce it. So now we essentially have transformed a ribosyl derivative to araminofurannosyl derivative. And if you start with araminofurannosyl derivative, you will be able to make a ribofurannosyl derivative. Having said that, you can choose appropriate precursors, and then we will be able to make 7 out of the 8 possible nucleoside analogs. So by doing this one, we were able to develop a new way to make these nucleosides in a much easier fashion. Okay, so having said that, then the next thing that remains is we have also made this kind of a thing. I'm going in backward direction. Yeah. Okay. So now what we can do with the hydroxy group? So now I can convert this one into a triplet and then subject it to nucleophilic displacement so that we can make 2' fluoro or 2' azido derivative of these ribofuranosides. These are very important in the siRNA therapeutic field. So where they try to use them for a variety of different purposes. Let's not worry about that. And the same reaction conditions with a little bit of peaking with the counter anion, we could able to also develop the procedure for making or attaching the asparagine too. And now the asparagylation can be done with the original molecule of the chlorovirus epitope. So we can do with the you attach the asparagine and then conduct the glycosylation, or you can also do the asparagation as a late stage step 2. So having said that, now we are on the way to make this particular complex molecule so that at some point of time we'll be able to make the most important carbohydrate epitope which is present on the chlorovirus. So what about the next third one, which is nothing but this quinoline derivative? These conditions are suitable for making the quinoline glycoside too. And while doing this one, and then there was a pharmaceutical company which approached us they said that they wanted a large scale process for this kind of molecules. But the problem that they faced is after spending a lot of time for them to demonstrate that gold, silver, and all these things, we all as academicians think that we have to develop green processes, and then so many things we say that catalytic, non-catalytic, and then all sorts of things we say, but industry does not care about that. They care about, they don't, Indian industry especially, they don't care about the greenness or whatever the 12 parameters that are listed in the Green Chemistry Journal and then all that. They said that we don't bother about that. That's first one. And the second problem for that happened is because of the corona problem. So the corona, during the corona, the transport has become limited, and then gold catalysts also have suffered. And because of that, we thought, okay, can we find an alternative compared to these gold catalysts which are governed by the sigma aldrich? So the chemicals which are locally produced and then locally made and then which are there in every single lab should be utilized for doing the chemistry. And after doing a lot of survey, we found that simple molecular iodine in the presence of TMSO triplet works beautifully as comparable to gold and silver catalyst. But there you are using 5 mole% or 8 mole% each of gold triplet or gold chloride and whatever gold phosphate chloride and what is that silver triplet. But here what we are using is iodine and TMSO triplet. That's the only thing. But here we are using stoichiometric quantity of, but the effluent that you get will be brown in color. And at the same time, if you look at the process economy, this is much more costlier compared to the gold one. But still, industry feels that they are happy with this procedure rather than the much more greener procedure that we developed. So having said that, and then during the corona period, this molnupiravir, which is a molecule for COVID-19, so that has become very popular. There were a variety of different processes which have been developed by many investigators, including it from India too. And then we too also have developed from ribose and in about 4 parts with one single purification of column. That too we did, and now we are trying to avoid this particular single column chromatographic purification too. And in about 48%, we'll be able to produce this molnupiravir, which is the molecule that is required for making the COVID. Now, so far, what I have shown you is, now more or less we have identified procedures for making any kind of a glycan, is say from disaccharide to we made up to tetra quanta, that means that 54 mer and then variety of different linkages, and then we could more or less make that. So that brought us to a thinking that suppose if somebody does a mistake and then make a glycan, then can I actually correct that one? Can I insert another piece into the entire glycan? With that question, and then variety of different questions can be asked around that one. So we look at how the nature does it and then what other fields are doing. Okay. So in that particular one, this genomic editing, which is nothing but as called as CRISPR-Cas9. So what does it do? As a chemist, if you see, there is a long DNA and then you add another DNA, it goes and then sits there. And then it opens up some portion of that particular DNA so that now it cuts and then opens that entire thing. And then you put another one and stitch it. So what you have essentially done is, this is a target DNA. This is the one that I am saying, which gets inserted. And then it cuts. And then you can insert another piece of DNA into that one. So that variety of different things Jennifer Doudna and the Zhang have demonstrated. And if you look at the carbohydrate analogy of this one, if you have a glycan, can I convert this one, cut the molecule, and then make it into an electrophile and nucleophile? And now you play with the electrophilicity and nucleophilicity of the molecule. And so that now you can take a complementary nucleophile electrophile. Then what will happen is when I conduct the reaction, now this leaving group gets attacked by this nucleophile, and this nucleophile should be attacking this leaving group. Then I will be able to get a glycan piece being inserted into the already existing glycan. And if you look at metabolic oligosaccharide, oligo or glycan engineering is yet another popular one developed by Caroline Bertozzi, where you take a small appendage, you put it on the monosaccharide and then feed it to cells with a wishful thinking that it takes it as a food, and then ultimately it gets incorporated into its cellular machinery, and then ultimately you will get that reporter coming onto the molecule, so that you use variety of different probes and image, or you can use antibiotics and then do a hell lot of other stuff. Or one can also look at a specific enzyme to cleave off, let's say you have an enzyme that can cleave off this particular bond, and then you can get it out. And then after that, you add another glycosyl transferase so that you will be able to attach another foreign piece into the existing glycan. These are the only two popular ways of doing that. And this has never been tried. So we thought that, can we do that? If we have to do that, how do we do that? As I told you, if you have a benzoate groups, then what happens is, because of the presence of the benzoates here, electron withdrawing groups, so the carbocation which is formed here is not going to be favorable. And because of that one, this is called as a disarmed one by Fraser-Reed. Well, if you have benzyloxy group which is donating electrons, so the carbocation formed is stabilized, and because of which these are called as armed to react kind of thing. So we thought that there is a difference in rate of hydrolysis which has been studied by Fraser-Reed very earlier on in 1980s or 90s. And we thought that, suppose if I make this kind of a trisaccharide, now if I use a reagent which is slightly acidic, then because of the favorable rate of hydrolysis of this bond over this bond, now what will happen is that becomes the weakest bond, and then I shall be able to cleave off that one, so that now once the oxocarbenium ion comes, now we are competing with paratoluene thiol, the captain, so that now I could get the estol group there. Now, once I got this estol group, what is the beauty of this one is, if you add any thiophilic reagent, just 1 minute, I'll be done. Okay, when you add a thiophilic reagent, this leaves off, and then it becomes a leaving group in the presence of this one. So now what I do, I come up with the other nucleophile electrophile combination, so that now the reactivity of this one is more than the secondary alcohol. So this attacks on this sulfur, and then I'll get this one. And of course, this already is present in my reaction mixture. So now what will happen is, I shall be able to activate this one so that I can get the tetrasaccharide of my interest. Essentially, what I did is that I have opened the molecule and then inserted a small piece of glycan and then stitched the molecule like what surgeons do in an operation theater. And we can now do it in one single round bottom flask. And we call this as cut, insert, stitch, editing reaction. And then we proved beyond doubt that this kind of a thing is indeed possible for inserting even larger pieces of glycans, whether be it in branched or in a linear fashion. Here is the one which shows that the same trisaccharide or similar trisaccharide, we took it, and a heptasaccharide could be inserted, or a linear heptasaccharide also could be inserted. And then variety of different studies we have done to prove and trap these intermediates, and then did variety of different things. All that remains for me is the generous research support from variety of agencies, DST, SERP, CEPIPRA, ISER Pune, and NCL Pune in the beginning of my career, and variety of different people who have supported, who are being supported by the CSIR, UGC, and CEPIPRA, and a fantastic research group which has a lot of faith in me and continues to have faith in my research. By these two have led to the stage where I am to. Thank you very much for your kind attention. If you have any questions, I'll be happy to answer.
Thank you, Professor Srinivas.
Yeah.
Thank you so much.
Any questions? Yeah, please.
Please hand over the mic.
That's how I designed the trisaccharide. It's based on the rate kinetics of the hydrolysis of those. There are 3 glycosidic bonds.
Okay.
And we know that one of the glycosidic bonds is weaker than the other. So we particularly cut
Use
that
that chemistry to target.
Yeah. But at the same time, now in future, we will be using enzymes to cut that, bring the specificity to cutting that particular.
Okay. Yeah. Wonderful.
Thanks. And we are also trying to do similar things with organic molecules too. Yeah.
Yes.
So,
Thanks. Yes.
How much you are using
Stoichiometric.
So what is the byproduct coming out?
Vinyl iodide. That we have confirmed by crystallography beyond doubt. Yeah. Yeah.
Sir, this CRISPR gene editing process is a great approach to human better development of mankind. So, in your technique, what will change? What the properties it will change, and how it will help?
If you look at the CRISPR, that was discovered in 98. And it took almost like 15 years to come to a stage today where we are to find out applications in the human genome or whatever. I think you have to give it enough time to for saccharides also to evolve. But nevertheless, what I would say is that if you look at, there are some diseases where the mannose expression is important. And then there are diseases where particular mannose has to be cut and then insert something else. Okay, so this kind of things will be possible in future, not for current situation. Yes.
Thank you.
I think it will evolve at some point of time.
Let's thank Professor Srinivas. If there is no question, thank you so much.
Thank you.
Thank you, Professor Srinivas. I once again request Professor Dilip Kumar, chairperson of the current session, to kindly present a memento to Professor Srinivas Hota as a token of reverence. And with this, may I now request Professor Meenakshi Jain, Head of the Chemistry Department, University of Rajasthan, Jaipur, to come over the stage and kindly felicitate Professor Dilip Kumar as a token of gratitude for his kind cooperation and coordinating this session. Thank you, Professor Dilip. Thank you, Professor Meenakshi. Ladies and gentlemen, as I told you earlier, this is going to be the marathon. So one session is over and another session is going to start. We have with us Professor Rakhi Gupta, a distinguished professor, and may I request you all to welcome her with a big round of applause. She will be the chairperson of this session. Professor Gupta is currently working in Department of Chemistry at IIS deemed to be university. She is the principal of International College for Girls, Jaipur. She holds many reputed positions in various academic societies and committees, like Member Advisory Panel of Association of Commonwealth Universities, ACU, Gender Program UK, member of the Research and Innovation Committee, Association of Universities of Asia and the Pacific, Thailand, member of Confederation of Indian Industries, CII, panel on education and skill development, and the list goes on. Again, instead of wasting much of the time,
thank you.
The session to her.
Thank you so much for your kind introduction. And I'll just make a small correction here. I come from IIS deemed to be university, which was earlier actually International College for Girls. But now the status has changed and it is now a deemed university. Thank you for this kind introduction. And namaskar, everybody. I take this opportunity to thank the organizers, especially Dr. Nilima and Dr. Satpal for inviting me to be a part of this wonderful program, though this is the end of the day, so I know everybody is looking forward to the break and the dinner. But let me thank everybody, and without further ado, let me introduce the first speaker of this last session, Dr. Surajit Pandey. Dr. Pandey is currently an associate professor in the Department of Chemistry at the Banda Institute of Technology and Science, Pilani. I'm sorry. So there's another correction which I took from the website. So I request Professor Pandey to make that correction on the website as well. So this is Professor in the Department of Chemistry at BITS Pilani, where he has been working for the last, since 2012. Dr. Pandey did his PhD in chemistry from IIT Kharagpur. He also did his postdoctorate from the University of Texas at Austin, wherein he worked in the Crookes Research Group. His research interests include homogeneous catalysis using dendrimer encapsulated nanoparticles. And in the last couple of years, his research group has extensively focused on cation and anion doping in a nickel-based system for an overall water splitting reaction, the development of which he will be sharing with us today in his talk. And we extend a hearty welcome to you, sir, and invite you for a talk on metal ion doped nickel-based system as a free, metal-free electrocatalyst for overall water splitting reaction. Please give a big round of applause and welcome Dr. Pandey. Dr. Pandey, you have 20 minutes as per the program schedule that I got.
Hello. Thank you, ma'am. This one, right? Good afternoon, all of you. So, thank you, ma'am. Thank you for your kind introduction. So, first of all, I would like to thanks to Dr. Satpal and Dr. Pragati Sagiria as well for inviting me to share our research ideas in this platform. So, the title of my talk says that metal ion doped nickel-based system as a metal-free electrocatalyst for overall electrochemical water splitting reaction. So this is a slightly different type that so far whatever we have learned, we have listened so many talks, beautiful talks today. So this is in the sector, in the discipline of energy conversion. So what we tried to focus to develop some, catalyst where there is no metal because the metals are highly precious. So to avoid the precious metal, we developed compound, those are doped system in a nickel. Now I will focus more. So the talk consists of basically the objectives are need of water splitting, second of all limitations, and then basically the importance of the work, and finally we'll focus our research work. So I don't want to waste our time by saying the introduction, but the most important in current scenario that the whole world is looking for the alternate source of energy, because whatever non-renewable resources we are using, which creates a lot of problem. And you know our energy requirement per day, which is very high, 16 terawatt per day. And if you look at the graph, mostly we are using the non-renewable resources. And the scary part that the resources are going to over by next 40, 50 years. So what next basically? That's why we all are looking for the alternative resources so that we can generate some energy which will be useful as well as efficient. So the point over here that let me spend a couple of times with this beautiful hydrogen scale over here. So here what we can use the sunlight as resources to split water in hydrogen as well as oxygen, so that can be used as an alternate fuel resource. At the same time, via the fuel reaction can be used, and as a byproduct we can use water as well. So the same water as a reactant can be recycled. So it's basically represent a complete cycle. With this, the most and important point why we are following the electrocatalytic process for the generation of hydrogen as an alternate resources of energy. The first point is it generates highly pure hydrogen. There is no hazardous chemical or intermediate, and this is one of the fastest method. And of course, there is no other GHG, basically no other greenhouse gas emission. So that is the concern in current scenario. So with this, I just want to spend some time on the thermodynamics of this water splitting reaction. So this water splitting reaction consists of two half reactions, hydrogen as well as the oxygen evolution. And the change in free energy is around 237 kilojoule per mole, which is a bit high. So, and the other thermodynamic parameters can also be calculated. So to get energy, initially we have to apply some energy.
And if you look at the potential, which is 1.23 volt, whereas the thermonuclear potential is 1.48. So a minimum potential 1.23 is required, but it is not possible to generate hydrogen at that potential. Definitely we have to apply more than that. And of course, no catalyst can generate less than 1.48. But in a standard condition, if we develop some, then you may get, but in most cases, 99.9% cases, we have to apply more than 1.48 volt potential to generate hydrogen as well as the oxygen. And if we look at the kinetics of this reaction, so let me tell you, this reaction represents hydrogen evolution, this represents oxygen evolution, whereas the other two reactions are the fuel cell reactions, hydrogen oxidation as well as the oxygen reduction reaction. So if we take a look, this hydrogen oxidation or hydrogen evolution reaction, the potential is 0. So kinetically sluggish. Whereas in other cases, either oxygen evolution or oxygen reduction reaction, it consists of 4 electron process. So kinetically, it's not sluggish. So kinetically, we have to think. At the same time, the potential is not passing with 1.23. So some extra potential we have to apply either to generate oxygen or to dissociate oxygen. That means some over potential is required. Moreover, in hydrogen, in oxygen or hydrogen evolution over here, we are getting the products as a gaseous product. So the gases can evolve from your reaction system. Whereas in other two cases, the gases are involved as one of the reactants so that the oxygen bond breaking to generate water, whereas the oxygen bond formation, those are very crucial. So in both cases, as it forms, so those are mass transfer, whereas the other two are charge transfer related reaction. So with this brief thermodynamics and kinetics, let us focus when you develop an electrocatalyst. What are the key points where you focus most? The important points are when you develop, of course, we keep the technology in our mind. We always try to develop the bifunctional so that it can generate both hydrogen and oxygen at a time. Of course, the cost and sustainability, which is very important. It can reduce the over potential and dependent on some other factor like stability, cost, as well as the performance. The related activity like current density, Tafel slope, these are the values. So with this all in our mind, we always try to develop some electrocatalysts and of course, keep our eye on the beautiful discovery in chemistry, that is periodic table. So far, what we have done, we have mostly focused on the transition-based metals, and those second row transition element we have used as a dopant, as well as few anions also we have used. But today I will focus mostly on the transition-based metal doped transition metal chalcogenides. So the point is, 3 important pillars that you have to always keep while measuring the parameters during electrocatalysis: activity, stability, as well as the selectivity. So, as I said, we always focus non-metal based material. So if you look at the list that we have developed so far, nickel hydroxide, nickel oxyhydroxide, tungsten based system, cobalt doped system, as well as the iron doped system, where the precious metals are completely absent. So one by one, I'll show you quickly. So first and most important point, if you take a look at the list, mostly are nickel based, we focused with other dopants. So the definitely an obvious question, why we have chosen nickel based material substrate. So far we have developed all the nickel based material, for example, hydroxide, composite, chalcogenides, phosphate, as well as some MOPs also we have developed in our lab. The reasons are non-precious, of course, and it has some electrocatalytic behavior. Second, that it demonstrates a different oxidation state. I'll tell you, which is very much beneficial for the electrocatalytic property. High elemental abundance, strength is very high, good. It can conduct very good heat and electricity, as well as the synergistic effect, which is very, very important. As I said, we doped it on a nickel-based substrate, so the synergistic effect between the dopant and the substrate, which is very crucial during electrocatalytic activity. So in 2020, first we have developed nickel-based like nickel hydroxide and oxyhydroxide. So if you take a look, 3 different states. Nickel is a metallic nickel. Here nickel source +2, here nickel source +3 oxidation state. Though there were multiple multi-metallic centers, still we were not successful to develop this kind of material for both hydrogen and oxygen evolution.
we were successful in the hydrogen evolution only. And we tried our level best to check the similar result in oxygen evolution, but we were unsuccessful. Then we thought, and the required potential to synthesize this material we have applied is minus 0.257, which confirms the formation of nickel. And if you take a look, the inset figure also says the material is magnetic, attracted by magnet, and nickel has a magnetic property. So with this, we thought, okay, how about if we add some dopant to generate some bifunctional activity in a catalyst? Let us go ahead and let us take a look on that. Sometimes we have followed the same electrodeposition electrodeposition process to develop the material. Sometimes other method was followed. So what we did then? We doped with some cation the resin again. Why? To guide the surface reconstruction, to improve the conductivity and stability, as well as to optimize the adsorption intermediate. And it was in our mind that we want to use the catalyst for both hydrogen and oxygen evolution. So keeping that in mind, thought, okay, we can dope with some cation so that it can generate the bifunctional activity within the catalyst. Keeping that in mind, we have developed first electrocatalyst, that was tungsten dope nickel hydroxide, nickel oxyhydroxide. So we have used tungsten 6+, which is a D0 system. And we were successful to develop both for anodic as well as cathodic reaction. So what we did basically, we varied the ratio of tungsten and nickel stoichiometrically, different ratio we have used, and we optimized, we tuned the best electrocatalyst. Second, as I said, it's a D0 system, which helps us a lot to develop the bifunctional activity. Third thing, it shows huge synergistic effect between the tungsten 6+ and nickel 2+ ion, as well as nickel +3. And finally, the Gibbs free energy, that also we have calculated theoretically, and we saw it favors the hydrogen and hydroxyl ion adsorption on the same surface. So altogether, it was beneficial for the overall electrochemical water splitting reaction. So quickly, how we developed via electrodeposition in the first step, and in the second step by using the dopant hydrothermal method. So this is the bare material, and this is the tungsten dope material. So these are the different ratios we have taken experimentally. And at the same time, we have confirmed the ratios via ICP AES analysis, and we were almost same that the amount we have taken experimentally. So our first point, as I said, we doped nickel in the nickel hydroxide and oxyhydroxide system. So of course, our target was to check the lattice suffers any strain or not. So first we have checked the PXRD, powder XRD, and there we have seen some peak shift. Now, if there is a peak shift in the XRD pattern, that means the electronic environment were changed and the lattice may suffer some strain. Accordingly, what we have done, using the Williams-Hall equation for a particular 2 theta values, we have calculated the beta cos theta and sin theta value using the other parameters as well. And we have seen the lattice suffer some strain, which is the positive strain, basically tensile strain. So we can confirm from the slope value of that Williams-Hall equation whether the complex suffer tensile or compressive strain. Here we have seen complex suffer tensile strain. Accordingly, we have also correlated from the HRTM analysis. We have calculated the D-spacing value, and we inferred that the complex suffered the tensile strain. Then what we did, we have checked the X-ray photoelectron spectroscopy, and here we have observed a beautiful phenomena. What was that? That was, if you take a look, as I said, we have used tungsten 6+ as a dopant, which is a D0 system. It has the strong Lewis acid property, and as it behaves as a Lewis acid, so it can scavenge the electron towards itself. So if it scavenges the electron towards itself, then what happens? More and more nickel higher oxidation state will form. And that is one of the requirements to develop a bifunctional electrocatalyst. So what happens basically, as it scavenges the electron, so more and more nickel +3 forms. So how we confirmed? We have calculated the area under the curve for both nickel +2 and +3 before and after doping. And we observed that after doping, the value is 5.89. What does that mean? That means the more and more generation of nickel +3 in the system. So now what we have tungsten, we have nickel +2 and more nickel +3. So altogether, the multimetallic center helps to develop a bifunctional electrocatalyst. And we have cross-checked with the FECM analysis, and where we have observed the vertically grown nanosheet in case of tungsten 0.1
helps better, generates more efficient electrocatalyst, whereas when we move the ratio in lower, higher or lower, the morphology was not uniform and not vertically grown. So we saw the best electrocatalytic activity with this species. Now quickly let me go through the electrocatalysis result that we normally do, the linear sweep voltammetry analysis. We used to cross-check via Tafel slope, and there if we take a look in the table that we have confirmed the Tafel slope value of the best standard catalyst, which shows platinum for hydrogen evolution 59.8, and our best developed catalyst shows 63.5. So we are very much close to platinum. We checked all other parameters like impedance to see the ease of electron transportation during the electrocatalytic property. We have checked the stability, so all the parameters were checked. Similarly, we have also checked the oxygen evolution property via the LSB diagram. We have cross-checked with Tafel, with impedance, as well as the stability. There also we have seen the Tafel slope value for the best developed catalyst was even higher than the standard ruthenium or iridium based oxide for OER. So once we are successful individually with hydrogen and oxygen evolution, then we thought, okay, how about we should check it now based on our requirement in the bifunctional electrocatalytic system. And yes, we were successful when we doped with tungsten in the nickel system. So this says the generation of hydrogen and oxygen both. So there what we did, if you look at the sample deposited carbon cloth, same material we have used as a cathode as well as anode. Show that both cathodic and anodic reaction occurs on the same material surface, and we have confirmed the stability up to 12 hours. And of course, related parameters were checked as well before and after electrocatalysis of stability. Then what we did, we have confirmed the phenomena, whatever we explained experimentally via the theoretical calculation, free energy calculation, D-band center calculation, and bare charge analysis. All the theoretical calculation supports our experimental findings. And we confirm that this tungsten 6+ and nickel 2+ and nickel 3 shows huge synergistic effect. As well as a result, we have seen the shift in the binding energy in XPS as well as the 2 theta value in XRD analysis. At the same time, as I said, nickel 2+ shows D8 system, whereas nickel D7 system, and tungsten 6+ D0 system. So d orbital has more space to absorb the hydrogen as well as the hydroxyl ion. So if more and more hydrogen and hydroxyl ion absorbed, then generation of molecular hydrogen and oxygen would be more. So accordingly, we saw very efficient activity with this catalyst, as well as it helps in the water dissociation, and of course the formation of O coupling favors by using this kind of doped electrocatalysis. So as I said, once we were successful, then we thought, okay, how about if we check with other nickel system? Immediately, we have checked with the cobalt doped nickel sulfide system, and there also we have seen the bifunctional electrocatalytic activity with the same system. And keeping in mind that nickel sulfide consists of nickel +2 and +3, as well as we doped with cobalt +2, but it converted to cobalt +3. So the same idea was multimetallic center in a nickel based system. Accordingly, we were successful, and these are the different ratios that we have developed, and we tuned the best optimized ratio for the generation of both hydrogen and oxygen evolution. So quickly, how we developed our material, we followed the hydrothermal technique via sulfidation, and we did all sorts of characterization to confirm the material as well as the experimental ratio that we have taken. So we have optimized the structure, and as I said, we were successful in the development or in the generation of hydrogen and oxygen together. So the same material, again, we have used as a cathode as well as anode, and we checked the stability. So this is the cell that we have used both as a cathode as well as anode. And what we have done in this case, we have confirmed our result with the theoretical analysis. Before that, just let me quickly tell you, as I said, the generation of higher oxidation state, same thing were confirmed from the CV analysis. We have calculated area under the curve, and we observe after doping more value of this, so which consists of the generation of more nickel +3 in the system, which is favorable for the overall water splitting reaction. We have confirmed the model structure with the help of Professor Jaideep Chaudhary from Jaipur University, and we observed the defect formation energy was maximum for this optimized ratio of doped system. At the same time, what we have done, the calculation of the band gap, as I said, the doped system always shows more metallic character. That means the band, the conduction and valence band come closer. So same thing we observe. So after doping, before doping, the pristine material shows 0.8 electron volt band gap, whereas after doping, it almost reached to 0. Means it shows more metallic character. So more metallic character, that means it can generate more hydrogen and oxygen, more efficient electrocatalyst. We have again confirmed from the PDOS and TDOS calculation, where we have confirmed that the metallic nature, and as well as the cobalt that we have used as a dopant, the 4s orbital take part properly and confirm in the favoration or in the favor of this metallic behavior. Here, if we take a look, the cobalt 4s orbital shows a prominent nature over here, which also confirm the metallic behavior of the dope system. And as it is metallic, so that means it is more efficient. We have also calculated the free energy for all the ratios, as well as we have further confirmed from the Tafel slope calculation. Now, Tafel slope, if you take a look, 0 value, where the most optimized ratio shows exactly 0 value. That means neither in the higher side nor in the lower side. That means it favors, it develops, it supports the efficiency of the electrocatalytic behavior. And that we have observed from both free energy calculation as well as for both hydrogen as well as oxygen evolution. Finally, we have reconfirmed the mechanism of the reaction from experimental as well as from theory. And in both cases, we observe the Volmar-Hayarovsky reaction pathway is the more favorable for water splitting reaction. So there are two pathways basically, Volmar-Hayarovsky and Volmar-Tafel. In both experimental and theoretically, we observe Volmar-Hayarovsky is the more favorable from this reaction pathway and the free energy pathway calculation, both for hydrogen as well as for oxygen evolution. With this, we have done the XPS study, characterization, and same thing observed that the cobalt scavenge the electron towards itself so that it can favor the formation of more nickel plus 3, which is ultimate favorable for the generation of more hydrogen and oxygen. Again, we thought what are the reasons behind it. As I said, it developed the maximum efficiency. So of course, the synergistic effect we have seen, and it shows the change in the binding energy as well as the 2 theta value. We have also observed the availability of unfilled d orbital, which is more, and of course, which is the reason for the change in the electronic environment. And here we have observed from the XRD Williamson-Hall calculation that lattice suffer compressive strain. So as I said, there will be some strain. So here we have observed compression, and as well as the kinetics formation also more, it shows or it favors the generation of more active sites. So now, if you have more active site in your catalyst, that means more and more formation of hydrogen as well as oxygen. We have checked the stability for long period of time. And of course, we have also checked the property after electrocatalysis. The catalyst remains same. There was no change. Last couple of minutes, we also done iron doped nickel cobalt selenide system. So first we have used nickel hydroxide, moved to nickel sulfide. Then we thought, okay, nickel cobalt, nickel selenide system. So initially we were not directly successful with nickel cobalt, nickel selenide. Then we thought, okay, how about if we enter one more metal center? And accordingly, we have developed nickel cobalt selenide system. Now in this system, we doped with iron, and of course we were successful. So how we develop the material? Directly, we develop the material via hydrothermal and selenization on the carbon cloth itself, so that directly we can use the same cloth as a cathode as well as anode. And we have optimized the structure over here as well. So the beautiful image we have seen, and here also we have optimized the structure, the ratio, and we have seen 0.1 dopant amount was much better than the any other ratio. And same thing can be observed from the structure as well, where if you dope lesser amount or higher amount, then excess or lower deposition occur. That also supports the favorism of the optimized ratio. So after that, we have checked the electrocatalytic property, and again we were successful. So, and the material was stable up to 24 hours. Same material was used as a cathode as well as anode. In every cases, whenever I said we generated hydrogen and oxygen, what we did, we have checked the Faradaic efficiency, both experimentally and theoretically, by using the H shell. And we have seen around 89.9 and 91.3% efficiency for OER and HER respectively. One more observation, that repeatedly, as I said, multimetallic center involvement. So one basic inorganic chemistry we have done at the end to confirm the involvement of the multi-metal ions. What we did, during the electrocatalysis in alkaline environment, we have added potassium thiocyanide. So, if you add potassium thiocyanide, then the metal center, whatever available, can form a thiocyanide complex. That means all the metal centers were poisoned by addition of potassium thiocyanate. And it happens. So as a result, what we have seen, after a certain period of time, there is a drastic decrease in the current density as well as onset potential. With respect to time as well, we have observed, so that means thiocyanate creates poisoning in the system, and again reconfirm the generation or the involvement of the metal ions during hydrogen and oxygen generation. Now the last point that we have recently, not last 1 year and onwards, we have started to couple with the PV system, because without coupling with the PV system itself, electrocatalysis is not that successful, because as I said in the beginning, to generate some energy, you have to apply some energy. So to avoid that, if we use the direct resources, so we are planning to couple with the PVEC system, and we are already successful with some system that we will do some more work. So with this Faradaic efficiency as well as the thiocyanate poisoning, we thought this is one of the system where we are getting even better results. So initially without any dopant, and then slowly we doped so many cations, tungsten, then cobalt, then iron, even we have done samarium, cerium, ruthenium, and copper. So far, these are the cations we have used, as well as the anion, sulfide, and some halogens we have already used. So I just showed few results. So altogether, the overall conclusion that tuning we have done with the dopant amount, and always we were successful to develop the maximum or the optimized catalyst. Second, that unfold the microscopic mechanism, the involvement of the ions in the HER and OER evolution. And the third point, that which is very important, we confirmed, again reconfirmed also, the involvement of the multimetallic sinter during the generation of hydrogen and oxygen. So with this, let me acknowledge my students, Dr. Pragati, who was my first student, and I'm fortunate enough that I'm here. She invited me as well, and she is a faculty of Rajasthan University also. So it's my pleasure to thank in the stage to my own student. And I'm also thankful to my other students who started this work long back, and all the work that have done by my current student, Dibba. She also did her master's from Rajasthan University. And I'm thankful to the collaborator, my wife, Dr. Minmoy Basu, Dr. Jaideep Chaudhary, with whom we did all the theoretical calculation, Dr. Rajnish Kumar, Dr. Shomak Chatterjee, as well as Dr. Arko Banerjee. I'm also thankful to the funding agencies. With their help, I'm here. Otherwise, it would be impossible for us to deliver. And finally, BITS Pilani. And thank you for your kind patience. Thank you.
Thank you. Wonderful talk and very need-based work. So maybe a couple of questions we can take.
Yes, sir.
Please hand over the mic.
Yes, sir. Sir, both was there, nickel hydroxide and nickel oxyhydroxide. So, I mean, the altogether substrate was both nickel +2 and nickel +3. So we didn't specify whether it was doped in the nickel hydroxide or nickel hydroxide, but both were there. And in that system, we doped the tungsten.
Trying to understand it.
Okay. Yeah, that's true. That's why whenever we explain the role of both. But in case of nickel +3, it was more important because it's a D7 system. So more space available on the d orbital. So which allows more adsorption of the hydrogen and hydroxyl ion. But we use both as a together system. And the second case also same thing, nickel +2, nickel +3, nickel sulfide also. Sure. Thank you, sir.
Thank you, Professor Pandey. It seems there are no questions further. So please join me in thanking Professor Pandey for this wonderful talk.
Thank you, Professor Pandey. I now request Professor Rakhi Gupta to present a memento as a token of appreciation to Professor Surajit Pandey. Thank you, Professor Pandey. Thank you, Professor Gupta. We may now have our second lecture.
So it's time for the second talk. Professor M. Bhanu Chandra. I'm fortunate to introduce him. Professor Bhanu Chandra is an assistant professor at Central University of Rajasthan. He obtained his PhD from University of Hyderabad under the guidance of Professor Akila Kumar Sahu. He was a postdoctoral fellow in Professor Hideki Yorimitsu's lab at Kyoto University, Japan. And his area of interest is to develop transition metal-free reaction CH functionalization and synthesis of pi-conjugated materials for organic semiconductors. So ladies and gentlemen, let us welcome Dr. Bhanu Chandra with a round of applause. And I invite him to deliver his talk on the chemistry of sulfur compounds in organic synthesis.
बंद हो गया लाइट आ रहा है ये पॉइंट Yeah, thank you, madam, for your kind introduction. First of all, I would like to thank Satpal sir for his kind introduction, kind invitation. Today, I am going to talk about the chemistry of sulfur compounds in organic synthesis and in organic materials, but I will talk only in organic synthesis. So this is sulfur, generally called as a brimstone, and it is by mass in the universe, it is the 10th available element, and in the earth, it is the fifth most common on earth. So these pictures are taken from internet sources, and if you see the source of this sulfur, so the natural process are volcanic eruption, and another we can see the sulfur mining, and even the organic sulfur compounds can obtain in the crude oils. And one of the major byproduct in fossil fuel industries are sulfur and its derivatives. So now, there is a lot of outcome is there in the sulfur, but if you see its utility in the organic reactions, so nowadays people are using the metallic sulfur in organic reactions, and also from the beginning it is witnessed that we can see the many organic sulfur compounds such as thiourea and thioesters and many other sulfur reagents were applied in the organic synthesis. So in this connection, we also would like to develop some chemistry using sulfur compounds. So the greatest commercial use of sulfur is production of H2SO4, which ultimately gives some fertilizers. Okay. So what we are doing at Central University of Rajasthan is we are synthesizing some pi-conjugated molecules having dibenzothiophene core, and we are studying its some photophysical properties, and we are also doing some chemistry on the oxidizer form of sulfur, that is partial oxidation. That is here, it is an sulfoxide unit. So we could take on the assistance of this in the CH activation reactions. And we are also developing some sustainable reactions using the fully oxidized form of sulfur, that is an sulfone. Okay. So now we are also develop some reaction using a commonly available sulfur reagent, that is a thionyl chloride. So today I am going to talk about the sustainable reactions here. Sorry. So dibenzothiophene is an aromatic compound having sulfur. So it is very peripheral modifications can be easily done by using Frobel-Craft kind of reactions. But it is very difficult to change the core because of its aromatic character. So, but we can do this one by simply doing the oxidation. So that is sulfone. So now this ring becomes very electron deficient and it can undergo a SMA reactions with efficient nucleophiles. So what is here shown is that, so in the presence of base, so this is the kind of nucleophiles. So where we are it should have a geminal hydrogens, vicinal hydrogens. Okay, so with the reasonable pKa values. So in the presence of base, it can generate a nucleophile. So this nucleophile can undergo intermolecular SN reaction, then followed by intramolecular. So this is where one can easily remove the sulfur atom in the core. So this is some of the publications in this area. So now the general mechanism for this twofold SN reaction follows like this. So the oxidation, then followed by intermolecular SNAR reactions with nucleophile, then we get the ring opening product. So after that, the intramolecular cyclization or intramolecular one more SNAR reaction will complete, will close the cycle. Okay, so this is how one can easily transform the core of sulfur to here. So, so with this in mind, so we selected a nucleophile. So we thought benzyl cyanide, because the pKa of these two geminal vicinal hydrogens are quite reasonable. And so we thought it can undergo a intermolecular and intramolecular SN reaction to give this kind of spiral compound. So then cyanide can be used for further post-functionalization reaction. So, but what we found is, so we did not get this product. So rather we got the reductive cyanized product. So that is 9-aryl fluorinol. So this was confirmed by X-ray analysis. So next we seen the synthesis of this 9-aryl fluorines in the literature. So these are the methods available for synthesis of 9-aryl fluorines without transition metal free conditions. So the method one is reaction of aryl grignol reagents to 9-aryl fluorines, 9-fluorinone. So generates 9-aryl 9-fluorinol. So on reduction of this one with the triethylsilane, so can give this 9-aryl fluorine. So this is a two-part method. So we have to isolate the alcohol, then we have to subject. And second method here, you see here, this is orthobiaryl acetates or alcohols. So under strong Bronsted acid or Lewis acids can also provide this one. Okay, so but synthesis of this one is required multiple steps. And if you have a substitution here, that is meta position, so we will get a rhizoisomeric mixture because of this Treadle-Crofts cyclizations. So this is some of the drawbacks with this method. So then another good method is 9-fluorinone with tosyl hydrogen forms a tosyl hydrogen, and reductive coupling with aryl boronic acid can also be gives. Okay, so here what we have to do, we have to add the sequential addition. First we have to add this, prepare this, then finally we have to add. So in this line, so we thought that so maybe we can work on this reaction. So as it gives a one-part method and transition metal free. So with this in mind, we started doing optimization reaction. First, we started with the previously established conditions for carbazole and other nucleophilic condition, that is potassium HMDS in 1,4-dioxane. So give 69% yield of this 3A. So then changing the solvents, what we found is petroleum ether is good, 81% is yield we got. And after that, we screened various alkaline metals HMDS, so these were inferior, and no reaction was found in case of cesium carbonate, and strong base potassium hydroxide delivered only 10% yield. So with this optimization condition in hand, so next we move to the scope of aryl acetonitriles. So electron donating and electron withdrawing groups containing 9-aryl fluorines were synthesized in good to excellent yields, and the ortho bearing 9-aryl fluorine was isolated in acceptable yields. So this is, as I mentioned in the beginning, that so if you have the Treadle-Crofts cyclization, if you have the substitution here, so we always end up getting the rhizoisomeric mixtures. But that kind of selective and the regioselective issues can be minimized or completely nullified with this strategy. So because it is free from such issues. Okay, so one can easily selectively synthesize this product. So this is the scope with respect to dibenzothiophene dioxide. So the second position and 2,8 disubstituted 9-aryl fluorines, and as well as this is the third position containing 9-aryl fluorines were obtained in acceptable yields. So it is important to note that the other sulfone system, that is 5 here, so 2,3-diphenyl benzothiophene dioxide is also participated in the reaction to give the densely aerated indene, so in 52% yield. So next, what we initially envisioned that the reaction may be proceeding via twofold SNAR reaction, so to give the compound 7. So later on, maybe the reductive deionization may be happening to provide the desired product 9-aryl fluorine. So in this regard, we performed some controlled experiment reactions by decreasing the quantity of equivalents of benzyl cyanide and base and shorter reaction time. So to our delight, we could able to isolate the compound 7. So then subsequent exposure of this one under standard reaction condition did not provide the yield. So this ruled out that probably the reaction is not proceeding via this pathway, maybe some other pathway is operating. So at this stage, we don't have any evidence of how the decyanation is actually happening to provide the 9-aryl fluorines. Sorry. So now, with the inspiration of these results, so we sought other kind of nucleophile, that is oxygen nucleophile. So with oxygen nucleophile, what will happen is the oxygen will undergo intermolecular SNA reaction to provide the ring opening product. Then desulfurization will provide the 2-aryl phenol. So after looking into the literature, so we have seen only the 2 reports where the molten alkynes were used at 300 degrees Celsius and aqueous alkaline at 300 degrees Celsius. So these are the very harsh reaction conditions, and only one example were shown in that papers. So then, so this 2-aryl phenol synthesis, the general methods or widely used method is taking the ortho-halide phenols and boronic acids and cross-coupling reactions. Okay, so now due to the inherent property of ortho-para-directing nature of this phenol, so one can easily get ortho and para-diaryl substituted phenols. But whereas the ortho and meta substituted phenols are very difficult to get. So, okay, so there are very limited methods to get such kind of substitution. But in this case, what happens is, so we can resolve that kind of regioselective issues by introducing the substitution at dibenzo sulfone stage itself. Okay, so that we can get easily this ortho and meta substituted phenols. Okay, so what we thought is that, so we envisioned that for success of this reaction to decrease the temperature, so a very good reactive hydroxide nucleophile would be required. So for doing the ring opening reactions. So what we speculated is that the super base, so that is called as the KOH in DMSO, would be a suitable choice to achieve this reaction, as the potassium ion is completely solvated and your OH minus is free to move in the reaction mixture. So if you are taking a super base concept. So with this concept in mind, so we started our optimization here. So KOH in DMSO at 100 degrees Celsius, so gave nothing. But when we increase the temperature 120 degrees Celsius, so we are lucky to get 94% yield of 2-aryl phenol. Now the changing of other polar solvents such as DMF, so does not provide any reaction in case of 1,4-dioxane also. And the reaction in protic solvents also completely turned off. So it clearly says the specificity of the DMSO in this reaction. And what we did next is decreasing the loading of KOH. So here I think it was shown in the footnote. So again, decreased the yield of the red. So that means 5 equivalent of KOH is required for this reaction. And even potassium tetrabutane bulky base also gave the 86%. As expected, the OH-free bases, potassium bases were did not provide any reaction. In sodium hydroxide case, we get only 42% AC. So with the optimization condition in hand, next we move to synthesis, see the substrate scope of this reaction. So this is a 2,8-disubstituted phenols under standard reaction conditions, so provides the densely related phenol. So what we can see here, it is an ortho and para substituted phenol. So this can be achieved with the corresponding bromines also, but this is meta-meta quarter phenyl, so 4 phenyls with respect to biphenyl unit, this is meta-meta. Okay, so obtained in the moderate yields. So this is the challenging one. So where I told that you see this phenol, the phenols here it is an ortho, and meta substituted phenols can be easily obtained by introducing the substitution at 3,7 position at the sulfoxide state itself. Okay, so we got this para quarter phenyl type phenols in moderate yields. That's okay in single step. So now, as expected, the unsymmetrical substituted dibenzothiophenes dioxides gave the regioisomeric mixtures. We confirmed this ratio by proton NMR spectroscopy. So even alkyl substituted dibenzothiophen dioxides are participated in the reaction. So interestingly, you can see here in case of heterocyclic substituted compound 1M, so the SNA reaction happened at one of the pyrazole unit, not without touching any sulfone unit. So we got this phenol containing sulfone in 57% yield. Sorry, okay. So next we looked into the possible reaction mechanism. For that we did some controlled experiments with 5 equivalents of base in shorter reaction time. So that is in 2 hours, then followed by the acidic workup. So we got an expected ring opening product in 48% yield along with the sulfonate ester in 24% yield. Probably it is formed by the intramolecular condensation between these 2 units. So next we individually taken this intermediates and subjected under the standard condition, and we got the 2-RL phenol in a quantitative yields. So it suggests that probably the reaction is going via intermolecular SNA reaction followed by the desulfurization process. So we did some post-functionalization of compound 4 with lithium and aluminum hydride. We got thiol and OH containing compound, and as well as another compound 5 in very good yields following the literature procedures. So this is we published it recently. Now I would like to move to the another sulfur compound, so which is commonly used is thionyl chloride. Okay, so this is thionyl chloride Mayer-Schuster rearrangement. Now we are in the process of doing this reaction, but this is alpha beta unsaturated carbonyl compounds can be synthesized by aldol condensation or Wittig-Hans reaction. But the shortcomings or limitations are always we found self-condensation reactions in aldol reaction, and as well as Wittig reactions we got the byproducts. But if you see this propergyl alcohol isomerizes to alpha beta unsaturated compounds, so generally known as a Mayer-Schuster rearrangement if the shifting is taking place, 1,3 shifting is taking place. So this is an atom economical process. Okay, so but if you see here, the strong protic acids are required and expensive transition metals were utilized in this reaction, and generally reactions required more than 100 degrees Celsius. So later on, people come up with metal oxo complexes that such as rhenium and vanadium and manganese molybdenum complexes. So where these reactions were proceeded under milder conditions in a catalytic fashion. So these metal oxo complexes were thought to proceed via 3,3 sigma tropic rearrangement, generate as per the literature. So what it forms is the first the propergyl alcohol will be trans-esterified with metal oxo complex. So to give the propergyl alcohol protected species. So then it undergo a 3,3 sigma tropic rearrangement to give a alinate species. So then the transmetallation with one propergyl alcohol will generate say alinol, so which then isomerize to a alpha beta unsaturated compounds. So if you can just replace the M with sulfur and X with chlorine, So generally what we can visualize is that this is an thionyl chloride, SOCl2. So, but there are a lot of difference we can see with molybdenum and transition metals compared to sulfur. So, but I will come to that point later. Okay, so in one of our project, we thought to synthesize allynyl chlorides. So we found some literature where allynyl chlorides were synthesized using proper gel alcohol, thionyl chloride in the presence of pyridine. So under that condition, we got the very complex reaction mixture. So then what we thought is that we replaced the pyridine. Okay, so then we conducted reactions. In that case, what we found is that the alpha beta unsaturated carbonyl compounds were isolated. So then, so this is the conditions. So decreasing the loading of thionyl chloride, so decreasing the yield of this reaction. And whereas at 80 degrees Celsius, even at very short time, 3 hours, we could able to get this alpha beta unsaturated carbonyl compounds. Okay, so then as we see that the byproduct may be here HCl, so HCl may be catalyzing the reaction. That's why we conducted one reaction with concentrated HCl, but we got a complex reaction mixture in that case. So with this optimization condition in hand, so next we move to the reaction scope of this terminal proper gel alcohol. So the electron donating, withdrawing, as well as hetero-aryl substituted substitution at this aryl position or provided the corresponding product in good to excellent yields. So this is again we got the regioisomeric mixture in case of unsymmetrical tertiary proper gel alcohol. So later on we move to the scope of internal proper gel alcohol. So again the scope is very good and yields are acceptable, and even heterocyclic containing terminal proper gelic alcohol were tolerated and provided the yields in moderate to good yields. So next to get the insight into the reaction mechanism, we did some isotope labeling experiments. What we did here is first we did the deuterium scrambling experiment with this. So then we recorded the NMR so that completely the proper gel alcohol peak is disappeared. So after confirming this, then we have added thionyl chloride 1 equivalent, relatively modified condition, that is room temperature and 12 hours, as we've seen that 1 equivalent required at room temperature. So we got 91% deuterium incorporation at the vinylic position. So next what we did is under the similar, we started with the deuterium incorporation at the terminal position, and under the same condition, so we got this product, so where the deuterium is retained at the aldehyde position. So that means the acidic proton is not scrambling over here, so it is intact. So later on we move to the this O18 labeled proper gel alcohol we have synthesized. So it was synthesized in 63%, 63 atom percentage O18 was there. And so same thionyl chloride 1 equivalent we took at room temperature 12 hours. What we found is here in this case, there was no incorporation of O18 was seen by mass. So it clearly says that the oxygen was transferred from the thionyl chloride, so not from the O18, as there was no O18 in the final product. So this would be a proposed mechanism for this thionyl chloride catalyzer reaction. So what happens first, the production of OH with thionyl chloride, so generates the chlorosulfonate, and probably it undergoes a 3,3 sigmatropic rearrangement to give this alynate ester. So then followed by trans esterification may provide this OH, and ultimately enolization, tautomerization will provide this product. So I hope I convinced you that we used some of the sulfur compound, that is dibenzothiophene dioxide and thionyl chloride in organic synthesis. And I thank DST, SEB and UGC for financial support. I thank CSIR for the fellowship to the students. Because of that motivation, they are working in the lab. And the Central University of Rajasthan for the infrastructure facilities, and lab members, because of them I am presenting my work here. So thank you one and all for your patient listening.
Maybe we can have one or two questions if we have. Yes, we have from here.
A very good evening, sir.
Good evening.
I had to ask, have you tried the propargyl 1 reaction with the secondary or primary propargyl alcohol?
Yeah, we tried with secondary propargyl alcohol,
Yeah.
but it did not work
Okay.
with this. We got some
Primary you tried?
primary we didn't try.
Okay.
We tried with alkyl,
Yeah.
but it didn't work even.
Okay, sir. Thank you.
Yes, we have one more
Sir,
question.
how you label O18 in place of O16?
Sorry?
How you label O18 in place of O16?
We started this one by taking diphenyl methane dichloride, or maybe 1,1-dichloro diphenyl methane. So then we have added O18 water. Okay, simple reaction. We can heat it. So then we can get diol, and which can be ultimately provide the ketone. From that we prepare this.
Okay, I think sir wanted to ask a question. Sir, would you like to?
Okay. Phenyl chloride attack. I go to that. No, not this one. This one, sir? Yeah, in optimization. I think maybe from this trans-esterification. So with one comes here and it replaces. HCl maybe remains here. So like that it is chlorosulfonate may be regenerated instead of thionyl chloride. It did not went, sir.
Okay, maybe we can continue this discussion over dinner. So it's time. Thank you so much, Dr. Bhanachandra, and excellent talk, excellent work. So I take this opportunity on behalf of the organizers to thank both the speakers today. And thank you once again.
Thank you, ma'am. Once again, I request Professor Raki Gupta to present him a token of reverence to Professor Bhanachandra. बेटे मैम के साथ लेके जाइए चलो ठीक
Thank you, ma'am.
Thank you, Professor Raki Gupta. Thank you, Professor Bhanachandra. I now request Professor A.K. Sahu from University of Hyderabad, who is here to kindly come over the stage and present a memento as a mark of gratitude to Professor Raki Gupta for her kind cooperation and coordination in this session.
Is your student?
Yes.
I'm student of it.
Everyone knows this. See, then good thing, na?
Thank you, Professor Sahu. Thank you, ma'am, for your valuable time.
Thank you.
Ladies and gentlemen, today's marathon of sessions is over, and now it's time for a break. I hope you all had a fruitful day. So let's take a break of 15 minutes and relax, and then sharp at 8:15 p.m. we all see you at the dinner time. It is outside the auditorium. Thank you all. Have a good night.
ये माइक वाइक संभालो